A data structure is a collection of data with well-defined operations, behavior, and attributes. It is a special manner of storing and organizing data in computer memory so that it can be used appropriately. In Java, a data structure is a collection of data pieces that provides an efficient method of storing and arranging data in computers so that it may be used efficiently. Through this course, we are going to understand comprehensive Java data structures. The course will progress from the most basic data structures such as arrays to most complicated graphs. We will also explain queue, stack, and linked list principles. Through this course, we will also cover trees, graphs, and heaps, as discussion of data structure would be incomplete without them. Also, each topic will be covered and implemented conceptually using the Java programming language. So without any further ado, let's get started right away. If you haven't subscribed to our channel yet, I want to request you to hit the subscribe button and turn on the notification bell so that you don't miss out on any new update or video releases from Great Learning. If you enjoyed this video, show us some love and like this video. Knowledge increases by sharing, so make sure you share this video with your friends and colleagues. Make sure to comment on the video for any query or suggestions, and I will respond to your comments.
Now let's talk about what is data structure and why do we need data structures. So as you can see, this word data and structure is made up of two words, data and structure. So data is nothing but the information that you want to store in a computer. And structure is how you arrange your data in the computers. Now, depending upon these two factors, right, data and structure, that means how you arrange your data in your computers, you can easily calculate time complexity of your problem. And you can also see, are you using any extra memory depending upon the structure that you're using. Now, if you talk about, let me give you an example of one of the data structures, right, and compare it with another. Now, if you talk about arrays, right, it's a data structure, and the way you arrange your data is different from how you store your data when you talk about linked list. In arrays, you have to always store data in a contiguous memory allocations, wherein if you talk about linked list, if chunks of memory are available here and there, you can use those chunks of memory to store the elements in the form of linked list, or you can use linked list at that point. But if 4 bytes are there, 4 bytes are here, and there are different places, still you can use linked list. But that is not the case in arrays. You need contiguous memory allocation. Now, in both of these data structures, one of them is using CPU much more efficiently. It is using the memory much more efficiently, right? So this is one of the basic difference between the data structures, right? There are n number of data structures available, and different data structures are used for different applications, right? Now, depending upon these factors, right, how you are storing your data in the memory, you can easily calculate what the efficiency of your algorithm, how efficiently you are implementing your algorithm, how efficiently you are doing operations, right? Are you doing operations which are costly, or are you doing operations which takes constant amount of time, right? Are you using your memory efficiently? Are you using your CPU utilization efficiently? Are you using your CPU efficiently? Are you using your memory efficiently? So all these things can be easily deduced from what data structure you are using. So this is the importance of data structures. Now let's talk about, in the next slide, let's talk about what different data structures. Are there any different types of data structures? Yes, there are two different types of data structures. One is a linear data structure and another is a non-linear data structure. Now let's talk about linear data structure. So linear data structures allows us to store data in a sequential manner, like one after the another. Let's talk about this example wherein we are using arrays. It is a linear data structures where one element, let's suppose this is 5, 6, 7, 8, and 9, and one element is stored, and it is stored after the next element, and next element is stored after the next element. So it is stored, all the elements are stored in a sequential manner. Let's suppose this is the address of the memory. Obviously, this will be a hexadecimal number. For simplicity, I'm taking this number as an integer number. Then the next memory available memory location is 104, then 108, then 112. Okay, so these are the available memory locations, and all the data is arranged in a sequential manner. And every element has two neighbors, right? If you talk about this element, right, it has two neighbors, the left neighbor and the right neighbor. And there are always predefined extremes. Like if you talk about array, there will be a starting index and there will be an ending index. So this is always the case when you talk about linear data structures. So let's talk about another data structure that is there, which is known as linked list, right? Again, it will have a predefined extreme, right? It will have a starting node that is known as the head node, and it will have the tail node, which is used to keep the track of the endpoint. So now let's talk about different types of data structures, right? That is linear data structures, right? The first one is the array, which is obviously the linear data structures, and all the elements are stored in a linear fashion. Now, this in this data structures, we can store data in a contiguous memory allocation. That means one after the other. In memory, if wherein you have the scenario where all the memory is occupied and you have chunks of memory. Let's suppose you require 4 and let's suppose you require 4 5s or 20, right? So 20 bytes of memory are required, so you have 8 bytes here and you have 12 bytes here. Can you store the array inside these memory locations? Like let's suppose you are storing 2 elements here and 3 elements here. Can you do it? No, because array require contiguous memory allocation. You cannot store it. Now, what was the drawback? That obviously you cannot store in a contiguous memory allocation. So that is wherein linked list come into picture. Obviously, with array you have a fixed size, right? That is not the case in linked list. The size is variable. That means we have a dynamic size in linked list. Now, if you talk about linked list, if same elements need to be stored in the memory, like these 20 bytes of memory are available, right? 8 bytes are available here and 12 bytes are available here. We can store elements in the linked list, right? So it does not require contiguous memory allocation, right? That was the drawback in linked list. Now stack, if you talk about stack, it follows a principle of what? LIFO, last in, first out. If you have a stack of plates, right? This is an example of stack. Now you have a stack of plates, one piled up over the other. Now, if you want to add an element in the stack, or if you want to remove an element in the stack, you cannot remove any of these elements unless and until you have removed the top, and then one by one you can go down removing one by one these elements. Right now, similarly, you cannot add anywhere, you cannot add here an element because that is not possible. It follows a structure wherein last in is the first out. Let's suppose you want to insert it, you are inserting it here. Now this is the last element that was inserted. Now this will be the first element that is out. Okay, so it follows the principle of LIFO. Now this has restricted how we insert and delete our elements, right? This is the restriction that is there. So this is your stack. Okay, now if you talk about queue, it works in a different manner. Now if you have a queue, let's suppose you are there in a bus station and you want to get tickets, so you are standing in a queue, right? And the person that comes after you will stand behind you. Let's suppose this is me, and the person that comes after me will stand behind me. You will not go in front of the queue. That is not possible, right? Now, and once this person gets his tickets, this will be removed. Now this one will be the first person, again this will be removed, this will be the first person, and so on. So there are two pointers that will keep track of the extremes: the front end, the front part, and the rear part. Now from the front end, always deletion take place. It's also known as an enqueue operation. We'll talk about these operations later on this course. Okay, so now the deletion will take place from the front and insertion will take place from the rear. So if you want to add an element, you will add it from the rear side. That means this side. You're adding the elements. This is your rear side. Okay. And if you want to delete it, you are deleting it from the front. Let's suppose this is 5, 6, 7, 8, 9, 10. Now you have 11 and 10 and still you have memory locations available. Now you want to add, you will update your rear and it will go there. And if you want to remove, you're going to remove this element and you'll increment your front pointer to this location. So this is how you work around with queue. So obviously with these two there, stack and queue, we can implement these data structures either using arrays or either using linked list. Okay, both of them. So obviously there will be some kind of difference in the way you are implementing it. Obviously with arrays you have fixed size, with linked list you have dynamic size. With arrays you have to store contiguous memory locations, right? And with linked list, even if there is no contiguous memory location, you can still use your memory very efficiently, right? So these are some linear data structures, and we will cover all of these linear data structures in this course. Now let's talk about non-linear data structure. So nonlinear data structure allows arrangement of data in a non-sequential manner. There can be n neighbors for a single element, right? So let's suppose this is a nonlinear data structure. We are talking about binary tree, or we are talking about n array tree. That means there are no restrictions of how many child this root will have, or this element will have, or this node, rather to be specific, this node will have. So there will be n number of childs for this node, right? So there is no restriction. For the next node, there can be two childs. So this is what is written. They can have n numbers. There can be n number of neighbors for a single element. And they do not have predefined extremes. Like we saw in a linear data structure, there were extremes, right? You have a front end, you have a rear end, or you have a top in case of stack, right? And you have, in case of arrays, you have to define a size. In case of linked list, you have a head and a tail. But here you don't have any extremes. There is no extreme in this nonlinear data structure. You can store them as you want, and it is not specific that every node will have extremes, right? So similarly, if you talk about binary trees, now we are restricting our number of childs that each node can have. So let's suppose this is a binary tree. So this node at max can have two childs, one on the left, one on the right. And this node can have at max either zero child, one child, or two child. So at max he can have two children, like in this case. It can be empty, or it can have one left child, or it can have, the next node can have a different right child, a single right child. So this is a binary tree. Now you can even restrict it further by arranging these data in such a way that you always store on the left hand side, you always store the lesser element than the root, and on the right hand side you always store greater elements than the root, right? So these are different variations. Now let's talk about different types of data structures, nonlinear data structures that are there. So if you talk about binary tree, right, this is a restriction of storing your data in a hierarchical fashion. So you will be storing your data in a hierarchical fashion, but every node will have either 0, 1, or 2 nodes, right? It will have left child, it will have a right child, or it can have two. This node can have two children. This node is having two children, right? This node is having 0 children. This node is having a right child, thus it has only one child. So this is a binary tree wherein every node at max can have two children, right? Now we can even restrict it further by saying that you can always have, let's suppose the data stored here is 10. So you can always have elements on the left hand side that are less than 10. That means you can have any number of elements, but they will be restricted in such a way that all those elements will be less than 10. So this is your BST, binary search tree. And all the elements that are greater than 10, that means 11, 12, 13, 14, will be on the right hand side. And all the elements that are less than 10, right, 5, 6, 7, will be on the left hand side. Now, then we have graphs, right? Again, a hierarchical data structure. Then we have AVL trees. Then we have red-black trees. So all of these data structures are non-linear data structures. So what is an array? It is a linear data structure. That means elements will be stored in a linear fashion, right? Linear fashion. Now, if you talk about array, let's take an example. Now let's consider that this is how you represent an array in the form of a row, right? And let's suppose it contains elements 1, 2, 3, and 4, right? Now with every memory location, there will be some address, right? So let's suppose these are the four elements, right? 1, 2, 3, and 4. And these are some addresses. Let's suppose this is 100 and this is 104, this is 108, and this is 112. Now, if you talk about memory, obviously these addresses will be hexadecimal. And when you talk about this particular array, it will be somewhere in the memory with four, or you can say 4 bytes of memory for each integer. Now, if I consider this integer, and let's suppose integer takes 4 bytes. Now, these 4 bytes are available for each integer. Now, this is an integer, right? Now, it takes 4 bytes. Now, the second address will start from 104, right? Because now again this will take 4 bytes, then 108. Again, it will take 4 bytes, then 101, 112, right? So in memory, it will be somewhere around. But the thing that obviously you might be thinking, okay, sir, let's suppose this is our memory, and now if we have 4 and 4 bytes, that means 8 bytes here and 8 bytes here. But they are available in chunks, right? This is one chunk and this is the second chunk, and rest of the memory is occupied. Can we store this array in your memory, in the memory? No, because it needs contiguous memory allocation. That means when this is the scenario wherein you have memory allocations or memory locations available in a one big chunk, right? That means if you talk about this array, it requires 4 into 4, that is 16 bytes are available, but and they are available in a contiguous memory fashion, right? Or they are available in such a way that it is a one single chunk of 16 bytes. Okay, so then only you can store the elements at that location. Now, obviously, for simplicity, I'm taking this addresses as a number, integer number, but in reality, those are hexadecimal numbers. Okay, so it is easier for me. Okay, so now one more thing is that the elements are stored in a linear fashion, right? But can we access elements randomly? Yes, with the help of indexes. So if you talk about this array, right? 1, 2, 3, and 4. Obviously, this there will be a name associated with this array, right? Now we have index 0, 1, 2, 3. Now, why indexing starts with 0, or why there is a 0 and indexing always starts with 0? Now, the question is that, right? Now, let's try to demystify this fact that why indexing starts from 0. Why not it starts from 1? Now, if you remember, right, I told you that there will be a name associated with this array, that is ARR. Now, this ARR is nothing but name of the array, and name of the array represents, right? It represents its base address, right? Now the base address of this was, earlier we spoke about it, so it is 100, this is 104, this is 108, and this is 112, right? So now this is 100. Now, so let's talk about how you access, we will talk about in the coming slides, we will see how to declare and initialize our array. But let's suppose if we talk about how to access this, we use array and then the subscript and then the index. Okay, the index is 1. Now I told you name of this array represents the base address, so base address is 100. Now plus 1. Now this 1 represents 4 bytes. Okay, so the 4 bytes, then what internally happens, it boils down to 100 plus 4, that means 104. Now 104 is not the first location, it is the second location. Okay, now similarly, if you talk about accessing the second element or third element in the array, it boils down to what? Array of 2, which is nothing but 100 plus 2. Now this 2 is nothing but 8, right? 100, 108. So you will be accessing the third element in the array. Now how can you access the first element? So ARR of 0, now it boils down to 100 plus 0 because there are no bytes, right? So it boils down to this, that array indexing starts from 0, and now you know why. And this is how you can access elements randomly, so with the help of these indexes. Okay, so now you might be thinking, okay, now we have an array, can we store different elements, right? Can we store, let's suppose this is the array, can we store, in this we will store integer, then we will store a floating point number, then can we store a character? No. If you talk about any particular array, let's talk about this array. Now the data type or the type of data that you can store in this array will be homogeneous. That means you can only store similar elements. Okay, so these are some facts and this is how array works. And what are the addresses, what are the indexes? Can you store different elements? No, you can only store similar elements in the array. Now let's talk about the applications of array. Now you might be thinking, sir, why do we need this array? What is the reason that we are using this array? So basically, when you talk about arrays, now obviously when you have a scenario wherein you want to store your elements in a linear fashion, right? And that too, you want to store them in a contiguous memory locations, right? So that you can use your CPU or you can use your memory efficiently, right? Not the CPU. You can use your memory and you can utilize your memory to the maximum, right? So you want to utilize your memory efficiently. At that time, you can use this. But obviously, it will have some drawbacks, right? It will have some drawbacks. That is why we have different data structures, right? So if you want to store your data in a linear fashion, you can use arrays. Okay. Now it is also suitable for the scenarios wherein you require frequent searching, right? If you want to search an element in an array, you can directly go and access these indexes one by one, right? So in a linear fashion, you will access, okay, is this the element that you're looking for? No. Is 20 the element that you're looking for? No. Is 30 the element that you're looking for? No. Is 40 the element that you're looking for? Yes. One by one, you can access all those elements and try to search for the element that you are looking for. Okay. So it is suitable for applications which require frequent searching. Now let's talk about one dimensional. So if you talk about 1D array, it can be related to a row, like we saw in the example, right? So that is what is a one-dimensional array. It is represented in the form of row, and we have addresses like 104, 100, 104, 108, 112, and 116. And indexing will be obviously 0, 1, 2, 3, 4, and then there will be a name associated with this array, which is ARR, and then you can store the elements in this array. Let's suppose here it is an integer array. Okay, so you can store only integer elements, and the size of this array is 5, and you have stored the elements 1, 2, 3, 4, 5. So now it can be related to a row wherein elements are stored one after the other, like you see. You have 1, then you have 2, then you have 3, and there's those all of these numbers are in a contiguous memory, are available in a contiguous memory allocation. Okay, now when you talk about 1D array, there is only one index used, right? When you try to declare and initialize your array, at that time you will use one subscript. Okay, so how you can use that? So let's suppose if I talk about this special array that I have defined here, right? You will define it ARR, and then the sub or the index is that the number of elements that are present here, which is 5. So only one subscript will be there, or one index will be used. Okay, so this is how you declare your array. So now let's talk about the declaration and initialization of this array. So obviously, when you talk about the array, there will be a name associated with the array, and then the data type. Are you going to store integer values in that array? Then the that one subscript or one index that we use, and then definitely the size of the array. So this is how you declare your 1D array. Now, how can you initialize it? There are different ways with which you can initialize it. Obviously, here you are declaring it. Then you might use a for loop to initialize all the elements. Or you can declare or initialize your array at once. So how do you do that? So you will write, and let's suppose this is the integer array, and you don't have to specify the size. You can directly write the elements, right? And those elements, let's suppose those are 1, 2, 3, 4, and 5. In this case, when you're declaring and initializing your array at once, at that time this size becomes optional. You don't have to specify explicitly the size of the array, but obviously the size of this array will be 5. Okay, now since you are declaring and initializing it at once, so this is optional. But in the case wherein you are not initializing it, at that time this size becomes very important, and you have to mention this size explicitly. Okay, now let's talk about two-dimensional array. So also it is known as 2D array. So it can be related to a table like this, or you can also say a matrix wherein you have rows and columns, right? Now in this, elements are stored one after the other in such a way that you can think of it as a 1D array. Now this is what 1D array, right? As we have already seen it, right? And inside this one ND array, you have another 1D array, right? Now this is known as 2D array. So now how it works, right? Let's suppose you have numbers over here. and you have four numbers, 1, 2, 3, 4. Then you have 5, 6, 7, 8. Then you have 9, 10, and 11, and 12. So this is a 2D array of having, and this will be similar to what? Of having three rows, right? You will have three rows, not four rows. You will have three rows, and in those three rows, right, you will have what? Four columns. One, two, and so numbers will be like this: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. Okay, done. So now obviously this will have, let's suppose this is a zero based indexing, and this will have a zero index here, one index here, and one. Now internally what is happening, it will be a 0 0, then it will be a 0 1, then 0 2, 0 3, then 1 0, 1 1, 1 2, 1 3, then 2 0, 2 1, 2 2, and 2 3 indexing, right? So similar to that, we will have this index will be 0 0, this will be like this, and this will be like this. So if you want to access the element that is present at this location, what you will do, you will run two for loops, right? One will be starting with from a, let's suppose one will start from I equal to 0 to the length of this outer array, that is 3 less than 3, right? So and the another from 0 to the number of rows that are there. Okay, so this one will be the outer loop, this one will be the outer loop, and this one will be the inner loop. That means the number of columns that are there. So this is for row, and this will be for column. That will start from 0 to less than 4. Okay. So this is how you iterate, and it will be similar to this. And now what about the addressing, right? What about the addresses that will be there? So this will be, let's suppose if this is 100, now this will be 104, this will be 108, this will be 112, this will be 116, because internally it is treated as if they are again in a contiguous memory location, but this time around you have a 1D array, and inside that 1D array you have another 1D array. So for declaring it, you will use two subscripts, right? So it will be something, the name of the array, then two subscripts. And now this will represent the number of rows, and this will represent the number of columns. So in this case, the number of rows will be 3, and in this, and the number of columns is 4, right? So this is how you declare your what? A 2D array. So dimension depends upon the number of subscripts you are using. So this time around, we are using two subscripts. Now, let's suppose you are using three subscripts, right? So similar to like this, 3, 3, and 3. Okay, so this time around, this is a 3D array. And similarly, you can have multi-dimensional array, right? And you just need to keep on adding the subscripts. That's it. Okay.
Now let's talk about the implementation of arrays in Java programming. So before getting into the IDE and writing down the code, let's try to see what is the problem statement. That is what code exactly we are going to write to learn implementing arrays in Java programming. Now the problem statement is that we have to write a program in which we are going to create one-dimensional array. Okay, it will hold integer values, and those integer values should start from 1 and store till maximum number it can fit into. Meaning, suppose the size of the array given is 10, then it should store numbers starting from 1 till 10. And also we'll learn how to access those numbers once it is stored in a one-dimensional array, and also display them as an output. So this will be the first part of the problem statement, and then we'll talk about how to create a two-dimensional integer array and how to store number into it, integers into it, starting from 1 to the maximum value we can store into it. And as we know, two-dimensional array is a matrix. So it will start from first row and first column, and then keep on storing the numbers going across each row till the last row and last column. Once the two-dimensional array is created, we'll be again writing down the code that will help us access those elements. And then we'll implement the search and sort operation. That is, we'll be sorting down in ascending order each element of the one-dimensional and two-dimensional arrays, as well as we'll implement search on the given array. Now let's switch to IDE and implement this code. So I'm using Eclipse IDE to implement this Java code. And here I have already created a class that is array solution. And there is a main method, public static void main string args. Now, here itself inside the main method, we are going to write down the code that will help us create a one-dimensional array first. So as we saw, the problem statement had two parts. The first part was to create a one-dimensional array and access the elements of that one-dimensional array. So how to do that in Java? Let's try to see that. So first you have to define or declare a one-dimensional array. To define that, you have to give a data type first using the square brackets. The square bracket represents that it is a one-dimensional array. One square bracket meaning one-dimensional array, two square bracket meaning two-dimensional array. Then space and then name of the array. Suppose A1 I want to give the name of my array. Okay. Then after this we'll be using new keyword. New keyword in Java helps us to create any object for a given class, or it helps to allocate space in the memory. Okay. So new and then again int, that is the data type for the array. And in the square bracket, we should define the size of that one-dimensional array. So here suppose I want the size of the one-dimensional array to be 6. And then square bracket will be closed and semicolon. So this is how we will create a one-dimensional array in Java. Now, how to store the elements. Now comes the point of storing the elements or numbers into it. As it is an integer array, it will store numbers, that is integers. So I have to store integers starting from 1 to the maximum value it can store. So to store the element, there are two ways. Either you can refer any integer by direct the index number of it, right? So the index in array starts from 0 and goes till the maximum. Suppose the size of the array here declared is 6. So it will go from 0 to 5. So either you can refer like A1 and then you can use 0 as a 0th index and assign some value here 4 and then semicolon. This way you can store it for each index, that is A1, 0 will store another number, maybe 5. But as our problem statement says that we have to store numbers starting from 1 till the maximum value it can store, right? So for that, it will be easy for us to use any looping condition. So Java has so many constructs where we can loop around a given code. Okay, one of the construct is your for loop. So we'll be using for loop here. So the syntax for loop is for keyword, then any variable which we'll be using to iterate over a given array. So array should start from where? I should start storing numbers or digits from where? From 0th index. So the value of I will be 0 because I is the variable which I'm using for iterating over the array. Then there will be semicolon. Then the next condition in the for loop is stopping condition, like till where this I should iterate over. It is starting from 0 and where should it end? So that ending condition should be there, the second parameter for. Okay, so I should end at the length till the end of the array I have to store, right? So that is the length of the array. So there is a function in Java that will help us create or calculate the length of a given array, that is a1 dot length. Okay, this will tell the exact length. Why I have given less than sign here? Because the length will be 6. That is the size of the array. But as I told you, index starts from 0 and it will go till 5. So we should not store at 6th place, right? Because 6 doesn't exist. It is starting from 0. So it will go till 5. If it starts from 1, it will go till 6, right? So that's why I should be less than only a1 dot length. Then the next parameter in the for loop is by what you want to increment I every time. Okay, by like you want to go to the first element, then second, then third, then fourth, or you want to go to first element, then third directly, or fifth directly. So that condition we have to put as a third here. So this will be, I want to go just like increment 1 each time. So I plus plus. So I plus plus meaning I will increment each time by 1. It will start from 0. It will increment 1, it will go to 1, then 2, then 3, and so on. After that, you have to give a for loop, curly brackets. Okay, this implies the body of the for loop. In this now I will write a code to store the element into it. I want to store in A1 ith location. I want to store what? Okay, I'm using a variable over here, count. Okay, this count we can initialize it here itself as count is equal to 0. So this count will start from 0. Okay, it should be of type int because that is what we are going to store in this array. So this, it will start from 0. So at when I is equal to 0, that is at 0th index of array, it will store the value of count, which is 0 initially. Then it will increment I. Then second location, it should store 2. That is, I should increment this count every time. So I'll increment, okay, as it is, we can start it from 1 because I want to store number from 1 to n, okay, 1 to whichever maximum it can store. So it will start from 1 and then every time I'm going to do count plus plus. It means it will increment count. So it will store 1 first, then at second place it will increment itself and store 2, then increment itself and store 3 and then 4 and then so on till the last place in the array. Okay, so this is how we'll be writing down a code for storing numbers into a given one-dimensional array. I hope this is clear. Now, we'll come out of this for loop. We have to access the elements of this one-dimensional array. To access and display, what we'll do, again we have to use for loop. Every time to iterate over an array, we have to use some looping construct. Okay, and I'm using for loop over here. So again, I'll go from int maybe j this time. You can take same variable also, no issues, but I'm taking different variable, guys. So j will be again less than here a1 dot length, okay, and semicolon, j will increment every time with 1. And in this, I have to access it, that is I have to display it. So I can do system.out.println, okay, syso if you type and press control space, guys, in Eclipse IDE, it will write the full form of it automatically. So system.out.println, and then here I should print what? A1 of j every time. Right, so it will display it, and as I have given here print ln statement, it will print 1 in each line. If I want to print all in the same line, you can do like this, plus, and then you can give a space here. So it will give a space between every number and it will display it. Save it and execute it. So once you will execute it, you will see the numbers has been stored starting from 1 to 6, because 6 was the size of array. So it started from 1 and stored till 6. If you want to change this, you can do, suppose 8 is the size, there won't be any other change. You will just change the size here and the for loop will take it till the end of the array, that is till the length of the array from 1 to 8. Okay, so this is the implementation of one-dimensional array. Now coming to the second point of our problem statement in arrays, that was about your two-dimensional array. So once we are done with two-dimensional, then I'll talk about the search and sort over this one-dimensional and two-dimensional arrays. Now I will comment this line here. Okay, and we can go ahead and from here we can write down the code for two-dimensional arrays. So here I'm going to write creation and implementation of 2D array. Okay. So what you have to do here is same thing, data type, that is which kind of data you want to store in the two-dimensional array. Then as it is a two-dimensional array, it should have 2 square brackets. Okay. Then again the name of the array, suppose A1, again same name I'm going to give here, and then equals to new operator to allocate space to it, and then again this the type of the array which you want to create, and then again two arrays here, I mean 2 square brackets here. You have to provide the size again, guys. So let's have 3 and 4, so 3 rows and 4 columns matrix or a two-dimensional array will be created. This is how we create a two-dimensional array. To access this, as there are not just a single column or a single row, there are columns and rows, so we need two variables to iterate over it. So first variable will be used for iterating over the column, and then the second one for rows, or first one for rows and second one for column, depends upon how you write the code. So it will start from 0 in the any matrix. The first value is 0th row and 0th column. So it will start from 0 itself. So it will go till a1 dot length, right? And then it'll increment I every time by 1. So I plus plus, right? Now this is to iterate over the row. Now to iterate over the column, we need one more variable. So one more for loop. Let's take it as j, suppose. Starting from 0 again, 0th column it will start, and it will go this time till each row it has to start from 0 and go till end. Then next row start from 0, go to the end of that particular row itself. Getting it? So it will go till the length of each row. First row, then second row, third row, fourth row, this way. So every time it should start from 0 and go till end of each row. Getting it? So it will go till where? A1 of I dot length. Then semicolon, and it will increment every time only one value. So j plus plus. Getting it? So you have to be very careful here with the ending condition. That is where the loop should end. I will start from 0 and it will end at a1 dot length. And j will start from also 0, but it will go till end of each row every time. First row, second row, third row. That's why it is a1 I of length. Clear? Now in this, to access or to store values, so first let us store the values, then only we can access it and display it. To store the values, the syntax is again same, just that you have to use I square bracket and then j square bracket and equals to, we'll store some value here. Let it be a variable count. So you have to again initialize also, guys, here. Count, let it initialize to 1. And as I want to store numbers starting from 1 till the maximum it can store, that is 1, 2, 3, 4, 5, 6 till the end. So I have to increment count also every time. This is how it will look like. Okay. Now to access it again, this is to insert the element. So now insertion is done. Now let us display the result. To display again, guys, you have to iterate over a two-dimensional array over a matrix. So the same condition, that is for loop, will be used. I and j, two variables, to iterate over the row and column respectively. So I'm just copy pasting the same thing from here. Okay. You have to write it down again. Okay. So yeah, to display it again in Java, there is system.out.println is a command you can say, or println is a function. Out as an object and system is a class which has out as an object, which is used for calling the println function. So in this, we can now display or call the array, that is a of ij. Getting it? Now, suppose you want to, like this, if I execute it, you see here what you will get as an output. So you can see it starts from 1 and it goes till 12. As the array was 3 to 4, 3 rows and 4 columns. So it will start from 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Right? 4 in each row. But you can see here it is displayed as like one element in each line, right? Or each row. I wanted to display it like a matrix, like rows and columns. Then only you will understand that exactly how many rows and how many columns were there. You can, little bit of formatting is required here, nothing much. So you can just use little bit of formatting constructs. Once you come out of this loop, you can put again a command of system.out.println, and I hope this should work. Let's see. So yes, you can see here the output as 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Now, as we saw how to create a two-dimensional array, how to store elements into it, and then how to access it. Now let's talk about the third point of the problem statement, that is sorting and searching. How to implement sort and how to implement search over a given array. Okay. Now to implement sorting, there is an inbuilt method that is your sort itself, that is defined inside array package of Java, which we can directly use it. Okay, and inbuilt this sort method uses quick sort basically, but we can directly use it just calling it as a method. Okay, so we'll see that, and then we'll talk about the search. How can we do over a given array? So here also I will talk about how we can create a array in a little different way. Okay, so in this also you have to define a data type, then the name of the variable, that is array, and then equals to new data type again, square bracket. After this, don't give the semicolon. You can put here the elements which you want to store into that. So now as I am going to store in sorted order, then Right now I'll be storing it in some random order so that later on when it is sorted, we can get an idea that, okay, fine, it is sorted. So let's take it 362958 or some more number, maybe 1. Okay. Then you put semicolon over here. Okay. So this is also one way of creating a one-dimensional array by just directly putting the values which you want to store there. Now, inside the array class, there is a sort method. Okay, so you can see here sort, it takes different data types, double, char, byte, float, int. So I have to take int here. So the array, it is already taking a1. So that's it. So I have to implement sort over a given one-dimensional array a1. So a1 will go as a parameter to sort, and as it is defined inside class arrays, so you have to call using arrays and then dot operator dot. Now if you want to print and just check that, is it actually sorted or not. So let's do one thing. We can first call or print the elements here itself, and then again after sorting we can print and just check that is it actually printed or not. Okay, it will go till the length of it, and then we'll do I plus plus, and in this we have to call system.out.println and then a1 of I. Okay, again we can call this for loop. So I'm just copy pasting it over here once it is sorted, and so that we can get an idea that is it actually sorted or not. So let's see, we'll execute this code and check. Okay, once again I will just not use println here so that it comes in single line and we can see the output properly. Okay, 1 second. So you can see here earlier the numbers was 3629581, right? And after that the numbers are in sorted order 1 2 3 5 6 8 and 9. So this is an inbuilt sort method which you can use to sort the elements of a given one-dimensional array. Now if you have to implement search over it, then how will you do it? Let's write a code for it. So okay, we'll write it inside the main method itself. Guys, to implement search, there is no inbuilt method which I'm going to use here, but a simple logic of linear search can be applied. Don't try to now worry about what is linear search. Normally, if I ask you to search a given element in an array, like suppose in this array, if I ask you to search where is 2, what will you do? You'll just start looking from the first one and then go until you find 2, right? That's a simple logic which we are going to write the code. So again, to iterate over a given array, we have to use a variable to iterate over it and a for loop. Before that, let's create a method first. So public void search. In this, I have to pass what? The array which you want to search and the key which you are looking for, right? So it is int a, or you can write array itself here, and then int key which you are looking for. And then inside this, you have to write okay guys, so this has to be written obviously outside the main function. You can't have another function inside a function. So yeah, I should have written it here. Yeah, let's see now. So search, let's have a return type to be of int. Okay, so that it will return the index once the given key is found. Okay, so here what I'm going to do is, to implement search, as I said, we'll need a for loop. Okay, it will start from the initial value, that is 0, and it will go till the length of the array. Okay, and it will iterate every time with just one value. Now inside this there comes the main logic, that is you have to search what, that the each element at a given index starting from 0, is it equal to the key which you are searching for. Then we need what, if loop for that. So if array at ith index, is it equal to the key which we are looking for? If it is equal, then it should return the particular index, that is I. Else, or you can, no need of else loop here, you can just come out of the for loop, and if doesn't found, like it scans the complete array and it doesn't found, then it should return -1, right? And that is your done with the method. That simple was it. Now we'll call this method in the main method here. To call this, we have to store the value returned from it, maybe the index value, into the index value is a variable which will store whatever is returned from the function search. Okay, so we'll call the search function here and we'll pass 2 parameters because this function takes 2 parameters. So what we need to pass, we want to search over this given array itself, A1, and we want to suppose search for let's say 9. Okay, so it will be called. Fine. Let's check with this. Is the spelling correct? Yes. Okay. Okay. So we need to have this as a static because we are calling it from the main method, which is a static reference. So from a static field, we cannot make a non-static reference in Java. That's the reason we have to make it as a static. Now, once it returns, then we have to print it. To print again, I'm going to put a condition here that if suppose the function returns -1, it means there was no element, right? If this index value is equal to -1, it means what? It means that there was no such element which you are looking for. That is element not found. Else, it will print that the element is found and is at index. Whichever is the particular index, we can print that. We can print what? Index value. Because the index which is returned is stored in the variable index value. Right? So this is the small code for searching a given element in a one-dimensional simple array. Let's try to execute and see if this gives the output. So yeah, it says that the element is found and is at index 6. Is it correct? Actually, we have sorted it already, right? So, okay, if I just comment this for you to understand it in a better way, let's comment this, okay? So once it is commented out and when we execute this again, what you found is this is all the elements of array like 3, 6, 2, 9, 5, 8, 1, and then we are looking for 9 here, and 9 is at index 3, right? 0, 1, 2, 3. And if you search for something which doesn't exist in this, suppose 11, then it should print that element not found. Let's correct the spelling here. MENTS, yeah. Element not found. Got it? So this is a simple code for how to create a one-dimensional array, how to create a two-dimensional array, how to access the elements of a one-dimensional and two-dimensional array, as well as how to implement sorting using an inbuilt sort method, as well as how to implement search. So technically or ideally, we have used quick sort, which is already implemented internally using sort method in Java. And in search, we have implemented linear search, which is a simple comparison of each element of an array to what we are looking for.
Now let's talk about advantages of arrays. So obviously when you have indexes associated with the array, right? We have indexes. So it is easy for us to access any element, right? With the help of this index. So if I want to access the third element, you can directly go ahead and say ARR of 2 in the 1D array, right? So you can directly access elements with the help of indexing. Similarly, it is easy for us to iterate through it, right? With the help of one for loop, we can iterate through all the elements, right? One by one that is there, okay, that are there in the array. And similarly, if you want to do the sorting, we can go ahead and easily iterate through these elements one by one and look for an element. If we are trying to search an element in the array, let's suppose uh, we are searching for 3, so one by one we will search, okay, is this element 3, 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 right? And if this element is 3, we can easily search. And also for sorting, right, let's suppose we want to sort this array. What would it be? It will be simply what, if you have 4 here, 3 here, 2 here, 1 here, and let's suppose you have 0 here. Okay, so now you want to sort this in the ascending order. So what you will do, you will use two loops. One will focus on this first element, and then the second one will compare all the elements. Okay, and then at the end of this thing you will have the largest element at the end of the array. So sorting, iteration, searching, it is easy in array. You just have to iterate through all the elements one by one. Now it is a replacement of multiple variables. Now what do you mean by this thing? Let's suppose you have an integer, or let's suppose you want to store the roll number of 10 students, right? So what you would have done earlier, prior to what, when you don't know the arrays, what you would have done, you would have said roll number 1, and then it's or you can say s1, s2, s3, s4, and one by one you can store the roll numbers in these integer variables, right? So as soon as our students increase, now let's suppose we are talking about here 10 students. Now as we talk about 100, now what happens if we talk about 500? Are you going to uh, write 500 variables, integer variables, s1 starting from s1 to s500? No, it is a very inefficient way of doing so, right? So instead what you can do, you can create an array, and you can create an integer array and name it student, and therein you will have the size, which obviously represents the number of students that are there, and in this case it will be 500. Now if you want to change it to tomorrow, if you want to change it to 600, you can go ahead and easily change it to 600, right? So it is the replacement of multiple variables. So this is what it means. Now let's clear the screen, and now let's talk about disadvantages. There is one disadvantage that can be easily noticed is the size. Now obviously when you're talking about 1D array, right, the size, or any array, right, the size is there, right? So you cannot exceed this size. The elements cannot exceed this. So let's suppose you have the size is 5, you can only store 5 elements, right? You cannot go more than that or beyond that. Now if you have a size 100, and now you're trying to store only 2 elements, anyway the 100 memory allocations will be there for this array. That means you are wasting your memory, you are not utilizing it efficiently. Okay, so this is what it means, that size is fixed and you cannot store more elements, and if the capacity is more than occupancy, most of the array gets wasted. Okay, so these are two things. Apart from this, you need a contiguous memory allocation. That means if chunks of memory are available here and there, you cannot store an array which is, let's suppose here you have 16 bytes and here you have 16 bytes. Only if you have an array which is of 16 bytes, that means if you have an array of size 4, that array can be stored here. But if you have an array of, let's suppose, size 8, you cannot store 4 elements here and 4 elements here. That will not be happening. Okay, that cannot happen rather. Okay, because it needs contiguous memory allocation. So there is one more disadvantage, and the last but not the least is that insertion and deletion is difficult. Now why do you say that? So let's suppose you have an array and you are having in this array 1, 2, 3, 4. Now let's suppose you want to insert a value 0 at this location. Now what you need to do, you insert the 0 and rest of the elements, every element will be swapped. So swapping is required, right? Swapping is required. Plus there should be memory available so that you can store that element. Else if there are only 4 elements and now you want to store 0, and the size is also 4, at that time around what happens, you will store 1 and rest of the elements will be swapped and you will be losing this value. So it is very difficult to insert the value. Now same thing will happen when you're trying to delete, but at that time you will not be losing data, but yes, swapping is required, right? So let's suppose you want to delete this location. So what you will do, or delete this number, what you will do, you will overwrite this with 3, you will overwrite this with 4, and let's suppose if there is 6, you will overwrite this with 6. So at the end you will have 1 3 4 6, right? 1 3 4 6 and one memory allocation. is there, and it will contain the same element, that is 6. So next time around, you will just overwrite this. So again, the swapping is required. So it is very difficult to insert and delete an element in the array. Now let's talk about stack. What is stack? Stack is a linear data structure. That means if the elements are stored in a stack, they will be stored in a linear fashion. Now, it follows the principle of last in, first out, also known as LIFO. That means the element that entered at the end or in the last will be the first element that will be removed. As simple as that. Now, you might be thinking, okay, it follows the principle of LIFO. Now, that does that mean its removal is restricted? Yes, it is. So you can only access the top of the element. That means this element is accessed. And how can you keep a pointer or keep a track of this top? With the help of this top index, this pointer or iterator that is kept for the tracking of the top of the element. So once you have entered this, the top will go up. Then you have entered this, the top will go up. That means you're incrementing top. And finally, the top is here when you enter this. Now, since you're removing this, that means only you have the access to the top of the element. You are removing this, then you will decrement your top. Okay, that's it. So with the help of this top iterator, you can keep the track of the last element, and you can also keep the track of the elements which entered in the stack. Insertion and deletion can take place only from the top, which is obvious, right? Let's suppose you're trying to insert the element. What you will do, you will increment your top and then insert your element. And if you want to remove it, you just decrement your top. That's it. So this is what you mean by pushing and popping, right? So the elements that you are inserting, that is nothing but your push operation, and you will increment your top. So elements you are removing is nothing but your pop operation. If you take an example of stack of plates, right, one after the other, the plates are stacked upon each other, right, one by one. So you can only access the top plate and you cannot access anything that is in between. So that is the restriction that is there. So in terms of stack, there are four major operations: push, pop, is empty, and peek. So push means nothing but to insert an element in the stack. So you are inserting. And now you might be thinking, okay, what is the time complexity of this push operation? Since we can keep a track of this, the top of the stack, right? With the help of this top, we can have a track of what are the elements that are on top, right? So only, let me just show you. Since the top is here, right, at this, now you want to push, so you just update your top, that's it, right, and you insert value. So this takes a constant amount of time. So inserting a value takes a constant amount of time. That is the big O notation, right? Big O of 1, that is constant amount of time. So similarly, we can remove the element, and it can be done with the help of this pop operation. That means we can remove this top of the element just by decrementing our top. Once we decrement our top, this top of the stack element is removed. So now again, we are just accessing, or we are just manipulating this top in a constant amount of time. Again, this push operation and pop operation, both of these operations take big O of 1 time. That is the constant amount of time. Similarly, if we check is our stack empty or not, we just check the value of this top. If this top is having any value other than -1, that means we have elements in the stack. So we return false. So again, this is empty operation, takes constant amount of time. Similarly, peek is nothing but it is similar to pop. Only thing is that we will not be removing, or we will not be overwriting the top of the stack value. We will just see what is the top element. That is, if we are implementing it with the help of array, we will see that it can be implemented using arrays and linked lists. So if we are implementing it with the help of array, as we have already covered it, and if we are implementing it linked list, we'll see both of these implementations one by one. So let's take an example wherein we are implementing it with the help of array. So what we will do, we'll just return this value. That's it. We will will not be either removing it or overwriting this value, will be just returning the top of the element. So peek is similar to pop, but the only thing is that in pop we are removing the element, in this we are not removing the elements. Again, this will take a constant amount of time. So all these major operations are taking constant amount of time. That means with the help of this top iterator, we can do all these operations in a constant amount of time, because he is the guy who keeps track of what are the elements in the stack, and with the help of this we can remove the element from the top of the stack, we can add the element from on the top of the stack, we can push, we can pop, we can check if the stack is empty or not based on the value of this top, and we can also peek the element, right? We can take a peek of the element, right? So with the help of this top. Okay, so again, that is in a constant amount of time. Now let's talk about the applications of stack. Now, whenever we use recursion, right? Whenever you use recursion, what happens internally? A stack is created, right? Let's suppose you have a function call, and in that function call, you are calling this function again. Obviously, this will be called from the main function, right? Let's suppose this is our main function. Let me just erase it and write it in. Yeah. So this is our main function, and it's calling this function, and this function is calling this function. That means it's calling itself again and again and again, unless and until a base condition is reached. Right now, once the base condition is reached, it starts popping it out. Right. This is all these are push operations. Right. And now pop is performed one by one, unless and until all the function call return its value, and finally it returns to our main function, and finally then main function is popped out of the stack. So whenever we are using recursion, a stack is maintained. And we also find out when we talk about recursion more in depth in this tutorial, we'll see how we to create this activation record that is created, and activation records are created, and with the help of these we can easily detect what are the statements that are yet to be executed, okay, in a function call. Let's suppose you have three statements in a program, and one of them is to check the base condition, second is to the function call itself, that is this function calling itself, this is a function outer function, and in that function you have three steps, and then this is a simple print statement, okay. Then let's suppose this is an activation record and one, two, three. So this is checked and this calls the function again. Again, an activation record is created. So again, one, two, and three are checked. So this is checked. Again, this calls a activation record. So now these are all push operations. So once it returns, now the pop is performed. Now it returns to this point and it executes this value. That is prints out the value, whatever is the value, and once it is done, so it returns to the function who called it, and once that is done, this will be popped out of the stack, and then once this is executed, it will return to the main function. So in recursion, stack is maintained internally. Now what about parsing? So whenever we talk about automata, right, automata is one of the subjects in computer science. Therein the parsing happens whenever your program is divided into tokens. Tokens are nothing but keywords. What are the keywords in this program? What are the conditional operators in this keyword? What are the constants? So all these in your program, all of these things are divided into tokens, and then parsing happens. Okay. What about the browser, your application? Whenever you open up any website, right? Let's suppose you are opening Great Learning Academy. Before that, you go into the Google Chrome, you type in Great Learning, therein you will get the link of Great Learning Academy. Click on it, it redirects you to the Great Learning Academy. Then in Great Learning Academy, you look for the popular courses, or let's suppose IT and software courses. When you click on it, let's suppose it directs you to the another course that is related to IT and software. In that you have, let's suppose, C. You click on it and it will direct you to the C program. So one by one, these are all push operations: P1, P2, P3, and P4. All these are push operations. Now once you press back, what happens? You pop out, this pops out of the stack, and you go on to this courses. Again, you press back button, you go on to the Great Learning Academy. So these are all pop operations, and finally when you click on the back icon, you go on to the Google page, right? So this is all that happens while we are working in browsers and in editors. Whenever you do redo operation or undo operation, again a stack is maintained. So these are all the applications of stack.
Now let's talk about the implementation of stack data structures in Java programming. Before getting into the IDE and writing down the code, let me tell you what is the problem statement. That is what exactly the code we are going to write for in stack data structure. We are going to write a program which will be implementing the following points. That is, we'll create a stack first. We'll see how we can create a stack in Java and then implement the different methods, different operations which we can perform on stack using the different inbuilt methods which are already there defined in different packages of Java. Then we will see how we can access those elements. Accessing the elements of the stack involves a different concept. So that concept, how we are going to code into, will be talked about. And then we'll be implementing the following given 7 functions. That is push, pop. We'll check if the stack is empty or not. Peek, search, size, and sort. Before getting into the implementation part, I would also like to tell you that stack is an inbuilt class which is defined in Java programming. This is the inbuilt class. Okay. There is a collection framework, or you can say a collection interface, that is implemented by stack. Okay. So stack implements the different methods of collection interface, and there is this complete concept of collection framework in Java which will help to implement different data structures. One of them is stack. Also, there is a class called as vector in Java packages. This vector class also has certain methods which stack extends. So stack has different methods. Some will be using from the vector class and some from will be implementing it which are there in the collection interface, and try to see how we can perform different operations on a given stack data structure. Now let's get to the IDE and try to implement it. So I've come to the IDE, that is Eclipse IDE, and here already I've created a file that is having a class called as stack solution, and also the main method, that is the method which is mandatorily required in any Java given code, that is your public static void main. This is written. Now inside this main method itself, we are going to perform all the operations on everything related to stack. So the problem statement we have discussed already. Now let's try to code it down. So to create a stack, we'll be using the inbuilt stack class. And to create a stack for a given class, we have to just simply do that, create an object of a given class. Okay, and the class is your stack. So stack, name of the class, space, the object which you want to create for this stack class, that is the name of the stack. Suppose S1. Okay, then new keyword, every time we'll be using new keyword to create an object that does actually what? Allocates memory to that object. And then we'll be using again stack. This is one way of creating an object. But here there is no way to define, this is an object. There's no way to define which type of data will this object consist of. So there is one more method or one more way of creating stack object. That is stack, that is name of the class, and then you have to give greater than and less than sign. In between this, you should write the type of the data will be storing in the stack. Suppose you want to store all numbers, that is integers, or you want to store all characters, or you want to store all the string values, or floating values, that is decimal numbers. So accordingly, you will give the data type here. Data type should be the classes, that is the wrapper class called as in Java, right? That there is a wrapper class for every data type. That wrapper class you have to use. For example, if I write int here, it won't work. It will throw an error. So I should use what here? Integer. Getting it? And then the name of the stack, that is S1. Then again new keyword. And then again stack class. But here you have to use again greater than and less than sign. And then the round brackets and then semicolon. This will specify that the stack S1 contains all the integer numbers. So this is how we create a stack. Simple. That is creating an object or stack class. You can implement stack using one-dimensional array also guys, but here I'm using the inbuilt stack class. Now in this, you have to perform different operations. To perform different operations, the first one is let's insert some value into the stack. To insert some value, there is an inbuilt method called as push. So how to call that or how to use this method? That is, you have to use the stack name, that is S1, using dot operator dot, then the method, that is push. And in the bracket, you will provide what you want to push into. Suppose I've used integer here, right? So you'll be using integer value. If here, suppose I would have used maybe a character or a string, then I should have given a string or a character value over here, right? Let's insert one more value. 4. Let's do one more just to check. Okay. 9. So this is how we'll be inserting the elements in the stack. Now suppose I want to print and then see that has it actually been inserted. So I can just print, that is system.out.println S1. Now let's execute this and check. So you can see here 2, 4 and 9 are the 3 elements inside the stack S1 which gets printed. Now suppose I have to delete something from this, remove. The operation is called as pop, and even the method name which is there to remove the elements from the stack is also pop. So how to use it? Again S1, that is your stack name, dot operator, pop. And in this we are not going to specify anything, just write pop, that's it. It will remove what? The first element which can be removed. So stack works in first in last out manner. So it will delete the last inserted element first, right? So S1 dot pop will delete what? See, you can see here first 2 was inserted, then 4 was inserted, then 9 was inserted. So you should pop out what? 9. Let's see. Does it pop out 9? So after that, I'll just put a print statement and check that is it actually deleting 9? So yeah, it is actually deleting 9. It's 2 and 4. Getting it? If suppose I do again S1 dot pop, then this time it should delete what? And again, I'll print this and we'll check. Okay. So you can see it deletes 4. So first it deletes 9, then 4. Now only left is 2. Okay. I will just comment out these lines. So this was the operation for inserting element into stack. So we inserted the element into stack. And here we did what? We created a stack by creating an object. Then we performed here the delete operation on stack, right? Now let's see and check about the other operations which we can perform. So what I'm going to do here is peek operation. Guys, as a name itself, the literal meaning itself of peek is that to look into. From top, suppose the stack is arranged, and from top, if you look into it, what will you see? The last inserted element will be on the top, and that will be visible to you. So that's the work of this peek method. That is, if you peek into a stack, look into the stack from above, what is that element which will be seen to you? So right now, if I execute this, guys, so right now the elements are 2 and 4 in this. So first 2 is inserted, then 4 is inserted. So if you look from the top into the stack, what will be the element you will be seeing? The top one, that is 4. So it should give 4 as an answer output to me if I use peek. So let's see. So S1 dot peek, if I call and we try to print this. Okay, we'll put it inside the system.out.println and let's see what it prints. Okay. So you can see 4 is the output, right? So that's the work of the peek operation. The literal meaning itself, that is looking into the stack over here. Now, next operation which we have to look into is to check is the stack empty or not. Many times you will encounter such situation where you have to check that is the stack empty, is the stack full. Stack full, there is no such concept. Okay, you can insert as many elements you want here, but if the stack is empty, that has to be checked, right? So how to check that? So there is a function called as empty, which has a return type as boolean, that is true or false. So we have to use a boolean data type here. Suppose status equals to, and then I'll be calling s1 dot empty, and then I will print this status variable. And let's see, right now is the stack empty? There are 2 and 4, two elements here. So it should say what? False, that the stack is not empty. So you can see false is the output. Right here you can see. If suppose I empty out, I perform so many pop operations here and I empty it out. So let's see here. So here I am going to call now s1 dot pop again. And then again I'll be calling s1 dot pop operation. Now I think 2, if I delete, that is 4 and 2 will be deleted. So it's empty now, right? Let's see what. Okay, it still says false because I'm printing it here itself. So I'll be printing again. Okay, let's do one thing. We will put the pop operation above itself, delete everything, and then try to call the status. I mean, check the status, is that empty or not. So you can see here, after deleting everything, so 3 pop operations and 3 push operations. That is, whatever we inserted, we deleted it. Push 2, push 4, push 9, and then again pop here, again pop here. That is, it's deleted. So status is true, that yeah, the stack is empty. So we saw 4 operations: push, pop, peek, and empty. Now, to implement sorting over here, there is an inbuilt method which you can use over it. But before that, let me talk about search first. Okay, to search also there is an inbuilt method called as search, which has a return type of integer. So whatever you are searching for, that will be found and the index value will be returned. Okay, so how to call that search method? Let's see that. As I said, it has a return type of int, so you should use int variable data type for a variable where you'll be storing the result of that search. So int maybe index found. Okay, and then you'll call s1 dot search, and then what you are searching for. So suppose I'm searching for 4 over here. Okay, I will comment out this pop operations so that I know it's not deleted. There is something inside so that we can get to know that we can search. Okay, so let these pop operations be commented out. So right now there is push operation only. So 2, 4, and 9, 3 elements are pushed into the stack. And now I'm going to search for the value 4. So it should search and tell me the index value. And then that index value I'm going to print here. That is your index found. Let's see what's the output. So you can see here, the last value, that is 2, prints is the output of the last print statement, that is index found. So it says 2. So you can see 2, 4, and 9. Here the 4 is at what index? 2. First is 1 index. So here it counts from 1, not from 0. At 1 index, there is 2. At 2 index, there is 4. At 3rd index, there is 9. So 4 is at 2nd index, and that's what the output is over here. So this is an inbuilt search method that is implemented over stack. We can directly make use of it in our codes in Java programming. Now, let's see how we can iterate over. So right now, to print any value of a stack, I'm just using system.out.println, and that particular stack name, that is variable name I'm giving, that is s1 over here. But what if I want to iterate each element one by one and then check or perform some operation or anything? In that case, we have to iterate over. So in other data structures. For example, in arrays, if you want to iterate over, we use a variable and a for loop and we iterate it. In stack, there is a different provision which we can do. That is, we can use a method called as iterator. How to use this method? Let's try to check that. So iterator is a class. You'll create an object of this class. Okay. And then on whichever stack you want to iterate over, using that stack, that is S1, I'll call the function iterator. Getting it? So now what happens is that this S1 becomes iterable because iterator is a method that is called over the stack S1. And how we'll iterate over it? That is how we'll scan over it using the object IT of class iterator, which we have defined here. So this is done. This part is clear. Now, so here, first of all, I'll write a comment that we are talking about how to iterate over a stack. Okay. Next is to iterate over here, we'll be using while loop. That is while there is next element in the stack. Like we'll start from first and we'll go till the end. Till where we'll go? Till where there is element in the stack. Once there is no more elements further, it should stop there. So to do that, we'll use while loop. While IT, that is the object of iterator class, has next. So has next is the inbuilt function again of the iterator class itself, which we are using it over the object of iterator class, that is it over here. It is the stack having more elements. So has next, is there a next element? Is there a next element? It will keep checking. So that is what has next does. And if there is next element, then we are just going to do what? Print it, right? And to print this, we will use it. Okay, we'll do one thing. We'll create an object over here. S2 maybe equals to new. Okay, no. IT dot next. And here we will be printing S2. It means what? This next function is used now to do what? It will just store that next value every time into S2 object, right? And then we are going to print this S2 object. So this is the complete concept of iterating over a stack. That is, you have to create first object of a iterator class, that is it over here, and using a method iterator will be making the stack iterable so that we can access it one by one. Then using while loop, we will traverse from beginning to the end of the stack, and has next is a method that helps there. That is, has next does what? It keeps checking that is there next element in the stack. And then next is a method which is used for fetching the next value from the stack, and it will store it in any object, that is S2 over here. You can give any name, any variable name for that object, and then we'll print that. Okay. Let's see the output for it. Okay, I'll just give print over here, not println, so that it comes in a single line and we can watch it properly. So you can see here 2, 4 and 9. It's not 249, it's the elements of the stack 2, 4 and 9. As I'm no here, see, you can see the how it was printed 2 comma 4 comma and 9, because I was printing the complete stack. But here I'm fetching single values from the stack and then I'm printing it. So it prints like this 2, 4 and then 9. Okay. The last statement here is the output of the last print statement. So this is how we iterate over a given stack. So we have discussed, I guess, all the elements here, that is push, pop, empty, peek, search. Okay, size and sort as the two methods which is left to be discussed. Let's talk about that. So we'll use here itself. To know the size of a given stack, like how many elements are there, how many space is occupied in the stack. To do that, we have an inbuilt function called as size. So s1 dot size. Okay, we can put it inside the system.out.println and we can see what is the output of it. So I'll put it inside this. So if I print this, the output should be 3. Okay. So you can see the last output, that is 3, is the output of the last print statement. That is the size of the stack. And size of the stack is, there are 3 elements, 2, 4, and 9. So it tells 3. Okay. Now let's see the last function or operation over the stack, that is your sort. So to implement sort also, we will use s1 dot sort inbuilt method. In this, inside you have to tell the comparator basically. So as of now, I'm not putting anything that like there is no comparator which I want to give. So it's null. So it will sort it out, and let's print the stack again. That is S1. I'm not iterating over, you can do that as well, but I'm just directly printing the value. So initially the value inserted was 2, 4, and 9. Guys, it is already in a sorted order. Let's like rearrange it in an unsorted order a little bit so that we can get an output as a sorted one. So you can see here the elements are 2, 9, and 5, right? 2, 9, and 5. And now it is 2, 5, and 9. Okay. You can see the index value here is -1 now, because the value which we are searching, that is 4, is no more there in the stack, right? That's why you can see in the output is -1, this value. This is the output of this particular statement, that is search this one. We're searching for 4, but 4 is no more in the stack. That's the reason it gives -1 as an output. But need not worry. Our point is here, sort, right? So we sorted it, and after sorting, the elements are properly arranged in the stack, that is 2, 5, and 9. Earlier it was 2, 9, and 5. So we saw all the different operations on the stack data structure, how to implement it in the Java programming. And those operations were push operation to insert the element, pop operation to delete the element, peek operation to just look into the stack from the above, what is the element. Or you can say it helps you get the last element of the stack. That's where peek will be used. Then empty is a method which will help you check, is the stack empty or full, or is there any element or there isn't any element. That is what the job of empty function or a method is. Then there is a search method. This is also an inbuilt method which you can use for searching a given value in a given stack. Then there is a sort inbuilt method which is used for arranging in ascending order the given elements of a stack.
Now let's talk about the advantages and disadvantages of stack. If you talk about advantages, it maintains data in a LIFO order, right? The data is maintained in a LIFO order. That means the last element that is there in the stack is readily available for us to use. So one of the readily available, right? So one of the applications of using stack is it can be used to evaluate expressions, right? Therein we require this feature, that is LIFO, right? And all the operations that are performed in stack, like push, pop, and then is empty, and then pick. All these operations take constant amount of time, which is very important while you're playing around with competitive programming or while you're doing competitive programming. At that time, these are very important that you program in the most efficient way. Programming in most efficient way is important and it is very crucial for your selection, right, in competitive programming. So all the since all the operations are performed in a constant amount of time, so these the stack is used oftenly when you are doing competitive programming. Now, what are the disadvantages? Since we are restricted, right? There's a restriction that we can only add and remove elements from top of the stack. So this is one restriction that is there. Thus, it is not very much flexible, right? It is not flexible. If you talk about the flexibility of how we are storing data in the stack, it's not very much flexible. So these are the disadvantages of using stack. Now let's try to understand queue linear data structure. What is queue? Queue is a linear data structure. That means all the elements in the queue are stored in linear fashion. Now, it follows a principle of FIFO. That means there's a restriction that whatever is the first item in is the first item that is to be out. Okay, so now let's try to make a queue. Let's suppose you are in a queue and you're waiting for a movie. You're waiting for a movie ticket to buy. Okay, so there is one person, then there is another person, right? So these are few persons here, right? And you're waiting in a queue. So now the first person who is in the queue will be the first person who will get his ticket, right? Makes sense, right? So he will be the guy who will get his movie ticket first, and he will be out of the queue. Then the next person who is in the queue is the next person who will get his tickets, right? And let's suppose a new person comes in, he's not going to go ahead from this person, rather he is going to go behind this person. Then the next person comes, he will go after this person, and in the same way. So this is nothing but a FIFO principle. Okay, the first person in is the first person out. Okay, now insertion will always take place from the rear end. Okay, and if you talk about deletion, it will always take place from the front end. Okay, so this is our front end and this is our rear. Cool. So for examples, buying tickets from the counter, or it can be a movie ticket, or it can be a bus station. You are in front of a bus station trying to get tickets for your bus, right? These are some examples. Now there are four major operations when you talk about queue. What are those major operations? Let me clear my screen. So NQ. So you are going to insert an element in the queue. This is what you mean by NQ. DQ, you are going to delete an element, okay, from the queue. Then peek first, that you're going to peek the first element that is in the queue. And peek last means that you're going to peek the last element that is in the queue. So you will have two pointers. One is front and another is rear. And with the help of these pointers, you're going to NQ, DQ, peek first, peek last. You're going to perform these operations. Now, one major advantage of these operations, these four operations, is that all of these operations are performed in a constant amount of time. That means the time complexity of performing these operations is O of 1. So that is why when you talk about competitive programming, Q is most commonly used data structure because of these things, right? Because of its time complexity, right? You're able to perform your operations in a constant amount of time. Now let's talk about applications of queue. So it is used in scheduling algorithms of the operating system, like first in, first out scheduling algorithm is there, round robin is there, and we have multi-level queue that is there. In all these algorithms, queue is used, okay, for storing the data or the processes. It's also used in maintaining playlists. Like when you have a playlist, let's suppose you have 10 songs in a queue, right? And after one song, the next song which is in the queue will be played, and it goes on for like this, right? So for maintaining a playlist, again, a queue is used. It's also used in interrupt handling. Let me take an example here. You know the process state diagram of operating system. So it is also used at that time. So when you have an interrupt and therein if your process is being executed at that time, that process is preempted out and it is stored in a queue. Now, the next time when this priority or this interrupt is handled, once it is done, then it starts picking up the process which was in the queue and starts executing that. In the meanwhile, if there are some other processes, that those processes will also be in the queue. So a queue is maintained, and once the interrupt is handled, they will start taking out that process that was being executed earlier and executes it and completes its execution and terminates the process. So it is also used in interrupt handling.
So let's start with linear queue. So before going to the concept of circular queue, we will be discussing about linear queue first. So coming to linear queue, it follows the FIFO order. FIFO order means first in, first out. So what's the meaning of first in, first out? It means the element which is inserted first in a queue will remove first. Now, coming to the next point, always remember that in a queue, insertion is done at the rear end, whereas deletion is done at the front end. Now, what is the example of a linear queue? So you can take the example of a lot of people standing in a line for a movie ticket. So the person who will be standing first in the line will get the ticket first. That means he will be getting the served first. So this is nothing but a FIFO order, an example of linear queue. Now, what's the limitation of linear queue? In linear queue, space is not utilized in an efficient way. I will give you the explanation here through example. Now, here you can see that this is the array implementation of queue. So what is the size of this array? The size is 5, right? So now let's start with the queue data structure. So here we are having front and rear, which is assigned as -1 initially. So whenever you are inserting any element, let's suppose if I am inserting here 7 in this, so my front and rear will set to 0. And these are the indexing positions of my array, right? So here you can see that I've inserted the elements, so my front and rear are set to 0. Now what will happen here? We are having NQ operation. So NQ operation is used to add an element in the queue. So let's suppose that if I'm inserting here 8, so 8 will be inserted here and there will be the increment in rear. So whenever you are performing NQ operation, there will be increment of 1 at rear end. So here my R is equal to 1. Similarly, if you are adding suppose 13 or inserting 13, then my R is equal to 2. Let's suppose if I am inserting 15, then my R is equal to 3. So you can see that there is an increment, that is R plus plus, right? And then after that, again if I am inserting, let's suppose 21, so my R is equal to 4. So front and rear contains the integer values. So another operation that I'm having is dequeue operation. So whenever I'm performing dequeue operation, it will remove the element from the queue. So here you can see that if I'm removing 7 from the index 0, then here my f is equal to 1. So let me remove this. Now after that, if I'm again removing 8 from here, then my f value will again increment and my new front value will be 2. Similarly, if I'm again removing 13 from here, then again my front value will be increment and it will be 3. And if I'm removing 15, then my front value will be 4. So you can see that whenever I'm performing dequeue operation, there is an increment in front, right? So now what's the problem with linear queue? Here you can see that I'm having an empty element at index 0, at 1, 2 and 3, and you can see that this array will look like this. I'm here only having 21, right? And my front value is here 4 and my rear value is here 4. And here you can see that at these index positions, my elements are empty. Now, what's the problem with linear queue? In linear queue, as we know that whenever we are performing NQ operation, there is increment at the rear end. Similarly, whenever we are performing DQ operation, there is increment in the front end. So the problem is that if the rear reaches to the end position of the queue, then we can't insert further more elements. Why? Because you can see that the size of array is 5, right? So we can't insert because the size is 5 only, right? So here you can see that these spaces are not utilized in an efficient way. So in this way, the concept of circular queue was introduced to solve this problem. So this was the basic idea about linear queue. Now let's see the concept of circular queue. So like normal queue, circular queue also follows the first in first out principle. That means the element which are inserted first will be removed first. But the only major difference here is that the last position is linked with the first position and that result in the formation of circle. So why we are doing this? Because in linear queue, the space wasn't utilized in an efficient way. So while linking the last position with the first position, we can form a circle and we can utilize that space. So this is a simple concept of circular queue. We can utilize a space in an efficient way. Now let's see the representation of circular queue. Here you can see that this is my linear queue, and here if you see the size of this array, or you can say length of an array, is 5 from 0 to 4. Now here you can see that my front is at index position 1 and my rear is at index position 4. So what was the concept in linear queue? Whenever you want to insert any element, then we were using the NQ operation for insertion, right? So whenever we are inserting any element, there was an increment in the rear. So I can write rear plus plus. Similarly, we were also having the DQ operation. So in DQ operation, it is used to delete the element. So whenever we were deleting any element, our front increases. So I can write front plus plus. So this was the logic for linear queue. So before moving to the circular queue, we know that in our normal queue, or you can say in linear queue, if I am coming at this last position, that is rear is equal to 4, and after this if I am performing NQ operation, then I can't do, because the size is fixed. So that's why the concept of circular queue was introduced. Now if in normal queue, if I am writing NQ operation, I can't do, but if I link this to the index 0 and if I form a circle, and then if I am performing NQ operation, then I can insert the element. So let's see how we can form a circular queue. So here we are having 5 elements, right? If I'm writing here 0, 0, 1, 2, 3, 4, you can see that initially at 0 index position I don't have any element, but at 1 I'm having 8, 5, 2, 7, and my rear is at 4. So I can write here rear is equal to 4 and my front is equal to 1, right? So here this is my circle, right? And now if I am performing here NQ operation, let's suppose here if I am inserting 17, right? So 17 will be inserted here. But what will be the logic? The normal logic for the linear queue was rear plus plus. So what will be the logic for my circular queue? So as we know that when we are at end position, we want the NQ operation and we want the element to be inserted at the 0 index position. So we have to develop a logic. And for that, I will write a logic that is rear is equal to rear plus 1 modulus size. And now here you can see that I want to insert the element 17, so I will be using NQ operation, right? So as we know that when I'm performing my NQ operation in case of circular queue here, so I want this rear to be shift at rear is equal to 0. So for that I have written the logic rear is equal to rear plus 1 modulus of size. Now here you can see that my rear is equal to 4 here. So if I'm writing here 4 plus 1 and modulus, so what do you mean by size here? Size means the size of an array. So size of an array is 5. So if I'm adding 4 plus 1, 5, and then 5 modulus 5. So as we know that modulus operator will give us remainder. So 5 modulus 5 will give us 0. So my rear is equal to 0. So here you can see that from rear is equal to 4, we come to rear is equal to 0. And this is the logic for the circular queue. Now let's take another example. Let's suppose this is my queue, right? And here if I'm having 7, 8, 9, and this is my rear here, and if I am making my queue, let me write the index position 0, 1, 2, 3, 4. So I'll write here 0, 1, 2, 3, 4, and my front will be here, right? So as we know that 0 and 1 here are empty, and at 2 I will write here 7, 8, 9. So now at 4 my rear is there, and at 2 my front is here. Now let's see how this logic work for each and every element of this circular queue. Now you can see this is my circular queue and my rear is at position 4. Now if I want to write NQ operation, and if I'm inserting let's say 11, then as we know that whenever we are doing NQ, then my rear position will change, right? In case of circular queue. So as we know that in circular queue, whenever we are doing NQ operation, that means element will be inserted and there will be a change in rear position, right? It will shift from here to the next position. So for that, if I'm writing here rear, so my rear is here at 4. 4 plus 1 was the size of array. Array size is 5. So 5 modulus 5. I will get my rear position as 0. So as 0, I am having 11. Now, once again, if I am performing NQ operation, that means if I am inserting here, let's suppose 15. So now what will happen? Here you can see that rear is equal to rear plus 1 modulus of size. Now the rear is at 0. So 0 plus 1 modulus of size is 5. So 1 modulus 5, you will get 1. So you can see that now the new position of rear is 1, and at this position my element will be 15. So in this way rear will go from 1 to 2, 2 to 3, 3 to 4, 4 to 0, 0 to 1, 1 to 2, and it will go on. So this is the simple logic of rear is equal to rear plus 1 modulus size. So this is a circular increment formula from where my rear will shift from, let's suppose that if my rear is at 0, so it will shift from 0 to 1, 1 to 2, 2 to 3, 3 to 4. So this was the logic for rear end. Now coming to the logic of front end. So front is equal to front plus 1 modulus size. Again it will be having the same logic, but the difference is that when we are performing DQ operation, at that time there will be a change in the front value. So here if you see this is a circle, and if I am giving the position 0, 1, 2, 3, and let's suppose that my rear is equal to 1, I'm writing here, and it's having the value at 87, and after that I'm having 98, and let's suppose here I'm having 5, and here let's suppose my f is equal to 1 also here, right? This is the initial condition that I'm writing here. Now what will happen if I'm performing DQ operation? That means if I want to remove 87 from here, then you will see that my front is equal to front plus 1. So front is 1 here, 1 plus 1, and then modulus of size. Size is here, what's the size of this array? I'm having size as 4, right? So here if I'm writing 2 modulus 4, so modulus will give me as a remainder, right? So if I write this, then you can see that it will give me remainder as 2. So my new front will be is equal to 2, and this element will be deleted, right? So in this way it will work. Similarly, if I want to DQ 98, right? So for that my front is equal to 2. So 2 plus 1 will give me 3, and 3 modulus 4 will give me the remainder as 3. So now my new front will be equal to 3, and this 98 will be removed. So in this way the circular queue works, and the logic of circular queue is rear is equal to rear plus 1 modulus of size, that is for the NQ operation. And for DQ, we are having front is equal to front plus 1 modulus of size.
Now let's talk about advantages and disadvantages of queue. First, we are talking about advantages. So it follows a principle of FIFO, or the elements are stored in a FIFO manner. That means, let's suppose this is a queue, and in this queue you have elements. So the deletion will take place from the front, right? And the insertion will take place from the rear side. So this is known as DQ, the deletion, and insertion is known as NQ operation. And both these operations are performed in a constant amount of time. So that is one of the advantages, right? And the insertion from beginning and deletion from end takes a constant amount of time. Plus, if we want to do peak first, peak last, all these operations are performed in a constant amount of time. And this is most widely used data structure when we talk about CP, that is competitive programming. When we talk about competitive programming, this data structure is most commonly used because of these features, that all the operations that are performed like insertion, deletion, peak first, peak last, NQ, DQ, all these operations are performed in a constant amount of time. Now let's talk about disadvantages. Since we are only able to delete or insert from the front and the rear, that means deletion from front and insertion from the rear. So the restriction of insertion or any manipulation, right? We have a restriction over these, right? What these operations, insertion and deletion. So this restriction is always there, and so this data structure, that is the queue, is not much flexible, right? We are fixed. We can delete and insert element in a fixed pattern or in the FIFO manner. Thus, it's not much flexible.
Now let's see some standard operations in queue. As I told you about NQ and DQ operations, in NQ operation it is used to add element from the rear end. And for the DQ, if you want to remove the element, then you have to remove the element from the front end. So this was all about NQ and DQ. And also the time complexity of NQ as well as DQ is big O of 1. Moving next, we are having front and rear. So front gives us the first element in the queue, whereas the rear gives the last element from the queue. And at last we are having is full operation as is empty operation. So is full operation will check whether the queue is full or not. And coming to the is empty, it will check whether the queue is empty or not. So these are the basic standard queue operations. We will see each standard queue operations while practical implementation. Now let's see the algorithm of circular queue. So now before coming to the algorithm, I just want to give you the idea about that if I'm writing here rear plus 1 modulus of array size is equal to rear, and if I'm writing here front plus 1 modulus array of size is equal to front. So these formulas are used for the circular increment. So these are the key point. Now in this NQ operation you will see different cases. So now the first case will be, if I'm writing here case 1, let's suppose that if my queue is empty, if I'm having my queue and this is empty, so at that time my front is equal to -1 and rear is equal to -1 initially, right? So you can see that when my queue will be empty here, I'll give the condition if front is equal to -1 and rear is equal to -1, then we will set front as 0 and rear as 0. So this is my first condition for empty queue. Now coming to the second condition, what if my queue is full? Let me insert the element here. So let's suppose my front is here and front is equal to 0. It's 1, 2, 3, 4, and here if I'm writing here, let's suppose 7, 8, 9, 10 and then 12, and this is my rear, that is rear is equal to 4. Now you can see that in this case my queue is full, right? So when my queue is full, at that time insertion is not possible. So the queue will be full, or you can say that it's a overflow condition. So let's see the condition. So this is the condition if I'm writing here rear plus 1 modulus of, I'm writing here size, that is array size, is equal to front. Now you can see that rear is 4. So if I'm writing here 4 plus 1, then modulus, what's the size of this queue? The array size is 5, right? 0 to 4, the size is 5 and is equal to front. So 5 modulus 5, I will get 0, right? Because modulus will give me the remainder operator and my front is 0. So in this case, my queue will be overflow, right? So this is a condition when the queue is full. Now coming to the third case, that is case 3. Let's suppose that this is a normal scenario in which my front is here, that is 1. Let me give the indexing positions. I am writing here 8, 7, 5, 3. So my rear is equal to 3 and my front is 1. And here you can see that queue is empty at the beginning, right? So in this case, my formula will be rear is equal to rear plus 1 modulus of size of an array. So my rear is 3. So you can see that 3 plus 1, and what's the size of this array is 4. So 4 modulus 4, I will get 0. Right? So this is the case for the NQ operation, right? Because in NQ we want to insert the element. So after this index position, I want to insert the element at position 0. So I will perform this logic. So if I'm writing here NQ and if I'm inserting 25, so 25 will be inserted here at index 0. So this is the logic to insert the element on the empty index position. So these are the three cases that I've explained you for the NQ operation. Now coming to the DQ operation, we know that when we are having empty queue, we can't perform any DQ operation. Why? Because DQ is used to remove the element, but we don't have any element to remove in the queue, right? So let's say the first condition, when my rear is equal to -1 and my front is equal to -1. right? So if this is the condition, that is the initial condition, then my queue is empty and I can't perform any dequeue operation. So this is my first case, case 1 I'm writing here. And here I will write if front is equal to -1 and rear is equal to -1, then it's an empty queue. Now, coming to the next case will be like this. Let's suppose I'm having only one element here. I'm writing 8 here. Let me write index position. So here my front is equal to 5 and my rear will be also is equal to 5 when I'm having only one element in my queue at the last position, right? So in this condition, what will happen? My front and rear will be set to -1. So whenever I'm having only one element at the end of queue, then it will set to front is equal to -1 and rear is equal to -1. So this is the second case that I've given here. Now coming to the case third, let's suppose this is my queue, and inside this queue, if I'm writing here 2 8 3, so this is my front is equal to my 1. Let me write the index position, so it will be 0 1 2 3, and here my rear is equal to 3, right? And my size of an array will be 4. So here you can see that I'm having elements in my queue, and if I want to perform the dequeue operation, then I have to remove the element, right? So in this case, I will write here front is equal to front plus 1 modulus of size. What is the size of array? It's 4. What's my front value? Front value is 1. So 1 plus 1 modulus 4. So 2 modulus 4 I will be getting as 2, right? So if I'm writing here dequeue operation, that means I want to remove the value, right, from the front end. Dequeue operation means you want to remove the value from the front end. So my front is equal to 1, and if I'm performing my dequeue operation, my front will be equal to 2, and the value that was assigned at the index position 1 will be removed. Similarly, if once again I am writing here dequeue, that means my front will shift here and my front will be equal to 3, and again 8 will be removed. So this is the logic. So I have showed you all the three cases. So after enqueue and dequeue operation, I will create a count variable. So for creating a count variable, I will create one more method and I will give the name as void display. And after that, I will write here count. So let's understand why do we use count. So count is used to get the number of elements contained in the queue. Let's suppose the example here. This is my queue. Let me give the index position 0 1 2 3. Let's suppose this is my front is equal to 1, and here I'm writing rear is equal to 2. So let me write the elements 7 and 8. Now I write the logic here for the count. So count is equal to rear plus size minus front, and then modulus of size plus 1. So now here you see the rear value is 2, and what's the size of this array? Size is equal to 4. And what's the front? Front is equal to 1. And again, what's the size of this array? Is 4. So here 2 plus 4 will be 6. 6 minus 1 modulus 4 plus 1. And here 6 minus 1 will be 5. 5 modulus 4 plus 1. Now 5 modulus 4 I will be getting as the value 1, and 1 plus 1 will give me as 2. So here you can see that I am getting as count as 2, right? So as I told you the formal definition of count, that count is used to get the number of elements contained in the queue, and I am having 2 elements which are present in my queue. Now, so why did I create my count variable? I will explain you. Let me remove this. We know that whenever we are performing enqueue operation, that means we are inserting the value. We want that the count has to be increased by 1, right? So that we can count the number of elements that are contained in the queue. Now, let's see how we can use this. So this was my formula. Count is equal to rear plus size minus front, and then modulus of size, and then plus 1. After this, what I will do, I will create a loop. So inside this loop, let's suppose I'm writing here int I is equal to 0. I'm initializing it to 0, and I will write I less than count, and then I will do the increment here. Inside this, what I will do, I will write print function, and I will write the logic here array, and I will write here front plus I modulus of size. So this is my main logic. Now let me give you the clarity over this. So initially I will create my array, and this is my index position of array. So if you see here, if I'm writing here 3, 4, 5, let's suppose this is my front as 1, 0, 1, 2, 3, and this is rear at third position. So you can see that here what I am printing here, front, my front is equal to 1, so 1 plus, and I is 0 initially. And then what is the size of this array? Size of this array is 4. So 1 modulus 4, I'll be getting 1. So what I will do here, now I will write printf, and inside this printf I am getting as array of 1, right? And 1 is the index position. So whatever the data elements I am having at one position, it will print it. Let's suppose in this case it will be printed at 3. Similarly, this is a loop, so I value will be incremented. So it will start from 0, 1, 2, and it will go up to I less than count. So let's suppose that my count value is 5. So it will take the value 0, 1, 2, 3, 4. After getting the index value 1, once again I will increment, and I value will be 1. My front was 1, I was 1, so 1 plus 1 I will be getting 2. So 2 modulus 4, what will I get as remainder? 2, because the modulus will give me the remainder, right? So this time I will getting array of 2. So whatever the data elements I am having at the index position 2, it will be printed, right? So in this way I will be getting the array 3. So you can see that I'm using this logic to print the data elements at the particular index position. So this was the basic idea about the enqueue, dequeue, and then about the count. Now let's see the practical example, hands-on example, to get more clarity over this. Now let's see the code of circular queue. So I will be using here C programming. So let's start with the preprocessed command. So I will write here hashtag include. Then I will write standard input output dot h. Now after this, what I will do, I'll create an array. So I'll write here integer array, and I will write here array size. Now after writing this, I will define my array size. Let's say hashtag define. So I will define the array size as 7. So after this, we know that initially our front is equal to -1 as well as the rear is equal to -1, right? So what I will do, I will create an integer, and I will write here front is equal to -1 and integer rear is equal to -1. Now I will create one more variable of count. So I will write here int count. So as we know that in queue we are having enqueue and dequeue operation. So first I will create a enqueue operation. So I will write here a function void enqueue, and enqueue operation is used to insert an element. So I will write here integer a, and I've showed you 3 cases. So the first case was when your queue is empty. So when your queue is empty, so at that time your front is equal to -1 as well as the rear will be equal to -1. So I will write here if front is equal to -1 and rear is equal to -1. So I will assign front as well as rear is equal to 0. We know that when our queue is empty, we will initialize front is equal to -1 and rear is equal to -1. But whenever we are inserting the first element, our front and rear has set to 0. So I'll write here front is equal to 0 and rear is equal to 0. So this is my first condition. Now coming to the second case, we have seen when all the elements are inserted in the queue, then we can't perform enqueue operation because the queue will be overflow. So let me write the condition. I will write here else if, and inside that I will write rear plus 1 modulus of array of size is equal to front. So these cases we have already discussed. So now this is the condition when we can't do any insertion because my queue is full. So in this case I will write here printf, and inside printf I will write my queue is overflow, or you can say that full also. So I'll write my queue is full or overflow. Now after this I am having one more condition. So I will write once again else, and the last condition was to insert the element in a queue. So for that I am having a formula. So I will write here rear is equal to rear plus 1 and then modulus of array size. So here modulus will give us the remainder. So now these were the three conditions. Now after this I will write my array, and inside the indexing position of array I will write here rear, and I will assign a here. So what will happen here, let's suppose if I am inserting here a 125. So 125 is the data element, right? So let's suppose that if my rear is 0, so at the 0 position my value will be 125, right? So the data element will be 125 at the 0 position. So let's suppose that my a value is equal to 10 and I got my rear value as 1 here. So array of 1 is equal to 10. So at rear is equal to 1, my data element will be 10. So this is the idea. Now, so this was all about NQ operation. Now coming to the DQ operation, once again I will write a function of DQ. So I will write here void DQ. So inside DQ operation, I don't have to insert any element. Why? Because in DQ operation we are removing the element. So inside DQ operation, what will be my first case? So my first case will be if front is equal to -1 and rear is equal to -1, then my queue will be empty, right? So I will write here if front is equal to -1 and rear is equal to -1, then I will write inside this condition my queue will be empty, right? So I will write here printf and I will write it's an empty queue. So this is my first condition. So now coming to the second case, my second case was front is equal to rear. So when my front is equal to rear, so let's take an example. Suppose that if I am having a queue and all the elements are inserted in the queue. Now if I am deleting an element one by one, so I will be having only one element in my queue. So in that condition, my front is equal to rear. So in front is equal to rear, I am having only one element in my queue. So at that time, what I will do, I will set front is equal to rear is equal to -1. So let me write the conditions. So I will write here else if, and I will write here front is equal to rear. Then I will set front is equal to rear is equal to -1. So this is my second case. Now coming to the last case. So the last case was removing each element. So what's the formula for that? I've already told you. So I'll write here else, and here I will write front is equal to front plus 1. Let me put it inside the round brackets. So front plus 1, and after that I will write modulus array of size. So this is my last condition. So you can see that I have created NQ operation as well as DQ operation. Now after this you can see that I have already declared here my count variable, right? Now what I will do, I will create one more function. I will write here, let's suppose I will write the here void, and I will give the function name as display, and inside that I will write the formula of count that I told you, that count is equal to, I will write here rear plus array size minus front, and I will do the modulus of this. Let me close this, and after that I will do the addition of +1, right? So this is my count formula. After that I will create a loop. So I will write here for, so inside this I will create a loop, and I will write, let's suppose the variable x is equal to 0, and then I will write here x less than count, and I will write here x plus plus, and then I will write printf. I'll write here %d. So here I have written %d to assign the integer value. So for float value you can write %float. Now after this, what I will do, I will write my array, and inside this array I will do the indexing. So I will write here front plus I, and then I will write here modulus, and then I will write array size, and let me put semicolon, and after that I will write printf, and inside that I will write backslash, and I will write n to jump into the next line, and then this is my void display function. So you can see that I have created three functions, NQ, DQ, and void display. So in void display I have created a count variable, and we are performing the operations. Now next, as we know that the execution of the program will start from the main function, so I will create here main function int main, and inside this let's perform some operation. As I was telling you that NQ means that you are inserting the element from the rear end, right? So if I'm writing here NQ, Let me insert the element as, let's suppose I'm inserting with 3. Let me copy and paste. Let's insert some more elements. Let me give here the value as 15. Here I will give the value as 28. And let me insert one more value. So I'll write here, let's suppose 45. Now you can see that I'm inserting the value, right? So NQ3, so this value will be inserted in my NQ function, right? And it will check the condition, and according to that it will perform. Now after this I will write printf, and I will write here elements inserted in the queue are. Now after writing printf function, I will write here display. So you can see that I'm calling my display. So why I'm calling my display? Because in display it will give me the data elements present at the particular index. This is my logic that I'm implemented here. I've already explained this you in the algorithm part. So this was all about the NQ operation. Now if I want to remove the elements from the queue, so which operation should I perform? I have to write DQ, right? So I'll write here DQ, and for DQ is just a removal for the element, so I don't have to put any parameter here. I will write here DQ. Now after DQ operation I want to check my queue, so I will write here printf, and I will write the final queue after DQ operation is, and after writing this I will write here display. So let me put here semicolon. So this is my program. Now let me execute this. So before executing, let me write here printf. So after executing, you can see that why I'm getting here error, because I have created the variable here x, so I have to write here x. So yeah, let me execute this now. So on executing, you can see that I am getting the elements inserted in the queue are 3, 15, 28, 45. So let me see here. So you can see that I have in queue here. That means I have inserted the element 3, 15, 28, 45. So you can see that elements inserted in the queue are 3, 15, 28 and 45. And after that, if I am performing DQ operation, so as we know that this will follow the first in first out. So 3 and 15 were inserted first, so they have to remove out the first. So you can see that the final queue after DQ operation is 28, 45, right? So 28 and 45 we are getting. So this is the concept of basic circular queue. Now let's take a quick recap of this course. We have started this course by learning the concept of linear queue, and we have also seen the limitation of linear queue. Moving ahead, we have seen the concept of circular queue, what is circular queue, what are the different operations involved in circular queue such as NQ and DQ operation. Then we have seen the algorithm as well as the practical implementation of circular queue. Thank you.
Let's talk about the implementation of queue data structure in Java programming. Before going to the IDE and start writing the code, let me tell you the problem statement. That is what exactly we are going to implement under queue data structure. So the program which we'll be writing will try to create a queue there, okay, and implement it using classes and inbuilt methods. And once the queue is created, we'll be implementing certain functions which will perform some operations on the queue. That is your NQ, DQ, is empty, size, and display. So NQ and DQ operations are basically inserting the element into the stack, deleting the element from the stack. NQ is inserting, DQ is deleting the elements. Is empty is a method to check whether the given queue is empty or not. Size will tell you the size of the given queue, and then display will display the elements of the queue. That is, it will help you access the elements of the queue and display it as an output. Before going to the implementation, few things which are important with respect to queue data structure under Java, let's try to see that. And that is, there is an inbuilt interface with the name of queue. So queue is already an interface defined in the Java package. Okay, and as it is an interface, it has to be implemented or extended by various other interfaces and classes. Okay, some of the interfaces and classes are linked list, priority queue, and so on. Although this queue belongs to the collection framework of Java, but it is an interface which has to be implemented to implement various other methods. Now, the functions which we are going to write, or the methods which we'll be writing in Java, is enqueue and dequeue. Enqueue is inserting the elements into the queue. So as we already know that, queue data structure follows first in, first out logic. That is, whatever is inserted first will be deleted also first. Suppose this is your queue. So this will be called as your front end of the queue, right? And this is called as your rear end of the queue. Fine. If I insert any element, it will be inserted from the rear to the front. Then I'll insert another element, suppose 4, which will be inserted here, then 9, and so on. The point here to understand is before implementing enqueue or dequeue operation, there is a condition check which has to be done. And what is that condition check? Initially, guys, for any queue, if it is empty, front and rear, both of these will be pointing to the same place. Yes or not? Because there is no element in this. So this is only the front and this is only the rear. Because right now nothing is there in the queue. Okay, this is one thing to be kept in mind. So when we insert anything and front and rear both are pointing at the same point, it means there are no elements. We'll insert the first element to the queue. Now if I insert the first element, that is 2 over here, front will be still pointing at the same place, but rear will shift to this location. It won't be pointing to this anymore. It will point to this location now. Getting it? Now suppose I insert another element 4 here. Now front will remain same there, but the rear will be pointing now to this location. Getting it? So this is how the front and rear pointer moves. Now, when will we find that the queue is fully occupied? When it reaches to the last. Suppose the size of the queue, like we'll be using one-dimensional array to implement this queue. Okay, and one-dimensional array has a fixed size. So suppose the size of that one-dimensional array which we are using to implement queue data structure is 5. Let's assume. So when the rear points at the fifth location, when the rear points at the maximum location, that is fifth location, it means the queue is occupied, is full, right? So when the queue is full, you cannot insert any more element into it. So what you have to check here, that if your rear is same as your capacity of the queue, or you can say size of the queue, then you cannot insert anything into it because the queue is already full, right? Now, this is a condition you have to keep a check for inserting elements into the queue. There is a condition which you have to keep a check for deleting elements from the queue. Will you be able to delete any element from the queue if the queue is empty? There is not at all any element into it? No, you will not be able to delete, right? If there is something into it, then only you can delete it. There is nothing inside it, then definitely you cannot delete anything. So that is a condition check which you should do. And how can that condition be defined in terms of front and rear, these two variables? If front and rear both points to the same location, it means there is nothing in the queue. Queue is empty. Or you can say when rear points to the first location, that is 0th location, 0th index, it means there is no elements in the queue. You cannot delete anything. So for deleting or dequeue, we have to keep a check for this. That is, if rear is equal to 0, there is no element, we cannot delete. For enqueue, if the rear is pointing to the size of the queue, it means that the queue is full. You cannot insert any more elements into it. So these are the two logics which you have to keep in mind, and always keep in mind in Java, queue is a interface which implements various other interfaces, as well as queue is implemented or extended by many other classes and interfaces further, but it belongs to the collection framework of Java itself. Now let's go to the IDE Eclipse and try to write down the code for the problem statement which I right now explain you. That is, we'll create a queue and implement all these 5 given methods. So you can see here already there is a class created with the name of queue solution, and there is a main method in this, that is public static void main, which is a required method inside Java programming. We'll be writing our main code inside the main method itself, but before that we have to implement queue, and for that I'll do it in a different class. Okay, so here I'm going to create a class with the name of queue using arrays. Okay. In this class, I will be having a variable for front and rear, two variables we need to track down the queue. So front of queue, okay, and then rear of queue. And then also we'll have the capacity of queue, or you can have like this, capacity of queue. Okay. Now we'll try to initialize these variables by having a constructor defined for this class. And to define the constructor, we have to just use the class name in Java. This is how we define a constructor. So queue using arrays. And in this, I'm going to pass the size of the queue. Okay. So I'll just write size. That's fine, I guess. I'm using longer variable names to make it more explanatory, guys. You can use shorter variable names also. Queue using array is a constructor here for the queue using array class itself. And in this, I'm going to initialize all these variables which are there for the class queue using array. So capacity of queue will be initialized with the size which is passed to this constructor. Okay guys, we are going to implement this queue using a one-dimensional array. So I'm going to define that one-dimensional array as well here. Let that array be maybe q1, which is equal to new. Okay, we'll do one thing. We'll let it be as of now like this and initialize it inside the constructor itself. Static int q1, and we'll be initializing it over here. That is q1 is equal to new int, and here it will be capacity of queue. Okay, so every time the size which is provided while making an object of this class, this constructor will initialize the array size to be of whatever size is passed here. Okay, so that's it, done with the constructor. Now let's implement the methods. So first I'll write the method enqueue and then dequeue, and then to display we'll be writing a method. Okay, so to enqueue we'll write a method void enqueue. Let it be this name itself. Okay, and in this I'm going to pass the value which you're going to insert. So int value. Okay, now I've told you that to insert an element into the queue we have to have a condition check. And what is that condition check? That is, if the queue is full, then you can no longer insert elements into it. Okay, so you have to keep a condition check that if rear of queue is equal to capacity of queue, then it says that queue is already full. You cannot insert element, right? So this is your if condition. Now coming to the else condition. Now if suppose there no capacity of queue and rear of queue is not same, then in that case we should go to else condition, and that is your, and if it is not same, like there is place to insert, then we'll be inserting it, right? And to insert the element, what we have to do is in the array q1. Okay, in this also guys, we have to insert at q of rear, q1 of rear of q. And what we should insert here? The value which we want to, which we have passed to this function, that is value. Okay, so this will be inserted here. Once it will be inserted here, your rear should be incremented one place, right? That's what we saw when I explained you the logic. So rear of q should be incremented each time. Okay, so this is your condition for NQ. I hope it is clear. Now let's write a function for DQ of it, that is deletion of it. To void function name, that is DQ, and we don't have to return anything from this function, so let it be a void return type. And in DQ, what should be the condition check? So in this, the condition check is that you have to see that there should be some element in the queue to delete it. If the queue is empty, then definitely you cannot delete it. So you have to check here if the rear of q is equal to 0, then in that case, it says that q is empty. There is nothing to delete, right? Else, what should be the delete? After delete, what should be the logic? Okay, to understand that, let's go back to the slide. So I'll quickly tell you here the logic of the DQ function. Okay, so one condition check is already there. That is when there is no elements in the queue, that is rear is pointing to 0th location, then you cannot delete anything from the queue. Apart from that, now if there is elements in the queue, okay, suppose this is your queue and these are the elements 2, 4, 6, 9. Suppose these are 4 elements. Now you have to delete, and definitely you can delete only from the front, first in, first out, right? That's the logic followed by queue. So you can delete only 2. So when 2 will be deleted, how will you represent this programmatically that 2 is deleted? What we'll do is we will overwrite in the same queue from the elements that is after the first element which is deleted. So 2 is deleted. So what we'll do, we'll overwrite 2 with 4. That is 4 will be written over here. We'll overwrite 4 with 6. 6 will be moved over here. 9 will be moved over here. That's all. The same queue will be now represented in this way. So as we have overwritten 2 with 4 and then 4 with 6 and 6 with 9, 2 is no longer there in the queue. It means 2 is deleted. So this is the logic which is followed for DQ operation. Now let's go back to the IDE and try to implement it. So coming back to the implementation here of DQ function again. So here we have done a condition check, that is if the rear of q is equal to 0, that is there is no element in the queue, then it should not delete anything and it will give a message that q is already empty. There is nothing to delete. Now let's see if there are elements. I've already explained you the logic behind it. Let's try to code it down in Java. So to write a code for it, you have to run for loop. So for int of I, starting from 0 till I less than, as it is a one-dimensional array, right? So we can use a for loop to run over it. Rear of q minus 1, because when we'll overwrite, the last element will become the second last element. So we should not go till the last element. We should go one less than the last element. That is your rear of q minus 1. And then rear of q plus plus. Okay. In this, what we have to do is that in q1, ith element, so it should be small I, ith element should be now, okay, this will be q1, okay, ith element will be now equal to q1 I plus 1th element, right? That's what we are copying, the second to the first, third to the second, fourth element to the third element, and the last to the second last. So this is what the logic will be there. right? After this, at the last, when we'll come out of this for loop, then we should do what? Rear of Q, it's capital Q, right? It should be minus of 1, or you can say minus minus, because that's how your number of elements will reduce. Earlier, the number of elements was suppose 10, the minus 1 meaning 9. So this is your DQ function. I hope the code till now is clear to you. Now coming to the main function, we will create the object of the class and try to call these functions of NQ and DQ. But before that, it will be better if you could write the display function also along with it. So let's write that as well. So void display. Okay. There is nothing to take as an input. So in the display, what will be the logic? So just the logic should be that if the queue is empty, then there should be nothing to display. Else, you can iterate over and display the result. So I'll copy paste the same code from here. So Control C and we'll paste it over here because this logic is going to be same, right? You can say here that, queue is empty, nothing to display. Okay. In the else condition, what should be there? Now, if there are elements, then in that case, you have to just iterate over it. That is for loop will be used as it is an array. So we can use for loop equals to 0 and it will go till where I should be less than your rear of q, right? And then it should go I plus plus. Okay, one mistake. Sorry, here it should be I plus plus. Yeah. So here in the for loop again, now system.out.println, and what we have to display here is q1 of I. So it will display all the elements. So for loop is closed here, else loop is closed here, and the function is closed here. Okay. So this is your display function. Now let's create the object of the class. The class name is q using array. So q using array. Okay. This is the class name, just verifying it one. Okay. So q using array and then maybe QUE, or I can say Q2, guys. Just a small name would be better. New q using array, and then I have to pass the we have used a constructor, right? So we have to pass here the size of the queue. So suppose the size of the queue is 5. Okay. Now using this q2, we can call all the functions like nq. Suppose I have to insert 2 here. Then I can again call this nq function to insert 4 over here. Then again I can call, the same function nq to insert maybe 8 over here. And then we can call the display function to just check that is it actually displaying everything or not. So let's save it and run this file. So yeah, okay, so it's println, so it's giving like this. Once again, I'll remove println from here so that you can, and we can put a, this is just a little bit of formatting, guys. You can do it in your code. So you can see here we have inserted 2, 4 and 8. So 2, 4 and 8 is inserted, and the display function, that's how we are seeing the output, that is 2, 4 and 8, right? So it's working fine. Now suppose there wasn't any element and I would have called display function. Then what should it say? It should say queue is empty, nothing to display, right? And so the code is working fine. Sorry, it should be q2. Yeah. Now let's see the DQ is working fine. So q2 dot DQ will be called. It means I would have deleted the first element which was inserted, that is 2. So it should display 4 and 8. Now let's call display over it. So if I call display over here and then try to run it, so we get 2, 4, 8 and then 4, 8 again. right? Okay, we'll separate this over here once again. I can just write here itself, or you can write it anywhere, guys. Just I'm separating it. So you can see here. So display 4 and 8. So 2 is deleted, is removed. Okay, if there is nothing to delete, then it should say the message that there is nothing to delete, right? If I call just this, I have commented out all the enqueue operations, so nothing is inserted over here. So if I run this, let's see, it says queue is empty, there is nothing to delete. Getting it? It means the code is working fine. So now, let me summarize it for you guys. So what I did is I used a class, any name you can give over here. So where front and rear two variables are used to keep track of the elements. Then capacity of queue is being defined, and this is the code for implementing queue using a one-dimensional array. So there's a static array which I've used, one-dimensional. Static because I'm going to refer it from a static field, that is main method, and that's the reason it's static over here. And there are other reasons also, guys, why we have static variables in Java, but that's a different point. So yeah, then we have a constructor where size is passed and then initialize that size uh, to, or allocated the size to capacity of the queue. Then enqueue operation, we have to just check that the rear should not be equal to the capacity of queue, because if it is equal to capacity of queue, it means the queue is full. You cannot insert any more elements there. Else you can insert elements over here. Then dequeue, same thing. If you have to just check that rear of queue should be not equal to 0, because if it's equal to 0, it means that the queue is empty. There is nothing to delete further. And if that's there, then the opposite, that is the rear of queue is not equal to 0. It means there are elements into it, and then you can delete it. And deletion logic is you have to override the elements from beginning again, because the beginning element, the first element, will be deleted every time. Then display function, there is nothing. You have to just use a system.out.println from beginning to the end. That is from 0 to the rear of queue. And with the condition check that if the rear of queue is equal to 0, it means there is no element to display in the queue, that is queue is empty. So that is it. Now here, if you want to know the size of the queue, so as you have used one-dimensional array and the size is already passed here as an argument, or you can say as a value of the constructor 5, so the size is already known here, right? So there is there's no need of separately knowing the size of the queue. Yeah, it's already known here, that is, or you can use an array, the size method of the array class, as it's the q1 q2 is the array itself here, and that will tell you the size of the particular array. Okay, although it's known here, so there is no need of separately defining it. If the queue is empty or not. So to check the queue is empty or not, guys, this is the condition which we have already used so many times in the display function. That is, if the rear of queue is equal to 0, it means that the queue is empty. So if you want to check is the queue empty or not, this is the logic behind it. There is no such inbuilt function which we could use it over here, but the logic itself can be helpful in knowing that the queue is empty or not. So this is how we implemented our problem statement, that was of creating a queue and implementing the functions of enqueue, dequeue, display, that is accessing the elements of the queue, and then knowing the size of it and to check that this queue is empty or not.
Now let's talk about linked list. Let's understand what is linked list. It is a linear data structure. That means it is storing its elements, or the elements are stored in a linear fashion. Now, if the elements are stored in the linear fashion, that means all the elements can be stored as per the memory availability. Now, what happened in array, right? If we have this memory location, that means if we have a 16 bytes of size available in the memory, only then we can store 4 elements here. If the chunks of memory, right, there were let's suppose 8 bytes here and 8 bytes here, and we want to store these 16 bytes of memory, or 16 bytes of elements. That means there are 4 elements in the array. We want to store those 4 elements in the array. We cannot, since elements can be stored as per the memory availability. That means in linked list we can use these chunks of memory, which was the problem in array, right? And that was resolved by linked list. That means we can use these chunks of memory. Now, if your memory is available, that means if your memory is available in chunks, we can still use the memory efficiently. Now, this is one thing, right? Now, these two things are clear to you guys. Now, the third thing is that you can access elements on a linear fashion, or you can access elements in a linear fashion only. That means if you have a linked list, let's suppose this is a linked list. We'll talk about this, why it is that I'm writing that. So now, in order to access this, you need to access all of these elements. Random access is not possible, right? So let's suppose if you want to directly go to this place, this node, it is not possible. You need to traverse all the nodes one by one. So in a linear fashion. So one by one you will go here, then you will go here, then you will go here, then finally you will go here and access this node. Now, like array, like array, if you have this linked list which is of in which you are storing integer values, you can only store, that means the data stored in all the nodes will be of type integer. Okay, you cannot, there is no such scenario wherein if you want to store a float in this and int in this, that will not be the case. Okay, so you can only store homogeneous elements which is similar elements. So in arrays there was one more problem associated when we are using arrays. That means the size was fixed. So now in this, the size is dynamic. That means if you have four elements to be stored in a linked list, you can store them without wasting any memory or without having the condition where you cannot store more than four elements, right? So if you want to store eight elements, you can store. Again, without wasting memory or without underutilizing your memory. Okay, or you can also let's suppose if I am saying in arrays the size was 4 and I want to store 8 elements, that was not possible. But here that the size is not fixed, it is dynamic in nature. Now we can easily insert and delete elements in the linked list. Now what you want to do, we want to insert an element in a linked list, right? We just need, let's suppose we want to insert a link node in here. So what we are going to do, we are going to just remove this link, add a node, link this node to this and link this node to this. That's it. So with the manipulation of single link, we were able to insert a node, which was not in the case of arrays. We need multiple swaps. Now, similarly, if you want to delete this element, right? So now let's suppose that we want to delete this node. Again, with the manipulation of single link. Earlier it was linking to this, now it's linking to this. That's it. With the manipulation of a single link, we were able to insert and delete a node, which was not in the case of arrays. We need multiple swaps. And also we need to keep this thing in mind while we are inserting, that there is a size available. Like suppose if four elements are there already and you want to insert a fifth element, that means even if you're swapping it, the fourth element that is there, the last element will be lost. That should not happen. Okay. So again, now there's one more thing that is associated with linked list and which is very important, that the root node, that is this node, is the key, right? What do you mean by this thing? That this is the head of the linked list. That means if this head is lost, right, this is the pointer which is pointing to the first node, and this is the guy who is responsible or who makes it easy for us to traverse through the entire linked list. So we always keep the track of our head node, and it is generally termed, or root node is generally termed as the head node, right? And if head node is lost, your linked list will be lost. Okay, now if this head node is lost, your whole linked list will be lost. So you always keep track of this node, and even if you want to traverse, you always store this head in a temporary node and then change this temporary node, not this. It will always point to the first node of your linked list. Now let's talk about applications of linked list. So as we have already seen that if the memory chunks are available here and there, let's suppose 4 bytes are here, 4 bytes are here, 4 bytes are here. So we can use these in order to store 4 or 3 elements, right? And we can link them later on. So if you have a system wherein your memory is very limited, right? And you want to, memory is limited and you want to use that memory to its full extent, right? It is suitable for those applications or the condition where your memory is very limited. So you can easily go for linked list. Also, we have seen that since there is not much manipulation required, right? When you're trying to delete or insert an element, let's suppose you are trying to insert a node, what you will do here, you will manipulate this link, you will link this to this and this to this, right? And then what you're doing with the manipulation of a single link, you are able to insert the element. And same goes for deletion. If you want to delete it, you just have to manipulate this link and you are linking this node to, obviously in this case it is link, you are linking it to this node. So with the help of a manipulation of a single link, you are able to insert or delete the node. So it is the application which requires frequent insertion and deletion operations. It is also suitable for those applications. You can easily go for linked list because you know you will be saving a lot of time as compared to arrays.
Now let's talk about the implementation of linked list in Java programming. So before going ahead with the coding directly, let me tell you the problem statement of the program which we'll be implementing. So here you have to create a linked list and then implement it using the various concepts of classes and methods which are predefined in the packages and libraries of Java. And then we'll be implementing certain functions on it. Functions like after the creation of linked list, we need to insert elements into it. And then we have to insert the elements at the beginning of the linked list, at the end of the linked list. Similarly, deletion process will also see how to delete the elements of the linked list. And then we'll write a code to display the contents of the linked list. And similarly, we'll explore various other methods like how to, look for or search for any given element in a linked list, and also how to, uh, if at all, suppose you want to transfer the content or all the elements of a given data structure to any other data structure, like from stack, you want to copy all the elements to the linked list, or from linked list, you want to copy to stack. So how can you do that? There is a predefined method for that as well for linked list, and that how to use that method we'll see that as well. So that's the whole idea of the code which we are going to write for understanding the linked list implementation in Java programming. So let's switch to the IDE, that is the Eclipse IDE. So here you can see that I have already created a class LList, and there is a main method already defined, public static void main string args. In this itself, I'm going to create a linked list and then perform all other operations on the given linked list. Now, to create a linked list, you need to understand first here that list is a class which is already defined in the Java packages, and that belongs to your collection framework. And to create a linked list, there is also a class called as linked list, of which we'll be creating an object, and that's how we'll create a linked list. So let's see how is that done. So as I said, linked list is a class. L1 suppose equals to new. Okay, again here, like in the stack data structure, we use the type of data you want to store in the linked list or the stack. So similarly here also you have to define the data type for the elements which you will be storing in the linked list. So here in this linked list, suppose I want to store integer elements. So integer will be the type here. Then name of the linked list, that is L1, which is equal to new. Again, new keyword is used to allocate space for the given object or allocate memory to the given object. New, and then linked list. And again, the two less than and greater than signs, and then round brackets, and then semicolon. So here we have defined a linked list L1 or created a linked list L1 using the linked list class. So let's see what's the error over here. Sorry. Okay, so you have to import java.util package, guys, because this linked list class is inside this java.util package. So you have to import either java.util.star, or you can write directly java.util.linklist also. So yeah, once that is done, the linked list is created. That is, you have created an object L1 of the class linked list, which contains elements of type integer. Make sure you provide here the wrapper classes for each data type, not the primitive data types. That is, you should not write here like this int. You can see it gives an error saying that there is a syntax error, insert dimensions to complete reference type. It means what? That the basic or the primitive data types are not supported. You have to provide the wrapper classes. That is, for every data type, there is a class defined in Java programming. So you have to use that class. Now, once this is done, we have to, next step is we have to add the elements to this linked list. To add the elements to this linked list, there are methods already predefined in Java programming. And what are those methods? Let's use that L1 dot add. So add is a method. You can see here the various, options which are being provided. So you can add an integer over here. Then there is add at particular given index what element you want to add. So we'll explore all these. Let's see. So here I'm suppose trying to add 3. Okay. So this will be the first element that will be added to the linked list. Now suppose I want to add another element, maybe 7. Okay. And then another element, maybe 10. Okay, so these 3 elements I added to the linked list. So this is how you will add the element to the linked list. Now there is another one more function which is related to addition or insertion of the elements to the linked list. But this is when you want to update something, like you have added at location, like first you added 3, that is at 0th index, then 7 at the second first index, 10th at the second index. So that 3 elements you have added. Suppose at some given index you want to update the value now. So for that you can use add, and then the second one, add int index and integer element. So here you have to add the elements and provide 2 parameters. One is the index at which you want to add, and the second one is what element you want to add. So this is generally used for updation, like you have inserted already some value and later on you want to update that to a newer value in the linked list, then this is the function which you'll be using, or the method you will be using. This method, that is add an integer and integer element, 2 parameters, one, this returns void as a return type. But the add methods which we already used for adding 3, 7 and 10, it returns boolean, that value, that is true or false. If the addition is successful, it returns true, else it returns false. So we can use this one here. So suppose at location second index, I want to update the value from 7 to maybe 6. Okay. Okay, unless we print this, you'll not be able to see it. So I'll tell you also how to iterate over the elements of the linked list. That's the different thing. I mean, we'll do it later on. First, let's understand the primitive operations here. This is done, that is, the insertion is done. Now let's understand how to remove the element from the linked list. Okay, to remove the element from the linked list, okay, so I'll put a comment over here. This is adding elements to linked list. Now we'll see how to remove elements from linked list. Okay, so let's see how to do that. So again, L1 dot remove itself is a function which removes the elements from the linked list. Okay, so just write L1 dot remove. It's going to remove the element from the linked list. Or there are other functions also, like no, you want to remove from the first, or you want to remove from the last of it. So that also you can do. So you can see here all the methods are being listed. That is, remove last is also there. You want to remove from particular given index, then from there also you can remove. So let's use a remove first here. Okay, so it will remove the first element of the linked list. If I suppose I want to remove the element at the second index, then you can provide the index number over here and it will remove the element from that particular index only of the linked list. Okay. Similarly, L1 dot, you can have remove last as well to remove the last element of the linked list. Okay, so these are the methods which we'll be using. The very simple, very easy inbuilt methods which you can directly make use of. Guys, I'm not saying that you cannot write the you know a complete linked list implementation on your own, we'll do that as well. But as of now, you can use inbuilt methods also, which are predefined in Java library, and that's what I'm doing right now. That is using these predefined methods, it is adding, removing, and all that. Okay, before going to the next any other function, let me just tell you how to access the elements of the linked list, how to iterate over it. Okay, so again here the concepts comes is of iterator class to make the elements of the linked list or to make the linked list iterable. So there is a iterator function which is defined inside the iterator class itself. So we'll make an object of iterator class, and over this linked list we'll call the using this linked list L1 we'll call iterator uh, method, which will make this linked list iterable. So let's see that what I'm telling you. Iterator. Okay. So iterator it is equal to it is a object for iterator class. Okay. So L1, that is the linked list dot iterator. Okay. And then semicolon. Done. So this makes the class iterator. Okay, it's again, okay, you have to import this as well. That's why I said you can directly do java.util.star over here. You need not do it again and again for every single class. You don't have to import that. But okay, no issues. The Eclipse IDE has itself figured out for me to provide that import statement. So I'll go ahead with that. So yeah. Now in this, what I should do is again use while loop to iterate over it. So while there are next elements in the linked list, like next meaning we'll start from the first and keep checking, is there next element, is there next element, is there next element, and until there are next elements in the list, it will keep printing it or keep accessing it. So for that the while loop is being used. While it, that is it, the object of iterator class, dot has next. So this tells that is there next element into it or not. If there is, then I'm just going to print what? It's going to print it dot next. So it will print the next element in the list. Okay. Let's see. So what I'll do is I'll just comment few lines here to just tell you that exactly how it works. So let's see right now, just uncommented lines are that I'm adding these 3, 7, and 10, and I'm running over it, accessing the elements 3, 7, and 8. So let's see what is being displayed over here. So you can see 3, 7, and 10 is being displayed. Again, I'll put a little bit of formatting over here to make it little representable. So yeah, 3, 7, and 10 is successfully inserted in the linked list. Now I'll add at second location 6. Now let's see which one is being updated from here. So you see here at the second location 6 is inserted. It means what? 0 first and then second. This was the second location, second index where 6 is inserted. And the elements after that are shifted one step ahead. So this is used for inserting it somewhere. Getting it? So that's what I said. So later on, suppose you've created your linked list and later on you want to update something, you want to insert somewhere in between some elements. So that you can do using this add different variation of add method with having two parameters. One is index number, other is element which you want to insert. Now let's see the remove one. I'll uncomment this again, and so that you can figure it out. So let's see one by one what is being exactly removed. So if I run this, so you see here it remove at the second index, that is we inserted 6 at the second index, right? So it deleted that. It's only 3, 7, and 10. Now if I say remove first, so the first element should be deleted, that is 3, right? So let's see, is that element being deleted? Yes, it is deleted. 7 and 8 is left. So remove first deletes element in the linked list from first. Now last meaning 10 should be deleted according to the current linked list elements. So let's see that. So yeah, 10 is deleted. So only 7 is left as of now. Okay, and as we are able to see this all these elements because this particular code is working fine. That is, we have created the linked list iterable so that we can iterate over it and access each and every element one by one. Okay, so till here it's clear, I guess. Now let's try to see the other methods which how we can implement over it on this linked list. And those methods are to search the elements into it and also to find out the size of the linked list. Okay, so let's see now how to find out the size of this linked list first, and then how to search the element I'll tell you. So this is the closing of this while loop. Okay, now after this, so to know the size of the linked list, there is a simple function that is called as size. So L1 dot size is what you can call it over from here. Now let me just comment out these lines so that it should not remove everything, okay, from the list. Let's have some elements in the linked list. That's the reason, then only you can get the size. So you can see here, uh, it prints the size over here, that is 3. So this last element which you are seeing over here is your nothing but the size of the linked list. So you can see I printed in the next line. So 3 over here is a size. There are 3 elements only, 3, 7 and 10. 6 we already deleted by this remove statement. So that's how you'll find the size. It's easy, right? So nothing to do. Now let's see how to search an element. So to search an element in the linked list, there is a function or a method called as contain. Okay. So how to call that? That returns a Boolean data type. So we'll store into this b1 is equals to, we'll call on L1 dot contains. So you can see here contains is a thing. Now in the bracket or in the parameter, you have to pass what value you are looking for. Suppose I'm looking for 7. Okay. And then I'm going to print this b1. So as it returns Boolean data type, this contains method. So it will tell that if the element is found, it will return true. If not found, it will return false. So b1 will be true in this case because I'm looking for 7 and 7 is already in the list, right? So it should say true. Let's see that. So when we execute it, it says true. If suppose I'm looking for something which is not there, like 11, then it should say false. So that's how the contains work. So it returns true and false. It doesn't returns the index number or anything of that type. So for that, you have to write a separate code. But simply if you want to know that a particular element is there or not, just search it. Then this is how you can do it. Now, one very important thing which I'm going to talk here is related to linked list. That is, Java provides a very good method support that is called as add all. Suppose you have created one data type or data structure which is having certain elements, and you want to create another or shift that data structure to any other data structure. Like you have stack and you have elements over there. Now you want to shift all those elements to a linked list. There is just one method using which you can very easily do it. I'm going to show you that now. So let's see. So what I'm going to do here is that copy contents from, or I can say better, elements from stack to linked list, or from one data structure to any other data structure. I'm using stack and linked list here, but from any other data structure you can copy it to linked list. Okay, so let's see how it is done. So first we'll create a stack, right? Let me create a stack. So that is how to create a stack using stack class. Okay, I'm going to use it of string type. The elements in the stack are of string type. So it is stack s1 equals to new stack and then semicolon. Done. Yeah, it will ask me to again import java.util.stack. So yeah, we'll do that. Now let me also create one empty linked list. Okay, so linked list L2 this time. Okay, this linked list should also be of type string. Okay, let it be L2 equals to new and linked list. Right, now let me insert the elements in the stack first, and that all the elements I'll copy it to linked list directly. Okay, so to copy the elements from stack to linked list, I should insert some elements. So I'm doing that. How to do that? Using push operation, and then as it is a string data type, so I have to push, suppose hello. Okay, wrong spelling of hello. This is how it is. Then suppose I want to push the next element to be uh, hello everyone. Sorry. So right. So two elements I have pushed hello and everyone to stack. So a stack contains these two elements. Now I want to copy all these elements to a linked list L2. How to do that? So you can call L2 dot add all. So you can see here there are no, so many options coming up. So you can take anyone, add all, and you have to add from where stack to this linked list. So everything from the stack, all the elements from stack will be copied to L2. Make sure these two data structure stores the element of same type because type conversion will be a problem there. So only this is the check which you have to do. And apart from that, you can copy all the elements from stack to linked list successfully here. Let's see, let me iterate over it. So to iterate, we have already written a code over here, right? I'm just copy pasting the same code to save time, guys. So just let it be IT1 this time because it will give an error if I'm using the same variable. Okay, this will be over L2 because L2 is a linked list here. So let's see what's the output. So you can see here, I'm iterating over L2, right? And L2 is the linked list. But I have copied the elements to this linked list from stack, that is S1. And S1 had hello and everyone, but I'm printing L2 where it's printing hello and everyone. It means what? That the elements have been copied from stack S1 to linked list L2. So this is all in the implementation of linked list, guys. So we have studied or we saw how we can add elements to the linked list, then how we can remove the elements from the linked list, how you can remove from the first and from the last, then how you can make the linked list iterable, that is you can iterate over it one by one and access each element individually. Then we also saw how you can implement searching, that is contains method can be used to look for any given element, is it present in the linked list or not. Then you can copy the content of any given data structure to any other. You can use array list also here. There are other data structures in Java, right? Array list can be used. I have used stack over here to demonstrate the example to you. So from stack, I have copied everything to the linked list. So this can be done. Then to do the size of the linked list also, you have a method, predefined method called as size. So by using dot operator on the particular linked list, you can call all these methods and you can successfully implement it.
Now let's talk about the advantages and disadvantages of linked list. First, let's talk about the advantages. So obviously, as compared to array, right? When we talked about arrays, they were fixed in size, right? We need to specify the size in the subscript. So fixed in size, which is not in the case of arrays. It is dynamic in nature and you can add as many nodes as you want depending upon your requirement, right? So obviously when you have that uh, independency over the size, you will never, there's no chance of wasting any memory, right? So if you require 4 nodes, you will use 4 nodes. If you require 3 nodes, you will add 3 nodes only. So in this way, the size of the linked list is entirely dependent upon your application. What are the things that you require, you make them, that's it. So you will not be wasting your memory and you will be utilizing your memory very efficiently. So this is the reason why this is written over here, the efficient memory allocation. How you are doing efficient memory allocation? Let's suppose you have chunks of memory available here and there. You can link them together and allocate the memory and use those memory location for storing the data, right? So memory can be used efficiently. Memory is not wasted. It is dynamic in size and it is very easy to insert and delete a node in a linked list just by manipulating a single link, as we have seen earlier. Just if you want to delete this, you just manipulate this link and just point this link to the next node, which is after this node. That's it. You are done with the deletion operation just by manipulating a single link. Similarly, when you're talking about insertion, at that point, you just if you want to insert at this location, you remove this link, point it to this, and then remove and point this new node to this node that was already there. Again, we are manipulating a single link. Okay. just the manipulation of single link here that is required for insertion, and a single link here that is required for deletion. Now, when we talk about disadvantages, one of the major disadvantage is that you cannot lose your head, right? The head node that is pointing always to the first node, either in a singly linked list or a doubly linked list or a circular linked list. This head node cannot be lost. If this head node is lost, or if it is manipulated, right? If the head node is lost or manipulated, the whole linked list will be lost, right? Let's suppose this is your linked list, and somehow, right, if this is the head node and somehow you made it traverse to this particular point, right? Now head node is pointing to this in a singly linked list. Now there is no way you can access these nodes, and you will get undesired results. Another disadvantage is that you cannot access randomly. So random access is not possible, because if you want to go at this particular node, you have to traverse through the first three nodes first. Why? Because this node knows the address of this node, this node knows the address of this node, this node knows the address of this node. There is no way you can directly go to this particular node. Random access that was there in the arrays, with the help of indexing you can randomly access the elements. That is not possible in terms of linked list, and the address of the first node is known to the head of the linked list or the root of the linked list. Okay, so that head is pointing to this first node. Okay, so you cannot change or manipulate or lose, or you cannot lose your head, because the whole linked list will be lost. Okay, and the random access is not possible in linked list.
Let's see more about what a tree is and the properties of trees. We're going to see the motivation for a tree data structure. We'll formally define what a tree is. We'll see what the concept of rooting a tree means. And there's a relationship between the number of edges of a tree and the number of nodes in a tree. So we'll see what the relationship is. So tree, you can say, is inspired by data which has a hierarchical organization. For example, your file system in your operating system, in your computer. So you have the root folder, and beneath that you have folders and files. And within those folders, you can have further folders and files. So there's a hierarchy. The root is at the top, and you have files and folders beneath the root at the first level. And within the folders at the first level, that is just beneath the root, are further files and folders. So it is a special kind of a graph. You can see it's a graph. If you can represent your files and folders using nodes of a graph, you will observe that if there is a file or a folder within a folder, you can join that parent folder with the child file or folder. So it will form a graph the way we have represented it. However, it's a special kind of a graph. If we assume that you can reach any node from the root, then it is connected. So that's one very important point that we'll note, that it is connected. You can reach from any folder, you can go to any other folder. You can CD, right? You can change directory and move to any other folder. So it is connected. That's point number one. Yet another point we can note in this special kind of a graph, that is tree that we are saying, is that there are no cycles. You cannot move from one node to back to the node itself. It's not possible using a cycle. You have to traverse back on the same path, right? This is not true if you had some kind of symbolic links, that is shortcuts. Let's say you have a shortcut from here to here. Then you would have a cycle. But otherwise, if you didn't have symbolic links, that is shortcuts, if you didn't consider, then this kind of data is acyclic. So the thing that we observed about this graph is it is connected and is acyclic. This is exactly what a tree is. It's as simple as that. It's just a graph where the nodes are all connected. The graph is connected. You can move from any node to any other node, and there are no cycles in this graph. Let's try to construct some tree out of these nodes that we have. So let me name the nodes. So these are our nodes, and we'll connect them through some edges. Is this a tree? No, it's not connected, right? It does not have cycles, but it's not connected. So let's connect C and D. Is this a tree? So it's connected. You can move from any node to any other node. And it's acyclic. Can you go from a node to itself along a cycle? No, there are no cycles in this graph. But let's try to add one more edge. So I'll try to add some edge, doesn't matter which edge. The moment I add an edge, now there is a cycle. You can see the moment we add this edge, there is a cycle. So you can go this way. So A to C, C to D, and D to A. That forms a cycle. So it is no more a tree. So there seems to be some limit on the number of edges that a tree can have. So we'll see that relation later. So at the end of the day, a tree is connected. You can move from any node to any other node, and it is acyclic. There are no cycles. So rooting a tree essentially captures the fact that trees are usually used to represent hierarchical data. So there's naturally usually some node which distinguishes itself. For example, in a file system, it is a root folder. So in a file system, it's a root folder. In a family tree, it's the head, the ancestor who represents the head. And in an organization chart, it's the CEO or someone. So we take a tree usually and we root it. So a lot of times we have to root a tree. It makes sense to root a tree. So rooting a tree just means we are taking one node and distinguishing it. We are calling it the root. We can root a tree at any node. It's up to us. Usually in the situation, it will be clear what is the root. But in general, if you pick up a tree, you can root it at any node. Doesn't matter. For example, this tree, when it's rooted, when it's rooted at A, then we might draw it like this. So the root node, we draw it at the top. And then the children of the root, we draw at one level below, at all the same horizontal distance. Okay, so the same along the whole same horizontal line. So we will draw C. And then you have, for C, you have B and D as the children. And then for B, you have E. So this is how a tree, the tree that we saw, rooted at A would look like. So we draw at each level the set of children from that previous level. The same tree could be rooted at C. How would it look like? We have the node C. And then the children of C. The children of C are like the ones it's connected to are A, B, and D. And then B is has an edge to E. So in this way too, we can represent when it's rooted at C. So the same tree can be rooted at various nodes, and you can view it in different ways. Usually in the situation, there'll be one clear root node. Okay, but if you take a theoretical tree like this, where it's not obvious which is the root, you can root it at any node. So how would you draw this tree when it's rooted at C? Just take a moment and try to draw it. I hope you have tried it out. You can pause the video if you'd like, and you can try it out. So let's see how you would draw this rooted at C. So you have C, and then B and D are the ones it's connected to. And then B is connected to A and E. So you draw that like this. Okay. So that's how you would root a tree. When we root a tree and we draw it, there'll be various levels that appear. So we have this tree and we have to root it at C, let's say. So we root at C. C is connected to A, B, and D. So we draw that. You can see that all the nodes that C is connected to are at the same level. So this is how we draw a rooted tree. the nodes that a node is connected to from the previous level are all shown in the same horizontal line. And then of course B is connected to E, we'll show it below. So that's what is meant by levels. We'll see it more formally later. Now there's an interesting relationship between the number of nodes and the number of edges of a tree. The number of edges in a tree is always one less than the number of nodes. You can check that out. Let me show the previous tree or two trees. Here, the number of edges is 1, 2, 3, 4, and the number of nodes is 5. So the number of nodes is one more than number of edges. Here too, number of nodes is 5 and edges is 4. So is this always true in any tree? Yes, it's always true for any tree. So let's see why. So let's take a tree, a general tree, and try to reconstruct it. So we are given some tree, T. We will reconstruct this tree. That is, we'll take one node at a time from the tree and join it to whatever nodes we have already chosen. So initially we have not chosen any node, right? So it's empty. So we are trying to reconstruct some tree. Okay. In this process, we'll see that the number of edges is one less than number of nodes. So we'll take some node from the tree. We are trying to reconstruct this tree T. Some node you take, pick some node, draw it. Let's say that is N1, node 1. Now definitely there will be a node that is connected to this node, right? Because tree T is connected. So take some node that is connected to any node. Okay. So we take the other node it's connected to. Definitely there's one. Okay. And we also draw the edge that it has in the original tree. Now there are still so many other n-2 nodes that are pending that we haven't picked up. My claim is there is definitely an edge from at least one of these two nodes to the remaining nodes. Why? Because if there is no edge, there is no node which is adjacent to either n1 or n2 in the original tree, then the original tree will be disconnected, right? There will be no way for you to go from n1 to some other node or n2 to some other node. So either n1 or n2, so at least one of the nodes in the currently constructed tree, n1, n2, whatever nodes are there in the set of nodes, must have an edge to the remaining nodes in the tree which we haven't picked up. So that is definitely a neighbor for at least n1 or n2. Okay. Let's say it is n2. Okay, it doesn't matter. Let's say it's n2. So we pick it up. Okay. And let's say that node is n3. Now n3 will be connected only to one of n1 or n2. That's my claim. In fact, I'll say if there are any number of nodes right now in the constructed tree, only one node from this currently constructed tree is connected to n3, is connected to the newly chosen node. How do I say that? Because if this thing had an edge to more than one of these nodes, then the original tree had a cycle and it wouldn't be a tree. That's a contradiction. So it must be connected to only one. It is connected to one, otherwise the original tree would have been disconnected. And it is connected to only one, otherwise the original tree wouldn't have been a tree again. So it would have had cycle. So it's connected only to one. Okay. Really doesn't matter which one. It's connected to one of these. So this way you can go on and construct the whole tree. It's possible, right? Because always in the remaining there is what you have not picked up, there is an edge to the things that is picked up and only one such edge. So in each step we are adding, and at the end we would have constructed the entire tree. All the nodes are added and we are adding all the edges to the chosen nodes also at each step. In each step we are adding one node. So if you see, we started off with number of nodes 1. We started off with a single node and no edges. And at each step, right? And at each step, we add 1 to the nodes, right? We are adding a new node, and it can have only one edge to the existing chosen nodes. So we are adding one edge. So at each step, that relation remains. That is, initially the relation is that number of edges is 1 less than number of nodes. And each step, we are adding one node and one edge only. Therefore, the relation will still remain that E is n minus 1 at each step till we finally arrive at the original tree. So always in a tree, number of edges is 1 less than the number of nodes. In summary, we have understood what a tree is and how useful it is, what kind of data it represents. A tree is formally a graph that is connected and that is acyclic. You have understood what routing is, how routing helps to represent some of the real world data. Routing also implies you have levels of the nodes. And there are also implied directions, by the way. So from the root node to the node it's connected with, you can imagine that there is some kind of a direction. It's an implied direction. This is one of the cases where we'll see an implied direction in the nodes, in the edges, right? So all the things at some level are somewhat within the top level, the level above, right? The node at level above. And finally, we saw the relation between the nodes and edges. The number of edges is always 1 less than the number of nodes.
Now we are in our next topic, which is what is the use of trees. Here we'll try to find out what are the different uses of trees when we compare it with other linear data structures. So let's get started. So tree, as we know, is a non-linear data structure. That means we are storing the data in a hierarchical format. We already know now what is a hierarchical kind of a structure. So now that itself makes a tree a great data structure to perform different kinds of operations. It could be insert, it could be delete. Now, as compared to other data structures, which are linear data structures, say for example an array or a linked list, where we are trying to store the values in the continuous location, which is one after the other. So a linear data structure has its disadvantages when we are trying to perform operations such as insertions or deletions, right? Now tree comes to our rescue whenever we are facing such kind of a problem. So tree is a non-linear data structure where we are not storing the values or the contents in a sequential format. So we have a hierarchical kind of a format to store the values, which can help us solve different kind of problems which require the data to be stored in that particular format. Also, when you use tree as a solution for your application or a program, the time required to perform any operation on a tree is O log of n, which is great when you compare it with other linear data structures. Now, when you consider an array or an ordered array, those are considered very bad when you want to perform operations such as insertions or deletions. Why? Because the data is stored in a sequential format. So from the beginning till the end, you have to traverse or search for a particular value to be deleted. So if that value is present at the end of the array, then from the beginning till the end of that particular array, you have to keep on traversing until you find that particular element. But that is not in the case of a tree. Why? We are storing the data in the hierarchical format and we have different methods through which the insertion, deletions or search operations can be optimized. But that is not possible in an array as compared to a tree. Also, when you consider linked list, the search operation can be cumbersome. So it can be slow as compared to a tree because again here we are trying to store the values in a linked list wherein it contains a pointer and a node. So the node contains the information. So we have to traverse so much things here. So tree comes to our rescue when we want to build such applications. So whenever we are not satisfied with the linear data structures for our application or program, we can go ahead with a tree data structure. So that will help us solve many kind of problems when we are building our application or a program.
Binary search tree. Now, what is binary search tree? So, binary tree is an additional restriction, right? This BST is nothing but the additional restriction on binary tree. Like we have already seen the binary tree wherein at most we can have two children, right? It can be on the left side or it can be on the right side. Now, what are the restrictions on this tree? So, the restrictions are that the data, that is, let's suppose this is 5 and these are another two nodes. Now, the restriction is that if this is a root node, then you always will have the element that is less than your root node. So you can have 4, 3, 2, 1 on these sides, but you cannot have 6 on the left side. Similarly, you can have 6, 7, 8, 9, and so on. On the right hand side, you cannot have 1, 2, 3 on the right hand side. So these are the two restrictions that are there in binary search tree. Now, if you talk about insertion, deletion, and while you are searching the element in the binary search tree, it is much more efficient as compared to binary tree, because we can obviously, when we are trying to search for an element, we can obviously, if let's suppose we are searching for 8, so will it make sense to go on the left hand side? No, we can easily neglect this part. Similarly, we can do it on the rest of the elements. This is one scenario wherein searching is much more efficient than binary tree, because in binary tree we cannot neglect any elements, or we cannot say, okay, now we cannot find an element on this portion, on that portion. Similarly, when we are inserting, now, if the element is greater than 8, so we can easily, in this scenario, right, we can easily go on the right hand side rather than searching where we want to insert it. And similarly, when we are deleting, a little bit of ordering is done in order to get the exact same situation, wherein your root is less than the right hand side elements and wherein your root is greater than the left hand side elements. So that scenario is there in the binary search tree. Now let's talk about the application. It is suitable for applications which require sorted hierarchical data. Let's suppose you have some data and you want to store them in such a way that always you want your elements that are greater than the root on the left, on the right hand side, right? You want them on the right hand side, and for the elements which are less than this root, you want them on the right hand side. Okay, so that you can easily neglect. Okay, you can now, let's suppose, not, if you don't want this scenario wherein you are just dealing with the greater than or the less than, you can have a similar kind of a situation wherein you are saying that, okay, on this side I will always have some files that are related to coding. Okay, let's say an example, and in this I will always have files which are related to entertainment. So you can do that so that you can easily neglect these files, because these are always going to be your coding files, and these are always going to be your your entertainment files. So wherever you require sorting, right, or you want you want your data to be in such a manner that it is easy for you to find, insert, and delete. So therein your binary search tree comes into picture.
So now we are in our next topic, which is operations on binary search tree. So here we'll try to understand what are the different types of operations which you can perform on a binary search tree. Now here we have these operations which you can perform on a binary search tree. So the first one is insert, then delete, then search obviously, and then traversal such as pre-order, in order, and post order. So let's say the first operation, which is insert. Now assume you have a blank tree. Okay, so for the first time when you're creating a binary search tree, the first node will be the root node, and then you are going to decide based on the binary search tree property whether the next incoming node should be the left child or the right child of the root node. So insert is very simple. So first, if there is no node present at all, the first node will be the root node, and then based on the binary search tree property, you are going to make the next incoming node as the right child or the left child of the root node, and then consecutively you can form the right subtree or the left subtree of the tree. Next operation is the delete. So here in delete there are three scenarios. So let's see what are the three scenarios here. So in delete we'll come across zero child when you have zero children, and then when you have one child, and then it could be that you can have 2 children. So these are the 3 scenarios when you're trying to delete a particular node. Okay, so a node which could have 0 child, you don't have any problem, you can simply delete that particular node. And then when you have 1 child, this also will not cause much issue, because you have to just delete that particular node and remove the link. Now the problem is, you have to be very careful when you're trying to delete a node with 2 children. So you have to think which should be the next parent node or the root node. So let me take an example. So suppose I have this particular tree here. So say for example, I have 10 here, I have 8 here, then I have 12 here. Now what I'll do is, I'll extend my tree. Let me have one more value here. So let me have 4 here, and let me have 15 here. So now if you want to delete this particular node 10, which is the root node, now what you have to do, which node, either 8 or 12 should be the next possible root node. You have to decide on that. So now if you want to delete the root node 10, which has 2 children, 8 and 12, now one possible solution is, if you want to make the root node from the left subtree, then you have to consider the highest among the left subtree, which is 8. If you want to make the root node or select the root node from the right subtree, then you should consider the least value from the right subtree. So it could be 12. So that is your delete operation. Then you have your search operation. So the heart and soul lies in the search operation when we are considering the binary search tree. So this is the most frequent operation which we are using, or which we are trying to implement using the binary search tree. And then finally we'll come across the traversal. So traversal is nothing but we are trying to visit each node at least once. So here we'll come across pre-order traversal, in-order traversal, and post-order traversal. Now we are in our next topic, which is pseudocode for binary search tree. So here we'll try to understand how to write the pseudocode for different methods in our binary search tree. Okay, so let's get started. So the first step is, you have to create a binary search tree, right? So for that, the first thing is we need a root node, correct? So the pseudocode goes like this. First, we are going to create pointer or the root node through which we can create the left child and the right child of this particular binary search tree. So what we have to do, first create the node, and then if you want to store the information, you can store it by assigning that particular data which is passed as an argument, okay, to the node or the root node. Okay, so the first value will always go into the root node, correct? And then we are going to create the left and the right child nodes, but initially these will be pointing to null. You can look at these statements over here. So for the first time, when you're going to create a binary search tree, the left and the right side of a root node will be pointing towards null. Only when you are going to insert the values to the left and right of the root node, you are going to remove the null and insert the data or the information over there. Okay, so let's try to understand few more methods of this binary search tree. So the next one is your insert method. Okay, so here we have the pseudocode wherein we are going to check first if the root node, okay, if the root node is equal to null. Okay, then what we are going to do is, let me take an example over here. So for the first time, this is the node, okay, which I'll tell it as the root node. Okay, so assume I'm going to insert a value 20 over here with the help of this particular parameter, right? So if the node, that is the first node in your binary search tree, is equal to null, then you are going to pass that particular data over here and you are going to return this particular node. Fine, as simple as that. And after that, if you want to create the left and the right child of this particular root node, okay, so you have to follow the binary search tree properties. And what are those? So assume if the next value, okay, which you want to insert here is 25. Okay, so 25 is the value, and then let me take one more value, let me take 18. Okay, so you want to insert these two values into your binary search tree. Okay, so what we have to do according to the binary search tree property rules, we have to check if the data which is coming as an input is less than the root node, that is node.data. Okay, so is 25 less than 20? No, right? So what should we do? If data is greater than node.data, that is, if 25 is greater than 20, what do you have to do? Simply call this method recursively and insert that particular value as the right child of the root node. So 25 will be inserted as the right child of this root node. Okay, now the next input is 18, right? So again we are going to start from here. So once we come across this statement, if data is less than node.data, that is, if 18 is less than 20, is it true or false? 18 is smaller than 20. So what we have to do, insert that particular node as the left child of the root node 20. So we're going to create a link over here and make 18 as the left child of this root node 20. So this is how your pseudo code for the insert operation can be written. So you can implement it in any language. It could be C, C++, Java, Python. Okay. But the important thing is you should know the concept of a binary search tree, how exactly a binary search tree is created, how the elements are to be inserted inside your binary search tree. Right. So next we'll check one more operation for our binary search tree. So the most important method here is the search operation. Okay, so obviously binary search tree is famous for its search operation, right? So let me take an example over here. So let me have 5, okay, and let me have one more node over here, say 2, and then on the right side let me have 10, and one more, let me take 20, and let me take one more child over here, which is 1. Okay, so this binary search tree is drawn according to the rules of a BST, right? So let's go to the pseudocode over here. So first, what we want to do here, we are going to pass the data or pass the element which you want to search, right? Now we should also pass the root node over here, the pointer to the root node, right? And then we are going to check if root equals null, okay, that is if nothing is present in our data, right? Or if root.data equals the data. Suppose the search value which you want to search for is 5. Okay, so at the first statement itself you are going to find a match for your search key, right? So what you can do, you can simply return this particular node's value to the function which is being called, right? So this is the first step, that is if the search key is present in the root node itself. Fine. Now what if it is not present in the root node? So the next step is you have to search it in the left side, or you can search it in the right side. Based on what condition? Let us see that. Now assume if the next value which you want to search for is 2. Okay, so now you're going to check if root.data, okay, that is 5, is less than the data which you want to search. Is it true? So 5, is it less than 2? No, right? So you're going to simply skip this part, okay, and go to the next set of statement over here and check if root.data is greater than that of the search element, right? So obviously this statement is right because 5 is greater than 2, right? So we have to simply search for our element in the left subtree, right? So you can simply not waste your time by searching on the right side of your subtree. So that is why search operation is very, very important in a binary search tree. right? So finally, let me take one more example. Suppose if you want to search for the value 20. Okay, so what you can do, simply compare this particular root dot data, that is 5 is less than 20, which is written over here. Okay, and if this is true, that is 5 is less than 20, then you have to simply search in the right side of your binary search tree recursively. Okay, so first you are going to compare 20 with 10, no match, right? And then you are going to compare it with the value over here, and then finally you will find a match over there. Okay, so by this you are not traversing or wasting your time traversing the left or right subtree. You are first comparing the search element with the root node, and then decide whether you have to go to the left subtree or to the right subtree. Okay, so this will save a lot of time in your search operation, right? So I hope with this you have understood how to implement a binary search tree with the help of this pseudocode. You can implement this in any programming language. Okay, thank you. Now we are in our next topic, which is pre-order traversal. So here we'll try to understand how a tree can be traversed in this particular pre-order fashion. So let's get started. So here we have to follow some steps or some rules to traverse a tree in a pre-order traversal method. So what are these rules or steps to be followed? So first is, in pre-order traversal, we have to traverse the root node first, and then we have to move to the left side of the tree, and then traverse the left side or the left subtree of a node, and then we have to move to the right side of the root node, and then traverse all the nodes present in the right side of a tree. So these are the steps which you have to follow whenever you are traversing in a pre-order manner. So you have to remember these steps in order to follow this particular traversal method. So what are the different uses and what are the different applications of a pre-order traversal when you are trying to apply it on a tree or binary tree or a binary search tree? So let's try to understand these with an example. But before that, let us try to understand how this pre-order traversal works. So let me take this example. With this example, you'll easily understand how pre-order traversal can be performed on a tree. So at the root node, we have 15. And then on the left hand side, we have 12 as the left child. And on the right hand side, we have 20 as the right child of the root node 50. Now, if you observe, the left side is also called as a left subtree if you have more number of nodes. And on the right hand side, it is also called as a right subtree because we have more number of nodes there. So there also some sort of subtree being generated. So now we have to continuously traverse from the root node until you reach all the leaf nodes in this pre-order traversal. So let's start and try to understand how this particular tree can be formed into a pre-order traversal method. So what we have to do here, first we have to start from the root node. So pre-order traversal, we are always starting with the root node. So 15, what I'll do, I'll make a note of it here. Next, according to the steps, what we have to do, go to the left side of the tree. So this is my left side of the left subtree. So here I have 12 as the left child of the root node 50. Now here again, if you observe, we have a tree here, which is a left subtree. Now this left subtree must also be traversed in a pre-order manner. So here again, I'll apply the same rules. What I'll do is I'll go to the left of the 12. So here what I can see is the value 10. So simply I'll make a note of this value 10 here. Correct? Let me repeat that. So here I have the left child of the root node, which is 12. And then I'll make a note of it here as well. So according to the rule, root node first and then the left and the right. So now I have made 12 as a note in my list, and then I'll continue to traverse on the left side of the left subtree. So here I come across the value 10. So 10 I have written it here. Now what is remaining here in the left subtree? It is nothing but 14. So now 14 I am listing it down here. So now if you observe, we are done with the root node we are also done with our left subtree. So we have completely traversed our root node and the left subtree. So 15, 12, 10 and 14. This is what we have got after traversing the root node and the left side of the root. Now what is remaining here? The right subtree. So in the right subtree, again we have to apply the same rules and traverse this particular right subtree recursively so that we finally get our pre-order traversed values. So now here if you observe, as a parent we have 20. So I'm listing down 20 here. And then we have 18 as the left child of 20. So what is the next thing? List it down here as well. What is remaining now? The last node is 25. Now list it here. So according to the rules or the steps of pre-order traversal, we have traversed all the nodes in our tree, and this is what we have got here. This is the list which we have got after traversing all the nodes here. Now you might be thinking, what is the use of this pre-order traversal? What are the different applications and uses? So the first and foremost is, whenever you want to replicate a particular tree or create a copy of a tree, you can use pre-order traversal because it will generate the same type of a tree. So that's the first thing. What is the next thing? Whenever you want to count the number of nodes in your tree, you can use pre-order traversal. And the third one is, whenever you want to count the number of leaf nodes, the nodes which are at the end and which do not have any child are called as leaf nodes. So whenever you want to count the number of leaf nodes in your tree, you can make use of pre-order traversal. And then one important aspect of pre-order traversal is, whenever you want to convert an expression tree into a prefix notation. Let me take an example so that you have a better understanding. Now here I'll draw a small tree. So here in my root node I have this plus operator, and on the left hand side I have minus, and on the right hand side I have suppose division. Now these operators also have some child, so let me write A here, and let me write B here, let me write C here, let me write D here. So now assume this is an expression tree which you have got, and you want to apply the pre-order traversal to this particular expression tree. So what will be the output of this particular expression tree when you apply the pre-order traversal? Let us see that. So first what we do, we visit the root node. So I've got the plus here, and then what we do, we visit the left subtree. So here we have the minus operator, and then we have the operands. So we have to traverse what? The left child of minus, which is A, and then we have to traverse the right child, which is B. Now again we are done with our root node and our left. So now we are done with our root node and our left subtree. So now what is remaining again here? The right part. So on the right part we have the division, then we have the operand C and D. So this is one more important application of a pre-order traversal. You can convert an expression tree into a prefix notation. So I hope with this you had a better understanding of pre-order traversal. Now we are in our next topic, which is in-order traversal. So here we'll try to understand how to traverse a tree in this particular in-order fashion. Let's get started. So in this in-order traversal, what we do is, first we visit the left side of the root node, and then we visit the root node. So this is the difference from the pre-order traversal. So first we visit the left subtree, then we visit the root node, and then we visit the right side of the root. So these are the steps or the rules which you have to follow when you want to perform the in-order traversal on a tree. Now, what are the uses of this particular in-order traversal, and how to implement or how to traverse this particular in-order traversal? We'll try to understand this with an example so that it will be more clear for you people. So just look at this example. We have a tree here. Now we want to perform in-order traversal on this particular tree here. So just observe the tree and be with me to understand this particular example. Now at the root node we have 15, and then on the left side of the root node we have 12, and then on the right side we have 20. Now these two are also left and right subtrees, as we know. Now, where do we start from? Where do we begin from according to the rules of in-order traversal method? Now we have to begin from the left side or the left subtree. So now this is our left subtree, correct? Now here we have to start from 10, because this is our parent node, which is 12, and this parent node 12 is having the child 10. So we are going to start our traversal from this node 10 here. So what I'll do, I'll just make a note of this 10 here, and then I will move on to the parent node, which is 12, and then again I'll make a note of this parent node 12 here. Then finally I'll traverse to the right child of the parent node 12, which is 14. Then again I'm listing it down here. So now I'm done with the left subtree here, correct? So now what do I get after traversing the left subtree? I get 10, 12 and 14. This is what we get after traversing the left subtree. Now let's move ahead and continue with our traversal operation. Now again we'll go back to the root node. Now our next job is to make a note of this root node here. So I've listed down 15 here because we are done with our left subtree. So the next thing is obviously we have to list down the root node according to the rule of the in order traversal. So we have listed it down here. What is the next thing? We have to traverse the right side or the right subtree of our tree here. So when we move to the right side, we have 20, 18 and 25 here. So 20 is the parent node, which is having two childs. Now what you have to do? Again, traverse in the same manner. So here I'm going to move to 18. So I'm listing it down 18 here. And then again I'm traversing to the root node and then making a note of 20 here, which is the parent of these two children. Now finally, I'm moving to 25, which is the last value which you're traversing in our tree. So I'm writing it down here as well. Now if you observe, we started from 10 here and traversed all the way to 25 here by applying the in order traversal rules or the steps. Now look at this list which you have got here. What do you observe here? So if you observe this list, it is in an increasing order, which is nothing but ascending order. So this is one of the important application of this particular in order traversal. So whenever you apply in order traversal on a binary search tree, what you get is a sorted output. So it could be ascending order in this particular example which we have seen. So like this, let me take one more example. What I'll do is I'll draw a small tree here. So let me write minus here and let me draw two children. Let me say plus and then multiplication. And then again these two nodes have child x, y, and this has s and t. Just assume this. Now if you apply in order traversal on this particular expression tree, what is the output you get? So there are situations when you want to visit the left side or the left subtree first, then the root, and then the right subtree or the right side of a tree. So when such scenarios are required by your application or program, you can choose in order traversal as a solution for your program. Now look at this example. What we'll do is we'll try to traverse this expression tree using the in order traversal steps. So first what we get here is we have to go straight to the left subtree. So here what we see in the left subtree is we see x. Then when you visit the root node you have plus. Then the right child is 1. Now let us go to our root node where we have this minus symbol. And then again we have to traverse the right subtree. So in the right subtree what we have s, we have star, and we have t. I have missed this minus here. So x plus y minus s into t. So this is your in order notation of this expression tree. So you can also apply in order traversal to such expression trees. So with this, I hope you have understood how to traverse a tree in an in-order fashion. Now we are in our next topic, which is post-order traversal. So here we'll try to understand how exactly a tree can be traversed in a post-order traversal method, and what are the different uses when you traverse a binary tree in post-order traversal. Alright, so let's get started. So, what are the steps to be followed when you want to traverse a binary tree using pre-ordered traversal? So, these are the steps which you have to follow. So, the first step is you have to visit all the nodes on the left side of your tree, right? And the second step is you have to visit all the nodes on the right side of your binary tree. And the last step is you have to finally visit the root node at the end of this traversal method, right? So you have to always remember in a post order traversal, first we are going to visit the left side of our tree, then we are going to visit the right side of the tree, and then finally we are going to visit the root node. So let me take an example so that it will be clear how exactly you can traverse a binary tree using this particular traversal method. So let me take this example here. So the first step is we have to visit the left subtree, then the right subtree, and then finally the root node. So first, when we go to the left side of our tree, we have a left subtree here, correct? So in this left subtree, apply the same set of rules of post-order traversal. That is, visit the left node first, that is 10. So I'm going to make a note of 10 here, and after 10, I'm going to visit the right child of this left subtree, which is 14. So 10 and 14 both I have listed down here. After this, I'm going to visit the root node or the parent node of this left subtree, which is 12. Fine. So 12 is listed here. So now we have completed traversing the left side of our binary tree, which is 10, 14 and 12. Next step is we have to go all the way to the right side of the right subtree of our binary tree and then apply the same set of rules, right? So here I'm going to visit 18 first. 18 is written here. Next, visit 25, which is the right child of node 20. So 25 is listed here. Then finally we are going to visit the parent node, which is 20, right? So 20 is listed here. Then the last step is we have to visit the root node. So root node will be visited at the end. Fine. So we started all the way from 10 here. We went on to the right subtree and then finally we ended up at the root node. Right? So what are few applications of this post order traversal? So one operation is you can delete or free the nodes. So this is one application of your post order traversal. Okay. And one more application is whenever you want to perform the post order expression. Okay. From an expression tree, you can use post order traversal. So how does that work? Let me take an example. So now consider this example here. I have an operator here, say minus. I have one more operator, say division, and then I have one more operator. Let me take plus. Okay, and this division has a child. Let me take A, and one more child, which is the operand B, and this has child. Let me take X, and this has one more child. Let me take Y. Fine. Then what we're going to do is apply the post order traversal on this expression tree. So here we have the operators and the operands. So operands are always on the leaf side or the leaf nodes, right? So when we apply the post order traversal, what is the output we get? Which is nothing but the postfix expression. And how do you get that? So first we'll begin our traversal from the left subtree here. So first I'm going to visit what? A here in this example. Next, I'm going to visit the node B. So after A, B it is. And then finally, we are going to visit the parent node, which is the division operator. Fine. And then we are going to go to the right side of our expression tree, and there we are going to get the operand X. Okay. And then we are going to get the operand Y. So X and Y here. And then finally, we are going to the parent of X and Y, which is the plus operator. And then finally, we are going to visit the root node, which is the minus operator. So this is your postfix notation or expression from this expression tree. So there are situations when you want to visit the left side, the right side, and then finally the root node. So whenever there is a requirement of such scenarios in your application or programs, you can take help of this post order traversal and solve your problem. So I hope with this you have understood how a post order traversal works and what are few applications of this post order traversal. Thank you. Now we are in our next topic, which is Java implementation for binary search tree. So here we'll try to implement the code for various operations in a binary search tree. So let's get started. So here we have the implementation of binary search tree. So if I have to start typing and explaining, then it'll take a lot of. So what I've done is we have the implementation code here. Don't worry, I'll explain the code line by line so that you have a better understanding, and all the methods implemented will be explained in detail. So let's start with our first line of code. So we have a class here, public class demo bst1. Then I'm creating an inner class here, public class tree node. Now whenever you are writing a program for tree, binary tree or binary search tree, the first thing is you have to create the tree first. So how to do that? First we need a root node, we need a left node, we need a right, and then the data or the information which you want to store inside your tree. So for that reason, what I've done here is first is int data to store the information inside the nodes. Then I have created the left node and the right node here of type tree node. And then we have a constructor here to initialize the members here. So this dot data is equal to data will initialize the data, and this dot left and this dot right is equal to null will initialize these two with the null, because initially the tree is empty. So whenever it is empty, we don't have anything to fit into our left or right. So that is the reason we are inserting null at this particular point here. Also, we are left out with our root node here. So that part is also declared here. Now again, when the tree is being created for the first time, we are going to insert the root with also null. So that is done here. So far we have created a tree, we have created the left and the right node, and root node is initialized with null because it is empty initially. So this part is with our tree creation. Now next, what are the few more operations? So let's start with insert, because once you've created a tree, the next thing is if you want to perform other operations, first the values should be present in your tree, right? So what we'll do is we'll create the insert method. So this is our insert method. Just observe this statement here. So insert tree node root comma int the data to be inserted. So we are passing two parameters here. One is the data which has to be inserted, and the other is we need the root node as well. Now, what is the first scenario when it comes to insert operation? So when we have insert, first we are checking if the tree is empty. If the tree is empty, then the first value should be inserted in the root. Correct? Now for that, what we are doing is observe this statement. If root equals null, then root is equal to new tree node. We're passing the parameter, the data to be inserted. So this statement will insert the first value in your tree inside the root node. If the tree is already present, if you have already few values or few nodes in your tree, then based on the binary search tree rules or the constraints, you have to properly insert the values. So what are those rules or situations? Let's try to understand. Now, if the value which you are trying to insert is smaller than that of the root node, what you have to do? You have to insert that particular node as the left child of the root, correct? So for that, what is the code or line of code? So if root dot data is greater than the data to be inserted, then insert that particular data as the left child of the root node. And how to do that? Root dot left is equal to insert root dot left comma data to be inserted. So here you are calling this insert function recursively to insert the value as the left child. Now, what could be the other scenario when you're trying to insert? So other scenario could be that the value which you're trying to insert is greater than that of the root. What do you have to do at that point of time? You have to make that node as the right child of your root node, correct? So for that, what is the line of code? Else if you're checking if root dot data is smaller than that of the data which you're trying to insert. What do you have to do then? Simply assign that to the right side of your tree. How to do that? Look at this particular line of code. Root dot right is equal to insert. Again, we are calling the same function recursively. Insert, but this time it is root dot right. And the value which you are trying to insert through the data to be inserted parameter. Clear? So I hope with this the insert method is clear. We're passing two parameters, the data to be inserted and the root. And first we are checking if root is equal to null. If yes, then simply insert that into the root node. If we already have some content in our data, then check and go with the binary search tree properties, insert the data or the nodes appropriately in the left or the right child. And then finally, we will return our root. So this completes our insert method. Now what is the next thing? We can also implement the search method. So how does a search operation work in binary search tree? First, we are checking if the value is present in the root node or if the root node is empty, nothing is there in our root tree. That is the first situation. Next possibility is you have to compare the search value with the root node or compare it and check if it is smaller or greater. If it is smaller, search in the left subtree. If the value is greater than that of root node, search in the right subtree. So this will solve your problem halfway through because you're not searching the whole tree here, correct? Let's try to understand the code here. So this is a method search tree node root int data to be searched, again of type tree node. The first condition here is we are checking if root equals null. What if nothing is present in your data? Then what are you trying to search? Correct? So we are trying to check that here. Or what if root dot data is equal to, that is double equal to data to be searched? You are comparing the value present in the root and the value which you are trying to search, if both are equal or not. If yes, then we are going to return the root. As simple as that. So now we are done with our first scenario. What could be the next possible scenarios in the search operation? Same according to the binary search tree properties. If the root dot data is greater than that of the value which you are trying to search, then what you have to do? Simply search for that value in the left subtree or the left side of your binary search tree. So for that, what is the line of code? Call the search method recursively. Search root dot left comma data to be searched. So this will search for the data on the left side of your binary search tree. Similarly, what if your value is not present in the root, is not present in the left side of your tree? So what is left now? Only the right part or the right side of your tree. And how to perform the search there? Simple. Again call the search method recursively, but this time it is root dot right and pass the one parameter data to be searched. So this will search for the value recursively on the right side. So all these methods are written recursively because this will solve the problem of lengthier code. So if you write iteratively, the code will be simple, but it will get extended. So here the code is according to the concepts of the binary search tree. It is very easy to understand if you have understood those concepts very well. You will not feel the program is lengthy or anything. So now let's continue. So this time let's discuss one of the traversal methods, which is in order traversal. So what happens in order traversal? First, there we are trying to traverse the left subtree of our tree. Then we'll visit the root node. Finally, we'll visit the right sub. So this is what happens in an in order traversal. And how to write the code for that? It is very simple code, just 4 to 5 lines, as you can see on your screen. So first we are going to check if root equals null. That is, what if nothing is present to traverse, correct? So we are going to check if root equals null. Then we are going to simply return nothing. What is the next thing? Next, we will call our in order method recursively and we'll traverse to the left side of our tree. How to do that? In order, pass the argument root.left. So this will recursively visit all the nodes from your left subtree. Similarly, after traversing the left subtree, we have to visit the root, correct? So now we are printing out the value present in our root. Then finally we have to traverse to the right. So for that, again the same line of code, but this time the parameter will be root.right because we want to traverse the right side of our tree. So with this, we have completed the in order traversal method as well. What is the next thing? Our driver program or the main program. But before that, just see here, we also have few wrapper methods for the methods which we have seen so far. So insert method is being called in the wrapper method insert into tree. Similarly, search tree is a wrapper method wherein we are trying to call the search method. And inside in order traversal, we are calling in order. Now, why is this written? So that it will enhance the readability of your program. So anybody looks at your program, he's able to understand by the code that, okay, this is the flow of the program. From here, we are going to this particular method. So this will increase the readability. Now, let's move to our driver program or the main method. So here we are creating an object or an instance of a class which is BST. And then we'll also need another two variables to take the input for our tree, correct? So we are also using the scanner class here. So scan is equal to new scanner system.in. So scanner is a class through which you can take the input from the keyboard or any other input device. So as we need input into our tree, we are trying to take it from the user. We're trying to make it a little bit of interactive program. So next line, system.out.println, we're asking the user how many numbers he wants to give as an input to the binary search tree. Now here, n is equal to scan next.int. So this will take the input for the n, which is the number of values to be inserted into our binary search tree. And then we're asking the user to enter all those n numbers. Then we have a simple for loop here, simple for loop block, wherein we are continuously taking those inputs. So for that, num is equal to scan.nextInt. So this will give the input into the variable num, and immediately we are calling the method bst.insert into tree, which will insert the value entered by the user into our tree. Next, we are simply displaying a message once we are done with inserting. Tree insertion done. And then we will try to perform a search operation. So we are asking the user enter the number to be searched. We are storing again that in n. And this time we are checking if the number entered by the user is present in our tree or not. And how we are doing that? If bst.search tree of n, we are passing the parameter n here, is not equal to null. So whatever value the user inserts, we are checking if that value is present in our tree or not. If it is present, then simply we are going to display the message number found. Else, we are going to display the message number not. And then finally, we will also try to print the contents of our tree in order traversal method. So how to do that? Just call the method. So bst.inorder traversal. That's it. So this will print your tree in the in order method. So what we'll do is we will quickly run a program and check if you are getting the proper output. So enter how many numbers. So let me give 7. So we'll quickly let me give the values 25, 20, 5, 7, 12, 15. One more value. So 21. So tree insertion done. Now we have to enter the number which we are trying to search in our tree. So let me search for 21. So the number found and the in order traversal is also being printed on the screen. So in order traversal, if you observe, it is in ascending order. So in order traversal will always print the contents of a tree in a sorted manner. Now what we'll do is, here I have shown only in order traversal, correct? Similarly, you can also implement pre-order and post-order with the same line of code, just a little bit of changes if you know the traversal properties correctly. Now what we'll do is, we'll also try to implement pre-order and post-order traversals. So for that, what I'll do is, I'll simply copy paste these contents. You don't copy, you please type it here. Due to time constraint, I am copying it. So pre-order, let me print the pre-order. So here I'll make it pre, okay, pre-order traversal. And then I'll also create a wrapper method for the same. So it will be pre, and this will also be pre. What else? The main part. Now what happens in pre-order traversal? First we are going to visit the root node, then the left, and then the right. So accordingly, change the lines of code here. So first we are going to visit the root node. So this statement I will put it in the first line, and then we have our left and the right. So are we done here? Yes. So we have written the code for pre-order, we have written the wrapper method also, and we are printing it here as well. So let me make the corrections here. Yes. So this is a pre-order traversal. Similarly, let us create the post order as well, so that you can see the examples for all types of traversal methods. So post order traversal, so here it will be post. Similarly, we'll create the wrapper method as well. What I have to change here, this will be post, this will be post. Now, so in post order, we are visiting the left first, right next, and then finally the root. So now what I have to do, I have to simply move this line at the end, and this will be post order. That's it. Those are the only changes which you have to make. So if you have known these traversal methods, it's very easy to implement. Now we are done with everything. Yes. So let's quickly run and check. Let me insert few numbers this time. Let me insert 5. So 25, 22, 1, and 7. Tree insertion done. Enter the number to be searched. So this time let me insert a number which is not present in our tree. So let me check with 36. Number not found. If you can see this, number not found. In order traversal, it is printing it in ascending order. Pre-order traversal is also being printed, and post-order traversal is also being printed. So we have performed the insertion, creation of a tree, insertion of a tree, searching for a value in your tree, all types of traversal methods also. So I hope with this you have understood all the methods which we have seen so far in our example. So from the beginning, we'll quickly check out. So this was our tree construction. After this, we had a method to insert the values into our tree, and then we had a method for search operation. Then we created the method for in order traversal, method for pre-order traversal, method for post order traversal. Now what are the changes here? It's just the rules which you have to follow, the steps which you have to follow for performing these traversals. So all the lines of code are same, but you have to follow the steps for the specific traversal methods. And then we have our wrapper methods here as well. And then finally we have our running program, driver program, our main program. So I hope with this you have understood the implementation of binary search tree using Java.
Now let's talk about advantages and disadvantages of binary tree. If you talk about advantages, we can represent data with some relationship, right? So this is the root node, or this is the parent node, and this is the child node. So that relationship, parent-child relationship, is always there. And while you are inserting or searching an element or a node in a binary tree, it is much more efficient as compared to other data structures which we have seen. Now, if you talk about disadvantages, if you want to sort this binary tree, it is much more difficult, right? Because we can either go on the left side. This can be a tree. That means this is a left skew tree, or this can be the scenario wherein we have all the elements on the right side of the node. So this can be another scenario wherein we have this right skewed binary tree. So sorting is difficult and it is not much flexible, right? If you talk about this binary tree, we always have either the two children or one children or no children. There is no flexibility in terms of how you want to store it. Can we store another node on the with this root node? No, that is not the case, right? And we don't follow any restrictions like, okay, we always find this node. That is, if this is in root node, we always find an element which is less than this node on the left side or on the right side. That is of the greater element. So that flexibility is not there. Binary tree. Now let's talk about what is binary tree. So it is a hierarchical data structure. As we have seen in earlier data structures like arrays, linked lists, stacks, and queues. All of these data structures were linear data structures. But when you talk about tree, is a hierarchical data structure. That means it can have one or more than one children. Doesn't have to be explicitly two children, but when you talk about binary tree, therein you can have at most two children. That means if this is the node and then it can have at most two children, or if this is a node, it can have either left child or the right child, or it can have no children at all. Okay. So this is a binary tree. And now this is known as the root of the tree. That means the first node is known as the root of the tree. And you cannot access elements or these nodes directly. Okay. So now this is the whole structure of a binary tree. Now there are some common traversals, right? How we can traverse through all these nodes. So one of the common traversal is pre-order, wherein you always, whenever you are on this node, you always print this node first. What is the value of this node? Then you go on to the left side and do the same. Then again you go on to the left side, then do the same. Print, go on the left side, print, go on the left side, and so on. Unless and until there is no left, then what you do is print that thing, okay? Then after that, you will go on the right side. So pre-order follows print first, then go on to the left, then go on to the right. Similarly, post is saying that whatever is you have, print it at the last. So go on the left, go on the right, print at last. And in order says left, print, and right. So these are all traversals. We will also see one by one how we can implement it, and how we will also see examples based on these traversals. Now let's talk about the applications. If you have seen the file hierarchy system, wherein we have the root folder, and inside that root folder we have subfolders like music, and we have bin, we have files, we have program files, and all those things, right? So it is a kind of a hierarchical data structures, right? And explicitly here we are not talking about binary tree but generalized tree. Now, if you have binary tree, it has multiple variations, right? If you talk about this binary tree, so here you always have either or the left child or the right child. When you talk about BST, the childs are inserted in the tree in such a way that on the left side it will be always less than the root, and on the right side it will be always greater than the root. So this is a variation. It is known as BST. So you have aerial tree wherein you don't exceed the height more than 2. So that is one more variation. Then we have red black trees. So these are all variations of binary tree.
Now we are in our next topic, which is tree versus binary search tree. So here we'll try to find out the major differences between these two and how do they get along with each other. Let's get started. Now, a normal tree, a general tree, or just a tree. All three mean the same. So do not confuse yourself with these different terminology. Now, in a tree, a node can have either zero child, one child, two children, or three children. It can have any number of nodes. So there is no restriction on how many nodes must be present inside a tree or when you're constructing a tree. Now that is not in the case of a binary search tree. And a tree also does not follow any ordering when you're trying to construct. So there is no arrangement as such that this value should be placed in the right subtree, this value should be placed in the left subtree. You can place that value anywhere, right? And there is no restriction that a parent must have only 2 child nodes, 3 child nodes. You can have any number of child nodes for a parent. Now let's see how binary search tree is different from a tree. Now, as the name itself says, you can have maximum of 2 child nodes in a binary search tree. Now you can here also again you can have 0, 1 or 2, not beyond 2. The restriction is maximum 2 child nodes. That's it, nothing more than that. Now, unlike a normal tree, we have some sort of ordering here. We do follow a ordering in case of a binary search tree, but that is not in the case of a normal tree. So here we have some sort of arrangement in case of a binary search tree. Now consider there is a root node. Now all the values present on the right side or in the right subtree of a root node must be greater than that of the root node, and all the values present in the left subtree of the root node must be smaller than that of a root node. So this is what is followed in a binary search tree. Now let me take one more simple example through which you'll understand why binary search tree has an advantage when you're trying to consider search as a major operation. Now consider you have your normal tree, okay, and you want to search for a particular number in that particular general tree. Now what happens is you don't know where that number is present, so you have to all the way drill down to the leaf nodes until you find the particular value. But that is not in the case of a binary search tree. Now what happens here, now there is a root node, so if the value which you want to search is greater than that of root node, you can simply traverse in the right subtree of the root. If that value is smaller than that of the root node, you can simply traverse in the left subtree of the root node. So this makes your search operation faster as compared to a normal tree. So in a normal tree, you have to traverse all the nodes and check if that value is present or not. So that might get your tree search operation little slower than that of a binary search tree. Fine. So I hope with this you have understood the major differences. Let us begin our discussion with introduction to binary tree. First of all, what is this tree? So tree is one of the fundamental data structure wherein it is used to store and organize data, right? So here we'll discuss what is a binary tree, what are the different terminologies associated with a binary tree, and how does it work. So let's get started then. Binary tree is a tree where a node can have 0 to a maximum of 2 child nodes. That is why the name binary tree. Okay, because binary means 2, right? So here in a binary tree, a node can have either 0, 1 or 2 child nodes. That's it. Nothing beyond 2 nodes, right? So this is how a binary tree will be created. And then in a binary tree, we do not store the data in sequential memory locations. Okay, this is very important thing to remember here. We are not storing the data in sequential memory location, that is one after the other. So how do we store the data in binary tree, right? So binary tree is a non-linear data structure. That is, we are storing the data in a format called as hierarchical. Now, what is this hierarchical format? Let me take an example. Suppose you have your computer or a laptop, a desktop, right? So there you have a folder which is my computer or my PC, right? So inside that folder, you are going to create one more folder called as games, right? And inside that games folder, you can have another folder, say XYZ, which is nothing but your game. So here at the topmost level, you have your my PC, the folder. Inside that you have the games folder, and inside that you have your games, right? So this is how a hierarchy is formed, right? So a tree is a non-linear data structure wherein you're going to organize or store the data in a hierarchical format. And this is also called as you're storing the data in multiple levels, right? Because you have a level at the top, then below that you have another level, then it can continuously have more number of levels. So this is how a binary tree can be created. Now, what are the different terminologies associated with a binary tree? Let's check out those. So these are few terminologies associated with a binary tree. So what are those? So the topmost level, okay, we have something called as a root node, right? So the topmost level, we have something called as a root node. And then to connect these nodes, okay, we have something called as a edge or a link, right? So with the help of this edge or a link, we are going to connect the nodes in our binary tree. Fine. Next, this root node has two child nodes. What are those? Which is nothing but node B and node E, right? So you can call the node B and the node E as the child nodes of this parent node A. Fine. Now, this node B can also be a parent when it has some child nodes, right? So in this example, we have C and D as the child nodes of this node B here. So B can be called as a parent node of these children C and D. Similarly, we have one more parent node which is E and having two child nodes F and G. Now observe these two nodes F and G. Okay, they are sharing a common parent node which is E, right? So F and G are also called as sibling nodes because they are sharing a common parent. Now C and D are also called as siblings because they are sharing a common parent node which is B. Now D and F, can we call them siblings? No. Why? Because they both are not sharing a common parent. So D and F cannot be called as a sibling nodes, right? Then there's one more terminology called as leaf node. So leaf node is the one which doesn't have any children, right? You can say C, D, F and G as leaf nodes because they are not having any children, right? So they are the last nodes of our tree, right? So those nodes are called as leaf nodes, right? Now we also have something called as levels, okay? So now the root is always at level 0, okay? Remember that. And the next level is what? The child nodes of the root node, right? So here B and E are at level 1. Similarly, when B and E have child nodes, then the next level is called as level 2. So this will keep on continuing until your tree grows. Fine. And then observe one more thing here. The root node doesn't have any incoming arrow or any incoming edges or link, right? So root node never has an incoming link. So which is the important thing to remember here, right? And binary tree can only have 0, 1 or 2 child nodes. That's it. So I cannot create another link here saying B has 3 child nodes. Okay, that is wrong in the case of a binary tree. Fine. Now one more thing to observe here. Now this B, C and D. Okay, so this can also be called as a subtree, right? So we can say that this B, C and D is forming a left subtree in our binary tree, right? Similarly, the nodes E, F and G is forming a right subtree for our binary tree, right? So these are few important terminologies which you have to remember whenever you start working on the binary trees. Fine. So you have to remember all the terminologies carefully. So whenever you are working on a binary tree, you should take care that you should not create more than 2 child nodes for any particular node. Fine. So I hope with this you have understood how to create a binary tree, what are the different terminologies associated with a tree, and how does it work. Thank you.
Now let's see what is binary tree. So here you can see that it's written why binary tree. So you might have a question that if you want to understand the concept of heap, then why you are understanding what is binary tree? Because as I told you that heap is a complete binary tree. So without understanding the concept of binary tree, it will be difficult to understand the concept of heap. So now let's see why we need binary tree. So a binary tree is a tree in which nodes can have at max 2 children. So let's see, this is my node. So this will be my root node. So as I told you that binary tree is a tree which will be having at max 2 children. So here these are the 2 children of this root node. So this is the left node and this is the right node. Now I told that at max 2 children, right? But we can also have 0 as well as 1. So let me create a binary tree. So this is my binary tree. You can see that this is my root node. And here, this you can say these are the internal nodes. So here this will be a parent node. Why I'm telling this as a parent node? Because this parent node is having child node. So this is the left node and this is the right node. And here it's already written here that it can have maximum 2 children. So here you can see that this is my parent node and it's having only 1 children. Even it couldn't have any children also. So you can also remove this. Let me remove this. So even this is my binary tree. So always remember a binary tree is a tree which is having at most 2 children. And even it can have children 0 as well as 1. So now after understanding what is binary tree, we are having various types of binary tree. We are having full binary tree, we are having complete binary tree, we are having perfect binary tree, balanced binary tree, as well as degenerate binary tree. Right? So let's understand each binary tree one by one. So let's start with perfect binary tree. So a perfect binary tree is a tree in which all internal nodes will be having 2 children and the leaf nodes will be on the same level. So let me write here perfect binary tree. So this is my binary tree. And here in this binary tree, you can see that this is my internal node, right? It's having 2 children. And let me write here internal node. So here you can see that this and this are the internal node which are having 2 children and the leaf node must be on the same level. So these are the leaf node. Now you might have a question, what is leaf node? So leaf node doesn't have any children. So here these are the leaf node, right? So perfect binary tree is a tree in which the internal nodes are having 2 children. So this is the internal node which is having 2 children. This is also internal node which is having 2 children. And here leaf nodes are on the same level, right? So this was the example of perfect binary tree. So after discussing the concept of perfect binary tree, now let's see what is degenerate binary tree. Now degenerate binary tree is a tree in which all the internal nodes are having only 1 children. So let me create degenerate binary tree. So as we know that this is my root node, right? So after creating my root node, now this will be my internal node. So as I told you that internal node will contain only 1 children. So here it will contain only 1 children. So this is the example of my degenerate binary tree. So let me give you data. Let's suppose here I am having data as 10, 20, 35, 46 and 78, so on. So this will be an internal node and this internal node is having only 1 child, right? Now coming to 35, so 35 will be a parent node for this 46, right? So this will be my parent node for 46. Now 46 is the parent node for 78, and here my 78 will be leaf node because it is not having any children, right? So this is the example of degenerate binary tree. So now talking about the balanced binary tree, it is a tree in which the height of the left and right subtree of any node should not differ more than 1, right? So this is the basic idea about the balanced binary tree. Now after this we are having full binary tree as well as complete binary tree. So we will discuss this in next slide. So now, as I told you that heap is a complete binary tree. So that's why we will discuss what is complete binary tree, what is full binary tree, and then we will jump to the concept of heap.
Now we are in our next topic, which is why binary tree. Why should you use binary tree when you have so many other data structures? So here we'll compare a tree with a binary tree, and we will check out few advantages of a binary tree. So let's get started. First of all, how is a binary tree different from a tree or a normal tree or a general tree? All mean the same. Alright. Now, a tree doesn't have any restriction such that it should have only one child, a two child, or three child, right? It can have any number of child nodes, but that is not in the case of a binary tree, right? Because here a binary tree can either have zero child nodes, one child node, or a maximum of two child nodes, nothing beyond two child nodes. So that is in the case of a binary tree. So this is the major difference between a tree and a binary tree, right? So why should you use a binary tree when you have so many other data structures, right? So let's try to understand few advantages of a binary tree. So here are few advantages which I have listed for you. So the first one says that the search operation becomes faster when we use a binary tree, right? So there is a variation of a binary tree which is called as binary search tree. So whenever the search operation is the most frequently used in your program, you can make use of this data structure which will help you for your search operation becoming faster, right? So that is the first one. Next, if you want to reduce the cost of the insert and delete operations in your program, you can use a binary tree as a data structure. So as compared to other linear data structures such as an array or a linked list, these two operations tend to be cost you less as compared to a linear data structures. Fine. Also, binary tree is used in various applications. So you'll come across different applications of a binary tree when you start building your applications or programs. Fine. Also, it will provide you a convenient way whenever you want to move your data in and around your program, right? Because here you are having multiple levels and you're not storing the data in a linear or sequential format. So the movement of data whenever you store and organize it is very easy when you use a binary tree. Fine. Also, whenever there is a requirement from your application such that the data has to be stored or organized in a hierarchical format, you can make use of this binary tree, right? So this will solve a lot of problems when you come across the linear data structures, right? So this non-linear data structures, which is a binary tree, will help you solve such problems easily. Fine. So I hope with this you have understood what are the advantages of a binary tree and why you should use a binary tree. Thank you. Now we are in our next topic, which is types of binary tree. So here we'll try to understand what are the different types of binary trees available for us and how do they differ from each other. So let's get started then. So the first type of binary tree which we are going to see is called as full binary tree. Okay, full binary tree. So here what happens is it's a binary tree wherein every node has either 0 or 2 children. Okay, so now look at these two pictures here. So observe, according to this statement, which out of them is a full binary tree. Okay, so let's check on the left side. So we have our root node, and root node has two child nodes, correct? And then the child of the root node, the left child, also has two child nodes, correct? So these both are satisfying the statement written over here, right? And also the left child again has a child, right? And that child also has two nodes, right? Which is again satisfying the statement over here. Okay, now let's look at this diagram over here. So we have our root node, but it has only one left child, right? But according to the statement, it should either have 0 children or 2, right? So the root node is not at all satisfying the statement written over here. Okay, then when we move forward, the child has two child nodes, right? So the left child of root node has two child nodes. Okay, that is fine. Again, the left child here has two child nodes, right? So this is satisfying the statement here. This is satisfying, but the root node doesn't have two child nodes, right? And it is not satisfying the statement written over here. So which among them is a full binary tree? Let's see. So the one on the left side is the full binary tree, which is satisfying the statement written over here. Okay, so always remember, in a full binary tree, every node has either 0 or 2 child nodes. So see here, this node over here doesn't have any children, right? So 0 children, fine. Similarly this node, and similarly these two leaf nodes. So this binary tree here is satisfying the statement over here. That is the reason you can call this binary tree as a full binary tree, wherein this tree is not satisfying the statement written over here. So this cannot be called as a full binary tree, right? So next we will see one more variation of binary tree. Let's go and check it. Now here we have something called as complete binary tree. Okay, now let's go through the statement over here. So a complete binary tree is a tree where all the levels are completely filled with the nodes except the level which is at the last. Okay, so the last level here need not be filled always. Okay, so all the nodes tend to be on the left side as much as possible. Okay, so what is a complete binary tree? It's a binary tree where all the levels are completely filled with the nodes except the last level, that is the leaf nodes. Okay, and in the last level, all the nodes always tend to be to the left side as much as possible, right? So now look at these two diagrams over here, right? And according to the statement present over there, let's check which tree among them satisfies the condition, right? So here we have our root node. We have two child nodes of the root node. And then again these have child nodes, right? But the right subtree over here, okay, does not have any child nodes to these leaf nodes, right? So the right subtree ends at this particular level, fine. So this is your level 0, this is your level 1, right? And this is your level 2. Now here at level 2, the right subtree ends, that is, it doesn't have any child nodes further. But here on the left subtree, we have two child nodes, right? And according to this statement over here, is this binary tree satisfying the conditions? Let's see that once we verify this tree over here. Okay. So now we have a root node here. Fine. The root node has two child nodes, that is the left and the right. Fine. And the left child node has one left child again, that is this. Okay. But it doesn't have any right child over here. Fine. But in the right subtree, we have left as well as right subtree, that is these two. But the most important thing which we are missing here is we don't have a right child to this particular node over here, and which is not satisfying the statement present over here. That is, all the nodes tend to be on the left side as much as possible, right? So this statement is being satisfied by the tree present over here. So among these two trees, which is a complete binary tree? So the tree on the left side is a complete binary tree because it is satisfying all the conditions present in that particular statement, right? So here, if we had a child over here, a right child over here, right, then even that could be a complete binary tree, right? Now here the most important thing is all the levels must be completely filled except the level which is at the last. Okay, that is this level over here, and then all the nodes should be left as much as possible, right? So we cannot leave something blank like this. Okay, you can't leave blank a node like this. Okay, so that will not satisfy the statement for our complete binary tree. So I hope with this you have understood complete binary tree. Next we will see one more type of tree. Okay, so the next type of tree is a perfect binary tree. So what happens over here? So it's a binary tree where all the internal nodes, okay, so these are our internal nodes over here, this, these are our internal nodes. So all the internal nodes have two child nodes and all the leaf nodes must be at the same level. Okay, so now let's check among these two diagrams which tree will satisfy the perfect binary tree statement present over here. Okay, so first let's check the tree on the right side. So we have our root node as usual. Root node has two child nodes, the left and the right, and again these two child nodes have the descendants, that is again left right childs over here. Okay, now according to the statement present over here, all the internal nodes have two child nodes. Okay, so this is satisfied here, these both have two child nodes, right? But look at the next statement, and all the leaf nodes must be at the same level. Okay, now here this is our level 0, level 1, level 2, but here we have one more level, right? So this tree is not satisfying the statement present over there because we don't have any descendants or child nodes for these leaf nodes over here, right? So which is not satisfying the statement present over there, right? So now let's look at the tree present on the left side. So here we have the root node which is having two child nodes, that is left and right, and then these left and right child nodes also have two child nodes, right, which is satisfying the statement present over here, and then all the leaf nodes must be at the same level, right? So this is our level 0, this is level 1, and this is level 2, right? So all the leaf nodes are at the same level, and this tree present on the left side is satisfying all the conditions. So the tree on the left side is a perfect binary tree, whereas the tree on the right side is not satisfying the statements present over there, so it cannot be called as a perfect binary tree. right? So I hope with this you have understood the different types of binary tree. Thank you. Now we are in our next topic, which is applications of binary trees. So here we'll try to understand where all you can use a binary tree to build an application. So let's get started then. So these are a few applications which I have listed on for you. So the first one is a binary tree can be used for classification purpose. So whenever you want to classify the elements or the items in your programs, you can make use of a binary tree because it stores or organizes the data in a hierarchical format, which will solve the problem of classifying, right? Next, there is an algorithm in machine learning which is quite popular and known as decision tree, right? So here, this binary tree will help you to take the decision for your program, right? So a decision tree is nothing but a supervised machine learning algorithm which uses a binary tree to make the decisions based on the input for your program, right? Next, we have something called as expression evaluation. Now, this is the most common application of a binary tree wherein the mathematical expressions such as your operands and operators, right? So combination of these forms an expression, right? So such applications or such problems can also be solved using the binary tree. Fine. Next, we have something called as sorting. So whenever you want the output to be in a sorted manner, you can use a variation of binary tree, which is called as a binary search tree, right? So this is a variation of this binary tree, which will help you in this sorting problems, right? Next, a binary tree is also used in many data compression applications. So data compression is nothing but you have a large chunk of data which has to be compressed in such a way that it can be easily moved or transferred on a medium, right? So in such applications also you can use a binary tree. And lastly, it is also used in routing tables. So this is related to networking wherein you have the IP addresses and other stuff. So there you want to store the information in a hierarchical format, right? So it is also used in routing tables to easily access or identify the networks, right? So I hope with this you have understood what are the applications in which a binary tree can be helpful. Thank you.
So now we will see the array representation of binary tree. So here you can see that this is my binary tree and this is array. So if I want to do the array representation of binary tree, so for doing, let me insert the element. I am writing here 10, 20, 30, 40, 50, 60, 70, right? So these are the elements of my binary tree and I want to insert into array. Then it will be inserted level by level, right? So first 10 will be inserted here, then 20, 30, 40, 50, 60 and 70. Always remember the elements will be inserted in an array level by level, right? And so after inserting the elements into array, we are having a formula. So what's the formula? Let me write here. So if I'm writing here, let's suppose this is my node and I will write here I. Let's suppose the indexing is starting from here from 1. So 1, 2, 3, 4, 5, 6, 7. These are my index values. Now here, let's suppose this is my node which is at I index position. Now if I want to find out the left node, then the formula is 2i. For right node, formula is 2i plus 1, right? And what will be the parent node? So the parent node, we are having the formula as I by 2, which is inside a floor value. Now let's see, let's take an example. Let's suppose this is my 30, right? So let me check here 30. So 30 is my at index position I is equal to 3, right? And we know that this is 30. So this is a parent node for 60 and 70, right? So 60 is the left node for 30 and whereas 70 is the right node. Now I am already having here I is equal to 3. So for left node, if I am writing here 2i, so I value is 3. So 2 into 3 is 6, right? And you can see that at index position 6, I am getting 60. So my left node is at 60, right? So this is a basic formula 2i. Now coming to the right node, I am having 2i plus 1. I value is 3. 2 into 3 will be 6. 6 plus 1 is equal to 7. So if you see here 7, at 7th position, I am having 70. So this is my right node. Now, what will be the parent node for 30? So as we know that the parent node for 30 is 10. So what's the formula here? So for parent node, it will be I by 2. And we will take the floor value. So here if you see, I is 3, right? So 3 by 2 is 1.5. And what's the floor value of 1.5? It's 1. So what is at index position 1? So here you can see that at index position 1, I am having 10, right? So 10 is the parent node for this 30. So this is basically an array representation of a binary tree, right? Now let's take an example. Let's suppose if I'm having a binary tree like this. And here if I'm having 10, here I'm having 15, 35, 78 and 89, something like that. Now as we know that the elements will be inserted level by level, right? So first 10 will be inserted here, then after 10 15 will be here, then 35, and then as you can see that here 15 doesn't have any child nodes here, so here I will give a blank, right? And then I will write here 78 and 89. So now if you are writing here 78 and 89, so what will be the answer? You will be getting the wrong answer. Now let me apply the formula here. Formula is for any node it will be I, and then for left node I will write here 2i. For right node I will write here 2i plus 1. And for the parent node, the formula will be floor of I by 2. Now let's see, let's check a node. Let's suppose this is my 35, right? So what's the position at 35? So I value is 3 here also. So if you see here I is equal to 3, then my left node is at position 6. So at position 6, I am getting here 78, right? This is correct. Similarly for right node, the formula is 2i plus 1. So I value is 3 here. So 2 into 3, 6, 6 plus 1 will be 7. So at 7th position, I am getting 89. You can see that. Now, if I want to know the left node of this and right node of this, then what will be the answer? Let's take the I value as 2, right? So now here you can see that node is equal to I is equal to 2 here. Now what will happen here? I want to calculate the child node of this. So what's the formula for the left node? It's 2i. So what is 2i? So 2i will be simple, right? I value is 2. So 2 into 2 will be 4. So at 4 position, I will check here. You can see that I am not having any element in an array. So we know that 15 doesn't have a right node as well as left node, right? So at 5th position, you can see that I am not having any element. So this formula will work for all the binary tree. But always remember, whenever we are not having a children of any node, then put it blank there. So this formula will always work. So this was the basic idea about array representation of a binary tree.
So now we are in our next topic, which is pseudocode for binary tree. So here we will see how a pseudocode can be implemented for a binary tree so that you can use that pseudocode and write code in any programming language you wish to, right? So let's get started then. So here on the left side, we have this particular pseudocode to create a tree for the first time. Okay, so you need the root node, the left child and the right child, right? When you're creating a tree or a binary tree for the first time. So look at the first statement over here. Okay, so first we want to create our root node, right? And then we want to create the left and the right child for the root node, right? So the left child and the right child has to be created for our binary tree. So that is the first and foremost important step. Only then you can insert the data or the information inside these nodes, right? So the first step is you have to create this code for creating a root node and then inserting left and right child with the values null for the first time, right? And then you are going to create the left and the right child for your binary tree. Now, once you create, the next step is you want to insert the values into these nodes, right? And how to do that? Let's see that. So on the right side, we have the pseudocode for insert function or insert method, right? So here, at first, we are going to create a temporary variable or a pointer which will point to the links in our tree, right? So first time, if temp.left equals to null. So that is, we are checking if this particular left node is equal to null or not. If it is equal, then we are going to insert the value or the data over the left side. So how to do that? Simple. Look at this statement. Temp.left is equal to node new. And we are passing the argument data here. Now, once you do that, if you want to insert the next data on the right side, what you have to do is if temp.right double equals null. You're going to check if the right side child has any value or not. If it is null, then you can insert the value in the right child of this binary tree as well, right? So this function or this particular line of code or the pseudocode will help you create the tree, the left and the right child with the null values for the first time. And next, when you continue with this method here, the pseudocode, you can insert the values inside your tree by checking if no null value is present, right? So if it is null, you can easily insert the values over there. Next, we will also see one more pseudocode that is for delete. So here, if you want to delete the nodes from your tree, so first we are going to delete all the left nodes and then we are going to delete all the nodes present on the right, and then finally we are going to delete the parent or the root node, right? So this is how you are going to implement your delete function or delete method. So we are going to check if b3, that is the argument which are going to pass here to this method delete, then we are going to recursively delete all the nodes present on the left side of our binary tree. Okay. Then we are going to delete all the nodes present on the right side of our tree recursively. Okay, so you can implement it in any way, recursive or iterative way, but an easy method would be the recursive method. And then finally, we are going to free all the nodes from our binary tree, right? And next, we can also check the time complexity for these. So it is good to know the time complexity for these methods in our binary tree. So assume we have a tree, something like this. So I have the value 9 over here. I have the value 1 and then I have a value 7 over here. Okay. Now, if you want to delete a node from this particular tree, suppose if you want to delete the node 7, okay, so you have to traverse all the way and search for this value 7 in your binary tree, right? So in the worst case, the complexity will be O of n here for delete method, right? Similarly, if you want to insert any value, okay, so assume if you wanted to insert 7, okay, or if you want to insert a new value or as a left child of the 7, so let me take 8. So in the worst case scenario, this will also take O of n as the worst case complexity when you want to insert a new node in a binary tree, right? So in this way, it is always good to know the time complexity of the methods you are going to implement, right? So I hope with this you have understood the simple pseudo codes with which you can implement the actual code for your binary tree implementation, right? Thank you.
So now let's understand what is complete binary tree. So here you can see the formal definition that all nodes must be completely filled, and at last level nodes should be added at left first. So now this is the formal definition. Let's understand with the array representation here. So let's suppose if I'm having here the elements as 10, 20, 30, 40, 50, and then 60. So total I'm having 1, 2, 3, 4, 5, 6. Total I'm having 6 elements, right? So let me insert here 10, 20, 30, 40, 50, 60. Now this is the array representation of a binary tree. So the insertion of this element will be done in array level by level. So first 10 will be inserted, then 20 and 30, then 40, 50 and 60. So basically we are inserting from left to right. So first 10 will be inserted, then 20, 30, 40, 50, 60. So this is the array representation of binary tree. Now coming to the next point, my question is, what is complete binary tree? How will you get to know whether this is a complete binary tree or not? So if you see, this is the array representation. Let me write here the index. So I'm starting indexing, let's suppose from 1, 2, 3. This is 4, 5, 6. And here I'm having a formula, right? Let's suppose node is at I. So my left node will be at 2i. Then right node will be at 2i plus 1, right? Let's take an example. So when I value is equal to 3, then I'm having a 30 here, right? So if I'm writing here 2i, so I value is 3, right? So 2 into 3, 6. So you can see that at index position 6, my value is 60. So that means the left node that I'm having of this 30 is having a value of 60. So this is basically a formula from which you can calculate the left node, right node, as well as you can also calculate the parent node. So the parent node will be floor value of I by 2. So my question is that I just want to know that whether this binary tree is a complete binary tree or not. So let's understand. If I'm removing this 2, then you can see that at position 4 and 5, there will be no child nodes of this 20, right? So now I will give you the basic definition. So a complete binary tree is a tree in which there is no missing nodes in between. So here if you're going, then 10 is having 20 and 30, 2 nodes, right? And if you see here 20, here nodes are missing, right? These are the missing nodes. So this is not a complete binary tree. Let's take some more example of complete binary tree. If I ask you, is this a complete binary tree? What you will tell? Yeah, it's a complete binary tree because nodes are not missing in between. If I ask you, is this a complete binary tree? Yeah, even this is a complete binary tree because nodes are not missing in between. Let's take an example. Is this a complete binary tree? No, it's not a complete binary tree because nodes are missing in between. Now you might have a doubt why this is a binary tree. I told you that there should not be any missing node in between, right? Here after this I am not having a node, that's fine, but in between there should be any node. So this is the basic idea of a complete binary tree. So the next question that arises in mind, can the complete binary tree can become a full binary tree? Yeah, why not? This is a full binary tree. So here you can see that this node is having 2 nodes, even this node is having 2 nodes, this node is also having 2 nodes, but these are the leaf nodes. So except leaf nodes, all the nodes must have 2 child nodes. Now coming to the complete binary tree, my definition was that there shouldn't be any missing node in between, right? So if I'm creating a node like this, then this is also a complete binary tree. So a complete binary tree can be a full binary tree, right? So this was the idea about complete binary tree. Now let's take some more example of complete binary tree. So if I ask you, is this a complete binary tree? So what will be your answer? Yes, this is a complete binary tree because I don't have any missing nodes in between. What about this? Again, this is a complete binary tree, right? But if I'm writing like this, let's suppose. So is this a complete binary tree? Yeah, it's a complete binary tree. So this was all about complete binary tree.
So after knowing what is binary tree in theoretical part, let's quickly implement the binary tree in practicality on Google Colab in Python. So before doing that process, so let's learn what are the different functions we are going to perform in a binary tree concept. It's generally by default, everyone will start learning with in-order traversal, pre-order traversal, and post-order traversal. So I'll quickly brief you what is in-order, pre-order, and post-order, and then we shall go to implementation part, right? So let me give you a brief explanation over this. First, we'll start with what is binary tree, right? I'm taking a simple example, nothing related to coding or anything, just a simple example. So binary tree in the sense, it should have at least one node and two different subnodes. I call it as left and right sides, right? It should have one data item. I'm putting it to one here, and it should also have left child and it should have the right child. So again, I'm trying to put 2 here, I'm putting 3 here, and extending with 4. So we'll be working and understanding with this simple example how does binary tree will work. So the first thing you have to know, I'm talking about in order. So what is in order here? There is a simple basic rule which you can remember. When you traverse throughout the nodes which you have in a binary tree, you have to start from the left, visit root, and then right. So I'm writing it here for you. So left first, root next, and then the right node, right side node. Okay. Then we have the next one, pre-order. How does this pre-order will work? It has the same rule, but in a shuffled manner. First you are visiting the root, then you are visiting left side of the tree, and then you are going towards the right side. Hope that's clear, right? And the last one which is left is post order. So what is post order? Again, you have a shuffled way of this three combination only. The first thing is it will go to left, that means left side of the particular diagram or the binary tree which you have taken, and then it will go to the right. After that, it will go to root. So this is the basic things you have to know on these three functions or operations which you do it generally in binary tree. So in order, pre-order, and post order. So let's quickly start with in order, right? So in order, it says we have to visit to the left first, then go towards the root, and then come back to right. So I'm implementing the same. So here, what is the leftmost node we have for this particular example? Simple example we have taken. So that is 4, if you could see, right? So this is the leftmost, and this is the rightmost, and this is the root, just for reference, right? So at the left, what do you have? 4. So for in order, I'm writing it here as well. So in order, you will put up 4 as the first element because the rule says you have to go towards the left of the binary tree. Then after 4, what do you have? This direction. You have 2. You have to first complete the left side part, then you have to go to the root. And next, on the way, what do you find? You find root. So what is the number in the root? Is 1. And then after coming back towards right side, so what is the number we have? We have 3. So this is how in order will work. So hope that's clear. We are starting from left, we are going towards the root, and we are coming back towards the right side. So again, how do you do it for pre-order? The next one. So what does pre-order say? You have to first visit root, then go to the left, and then go to right. So I'm going to root here in the same diagram. I'm drawing one more here for your reference. So this is 2, again this will be 4, and this is 3. Hope that's clear. So we are working for pre-order here. It says we have to go for root first. So what is the element in the node? That is 1. Okay. So next it says you have to go towards the left. So what is there in the left? This side you have 2 first and then 4. So what I'm writing, it's 2 here and 4 next. Then you have to visit right side. So at right side you have 3. So this is how pre-order traversal will work in binary tree. So quickly we shall see the last one, that is post order. Right. Post order, as per the rules, what does it say? We have to go towards the left first, then right, and then root at the last. So writing down a simple diagram again here for avoiding the confusion. For this is 3. Okay. So we are doing that. Left side, what do you have now? We have 4. Again, continuing, you have towards the right side 3. Right. After having 3, what do you have? You have to go to root. So what does it say? You have to first complete whatever there in the left. So what we have left out here? We have left the 2 because it is also on the left side. So what we'll do here, right? We'll try to put up this 2 here, finish it off. That is 4, 2, 3, and then you have to go to 1. So first what did I do? I went to the left part, that is 4. So after that, you have 2, and then you have to go to right and then root. So this is the root. We can't go there until unless we finish towards the right side. Towards the right side we had 3, and then we went to root back. So that makes 4, 2, 3, 1 as a post order. Hope this was clear for you. And now let's quickly hop into the coding part and check out the same elements, the same functions. How does that work? So what is happening here is the same example I've taken in a coding format. That is where I'm taking the 4 different nodes, that is 1, 2, 3, 4, and applying all the 3 functions we have. That is in order, post order, and pre-order with the same way of working but in a coding manner. So what has happened here? The first, if you could see, they have put up a class that is node, right? So after creating a class node, we have to initialize the values. Value is VAL is nothing but root, right, and left. So we have to have one single root node, and we have to have left and right for the same root. So then we'll create some functions for traversing towards pre-order, traversal towards in order, traversal towards post order. To make it clear and precise enough, I have kept related name to the functions and classes here. So what happens here is we'll be using the functions called pre-order, post-order, and in-order. So first it will visit the nodes accordingly as I told you. So first for pre-order it will go to root, left, right, and for in-order it will go for left, root, right, and again for post-order it will go for left, right, and root. So let's check out how does this program work in the manner. So here you could see I've used the left and right accordingly. So as per the rules I have told you, that has been used here as well. So let me quickly run the program for you and check out what is the output we get. Right, if you could see here, pre-order, we got it as 1, 2, 4, 3. The reason is because it is going from root, left, and right. And for in order, we are going with left, root, and right. So left side we had 4, 2, and again 1 was the root node and 3 was at the right. So left, root, and right. If you go for post order traversal, then it will start from left, right, and root. So leftmost was 4, 2, and it went to right. Right side was 3, and root is 1. So this is how the traversal will work in binary tree in Python.
Now let's talk about advantages and disadvantages of binary tree. If you talk about advantages, we can represent data with some relationship, right? So this is the root node, or this is the parent node, and this is the child node. So that relationship, parent-child relationship is always there. And while you are inserting or searching an element or a node in a binary tree, it is much more efficient as compared to other data structures which we have seen. Now, if you talk about disadvantages, if you want to sort this binary tree, it is much more difficult, right? Because we can either go on the left side. This can be a tree, that means this is a left skew tree, or this can be the scenario wherein we have all the elements on the right side of the node. So this can be another scenario wherein we have this right skewed binary tree. So sorting is difficult and it is not much flexible, right? If you talk about this binary tree, we always have either the two children or one children or no children. There is no flexibility in terms of how you want to store it. Can we store another node on the with this root node? No, that is not the case, right? And we don't follow any restrictions like, okay, we always find this node, that is, if this is in root node, we always find an element which is less than this node on the left side or on the right side, that is of the greater element. So that flexibility is not there.
Now let's see the graph data structure. So first I'll talk about what are graphs, and then we'll talk about its implementation using two different applications of graph, that is breadth first search and depth first search. So what is graphs first? So graph is actually a concept which has been derived from the field of mathematics to computer science. Okay, and graph is used here as a data structure. Here meaning in the concept of computers and programming and computer science. In this field, graph is used as a data structure. That is, it is used to store a data, represent a data in a different way. Okay, a graph consists of vertices and edges. Vertices are also called as nodes in computer science terms, but graph is basically the combination of vertex and edges. Edges connect two vertices. That is, a edge is always drawn between the two given vertex. There are different types of graphs on the basis of the different properties of vertices and edges and different properties of the graph altogether as well. But let me tell you, before going to the types of graphs, let us talk what is the different use of graph data structure in computer science. So if I talk about the application of graphs in computer science, I'll give you a very simple example. I ask you a question that, represent whoever is your friends in, like, suppose in your area or in your colony, and tell me in a pictorial way that who is a friend of whom and who is not a friend of whom, and how is that complete friendship structure in your colony or in your lane where you live. What will you do? You'll start drawing something of this type, like maybe, this is one person A, this person A is friend with person B, B is a friend with person C, and D is a person who is only friend with B. So this is how you'll represent. So this is nothing but what? A graph, where these are called as your vertices or vertex, and this is called as your edge, the line drawn between the two vertices. This is telling what exactly? The relationship between the two vertex, that is B and D. This, what kind of relationship in this example is it representing? That is the friendship relationship. So B and D are friends in the example of what right now I discussed. So in general terms also, edge between the two vertex tells some kind of a relationship between the two vertices. Okay. Another example I would give you, like suppose I ask you to, there are five different cities, suppose Delhi, Mumbai, Bangalore, Kolkata, Patna. And all these five cities, you have to travel from one place to the other. And I ask you what are the different routes I can take to travel between these cities. So what you'll do, you'll first represent these two cities like this, suppose A, B, C, D, E. These are the five cities. And so, okay, you can go to B, you can go to E, and then you can go from here E to B. To go from A directly, there is a place to go. Then to go from D, you can go either directly to E or you can go directly to B. Getting it? To go to A, you have to go to C first, and then you can go to A. So this is the representation. This is nothing but a graph. Okay, so we have seen two different applications, real life example applications where a graph is used in computer science. And I hope what is graph is clear to you as of now or till now. Now let me tell you what are the different types of graphs. Although there are multiple types of graphs if I consider the field of mathematics, but I'll discuss few here which is relevant and important in the field of computer science. So first one is your directed and undirected graph, which is important for you to know. So directed and undirected graph. Okay, directed graph meaning, suppose these are the vertices. There will be a edge between these. Okay, as it is a graph, there has to be edge between these vertices. Directed meaning there will be a arrow marked here. There will be a direction specified. Meaning, if there is these four vertices, B is having a directed edge from B to A. Meaning there is a relationship from B to A, but the relationship whichever is between these two vertices does not exist when it is talking about A to B. It is only for B to A. Okay, so this is your directed graph where there will be some kind of direction mentioned on the edges using a arrow mark. Okay, undirected graph where there is no direction mentioned. Okay, suppose this is the three vertex and this is your graph. So there isn't any direction mentioned here. This is your undirected graph, meaning the relationship which exists between B to C is also between C to B. Right? Now there is another group of graphs called as connected and disconnected graph. What is connected and disconnected graph? Suppose all the vertices, these are the four vertices, okay, in a graph. All these four vertices are at least connected to any one of the different vertex. Any one of the other vertex, if it is connected, then it is a connected graph. Disconnected, that out of a complete graph, suppose this is your complete graph, A, B, C, and D, and these two are connected, but D is not connected to any other vertex. It's also called as your isolated vertex. So if there exists any isolated vertex in a graph, that is your disconnected graph. Or there is no link between any two vertex of a graph, that is two different graphs exist. For example, suppose there is one more edge here, one more vertex here, and this is connected. Now this complete together is one graph, okay, graph G1. But this is a disconnected graph because there is no connection between this part of a graph and this part of a graph. There are these two different set of vertices where there is no connection between them. So you can divide if the complete graph into two different group of vertices where there is no edge connecting between any of the two vertices of those groups, then it is your disconnected graph. Clear? Or if there is an isolated vertex in any graph, then that is also a disconnected graph. So these are the basic classifications of a given graph. Now coming to the another concept of agency matrix or agency list. This concept is important here because when it comes to programming, agency matrix or agency list is what we use to represent graph programmatically. Okay, now what is agency matrix and what is agency list? Let's see that. So first I'll tell you what is agency matrix. Adjacency matrix is nothing but it will tell you that which two vertices are connected in a given graph. So this kind of a matrix, it is two-dimensional. There will be rows and there will be columns. And this represents, suppose, A, B, C, D, E, and F. Okay. Similarly, on the row side also, A, B, C, D, E, and F. Now, see, there is no self loops here. Self loop meaning if there is an edge from the vertex to the same vertex. So there is no self loop over here. So there is no self loop meaning there is no path to go from A to A. To go to A itself, there should be something like that. But there is nothing of this sort, right? So to go from A to A, there will be no path. So we'll mark it as 0. To go from B to B also no path, mark it 0. To go from C to C, similarly all this diagonal part will become 0. Now let's see from A where all you can go. You can go to B directly where you can go. Like, okay, indirectly after going to C, you can go to D also, but directly I'm talking. So from A directly you can go to B, directly to C and directly to F, only three of these, right? So B, C and F. So B, C and F will have the value as 1. Rest values will be 0. Okay. From B where all you can go either to A or to C. So A or C, rest other values will be 0. From C where all you can go. You can go to every place like A, B, D and E directly, not indirectly. Indirectly you can go to F also, but directly there is no edge between C and F. So you can't go to F. So F will be alone 0. Rest everywhere we can traverse from C. Coming to D. From D you can go directly only to C. Rest all other places direct edge is not there between D and other edges. So D2 C is only will be 1, rest all will be 0. Similarly, from E you can go only to F and C. So F and C value will be 1, rest all will be 0. From F where you can go either A or E. So A and E will be 1, rest all values will be 0. So this is your adjacency matrix. Now adjacency list, how is to create that? And that's what I'm going to use in programming also right now when we'll write a code for the different applications of graphs in Java. So there we'll be using adjacency list itself. Now what is that? So it is created in this way. So all the vertices will be marked A, B, C, D, E and F. Okay. This is column representation. And in the row, like this will contain a list alone. This will contain another list. This will consist of another list. This will consist of another list. This will also consist of another list. This will also consist of another list. This itself is also one list. Okay. And each of it is pointing to another list. Programmatically, I'm talking about. Okay. To represent it, this is column and these are the values in those columns. Now, what are the values here in this list? So whichever vertices we can reach from A directly, those will be contained in this list. So from A we can reach to B, C and F, right? So A will contain B, C and F. From B where all you can go? A and C. So it will be A and C. From C where we can go? A, B, D and E. So A, B, D and E. From D we can go to C only. So only C. From E where we can go to F and C. C and F. From F where we can go? We can go to either A and E directly, meaning there's a direct edge connecting between F and A, F and E. So A and E. So this is your adjacency list. Okay, that is from one given vertex, which all are the other vertices we can go. So this comprises of one list. So this is your adjacency list and this is your adjacency matrix. Now let us discuss the implementation of breadth first search algorithm. But before implementing it or writing down the code in Java, let us see what is exactly this breadth first search algorithm or how it works. So it is one of the application of graphs in which we are going to traverse the nodes of a graph in a certain order. Okay, so as the name itself says, breadth first search, that is along the breadth of a graph, along the horizontal level of a graph, we are going to search the nodes one by one in each level. So BFS is your, or breadth first search is your algorithm to trace the nodes of a graph in a breadth first order. Okay, that is in a single level. First all the nodes will be traversed, then we'll go to the next level and then next level. Now you must be wondering whether how is the levels defined in a graph, because graph is not like a tree that you can define levels, right? So yeah, I'll tell you, if you try to visualize it like closely, you will be able to figure out that there are levels in the graph as well. So let us talk about this example itself, which is there right now here, the screen you can see. So in this, if I talk about the levels, can I consider this to be one level? This to be the another level if I talk in this order, and then this will be another level and this will be another level. Yeah. Or if I talk in this order, we can talk that this is these two A and B belongs to the same level, then F and C belongs to one level, then E and D belongs to one level. Isn't it? So you can see here that the levels, if you closely observe a graph, you can find there are different levels as well. Now, to implement breadth first search algorithm, the concept used is of queue data structure. Okay. Why I'm saying queue data structure? Before implementation, let's see how it works actually. So in that, we'll start from any one vertex. Suppose A is the source vertex to start with. So we'll start from here and go on searching along the breadth of the graph one by one. So let this be a queue. Okay. The very first vertex which you will refer or visit, that is your source vertex. So once you visit this, we have to insert that into a queue. Okay. Now there will be one more, maybe a array which will be maintained, and let that array be called as your visited array. And this will have how many indexes or how many fields to store. equal to the number of vertices. So 1, 2, 3, 4, 5, 6 vertices are there. So 0, 1, 2, 3, 4 and 5. So 6 is there. 0 to 5 is 6. So 6 nodes will be there. Whenever you will visit or traverse any given node, that will be marked here as a true. Initially, all will be false. Okay. If the particular vertex is visited, that will be marked as true. So A is inserted first and it is visited first. Right? So A is visited first. Okay, this 0 represents maybe A. This represents B, C, D, E, and F. Okay. We can have these numberings also like 0, 1, 2, 3. That will be more no, connected, I guess, or you can relate it in this way also. So this will be marked as true. Okay, it means A is visited. Now, Q follows FIFO order, that is first in, first out. So now you have to do is remove the very first element of a queue. So remove the first element, which is the first element right now, A. So A will be removed from the queue. Okay. Now, so what will be inserted? Once you remove any given vertex, we have to insert all those vertices which are in the adjacency list of A. That is, which all are connected to A. So connected to A is F, C and B directly connected. That's what is in the adjacency list, right? So F, C and B. So we will insert here F, C and then B, right? And in this FCB is inserted. Now next, again we will perform the same operation. We'll remove or delete the very first element of the queue. Right now the first element is F because A is already deleted. So F will be deleted. And as F is visited, so it will be marked over here. And in this also, F will be marked as true because now it is traversed or visited. Which are the other nodes which are connected to F now? E and A, right? A is already traversed because this is made as true. So we'll not go with A. But connected to F is the E also. So we'll insert E again. Insertion is always from this end of a queue and deletion is always from this end of a queue, right? Okay. Next, again, same process. We'll remove the topmost element. Whichever are connected to that, we'll insert it into the queue. So C is the topmost element right now. So C will be deleted. And here the C will be marked as visited. That is true. And here also this will be your traversal list. So C will be marked here as well. And which are connected to C? A, B, D and E. So you can see A is already visited. So we'll not consider A. So E and B is also already in this queue. So that also we should not insert again. Only left is D. So D will be inserted here. Fine. Next to be visited is B. Right. So B will be deleted from here. B is the next visited and B will be marked as true over here. Right. Now, which are connected to B? C and A. And already A is visited, C is also visited. So nothing is there to insert right now. Now again we'll remove the topmost element. Topmost element right now is E. So we'll remove E and E will be visited now and this will be changed to true. And as connected to E, the vertices are C and F both are already visited because it has been converted here as a true. So we will not perform any insertion for C and F. Okay. Now next is the element to be removed is D. That's the only element left. So D will be visited now and this will be changed to true. And as now the queue is empty, will not perform this operation anymore on the graph. Okay, so this is the sequence which we get A, F, C, B, E and D in the breadth first search. Let's see, is it following any level by level searching? So you see first it searches A. Okay, A is this. Next it searches F, C and B. So F, C and B. Then it searches E and D. Now observe it closely. The first level comes as A, then the next level is B, C and F, then the next level is D and E. So this is your breadth first search where level wise, horizontal level wise searching is done for any given key. Okay. And this is the order we obtain. I hope the concept is clear. Now let us see the implementation of this in Java. And for that we'll come to the IDE now and try to write the code. So yeah, here I'm using Eclipse IDE and I've already created a class here that is graph search. This is the file. which is having a main method as well, public static void main. In this itself, I'm going to write down the code for a breadth first search, that is BFS algorithm. Logic is clear to you, so I'll go directly to the implementation. So first, what we have to do is, here we should have, so guys, how many things are required here? One is vertices, next is edges, or edges also I won't consider. The input will be vertex, that is how many vertices are there, and then the adjacency list. So we'll create an adjacency list that will tell us that related to, like for a given vertex, which all vertices are directly related. So these two will be our input, and our output will be the order in which the breadth first search is performed. So let's write the program. So what we need first is number of vertices. Let that be denoted as V, or we can use number of vertices also as to denote. Anything is fine here. After that, we'll go here. Now, in this, I'm going to use a data structure which is already predefined in the collection framework of Java, and that is your array list. Okay, array list helps us to store or create an array dynamically. Like it grows and shrinks as the size increases and decreases. Like if you delete element, the size will decrease. So dynamically the storage, the space allocation is done. So it is more effective. Space complexity will be less. That's the reason I'm using this. You can use any other linked list or array or to implement as well. So array list, this will be of type integer. Then let it have a name, that is maybe adjacency list. So let it be adjacency. Sorry. Okay. You have to import this actually. In the java.util.star you can import, or java.util.arraylist will be have to be imported to use array list in the program. Now, let me have the constructor for this class, graph search, because this constructor, using this constructor, we are going to initialize this adjacency list as well as the number of vertices and all those parameters. So I'm going to create graph search. Input to this will be number of vertices, number of vertex. Okay. So it will be initialized. So we'll initialize first v itself with number of vertex. Okay. Now we will also initialize this adjacency list which we created. Fine. So adjacency, this is equal to new array list. As we know that new keyword is used for allocating space to any object, and then this will be number of vertex. Okay, so adjacency list will have number of vertex as a column. The spelling correct, let's check once. Edges. Okay, let's have a small naming convention. So let it be ADJ itself. Okay, it will be easy to spell out. So yeah. Now the adjacency list is in the allocated space, and the size and all is declared. Now let's have the elements for it. So we'll need a for loop for this. For I is equal to 0, it will go till I less than number of vertices, number of vertex, and I plus plus. And in this we will allocate, okay, let it be ADJ itself, then I, this will be equal to new of array list. If you remember, I have told you that array adjacency list in itself is a list again. So there's one list which will have all the vertices, and then every element there is another list which consists of the list of those vertices which are directly related to that particular vertex. So that's why it's a array list over here. Fine. So these are the initializations which we have to do under this constructor graph search. So as this is done now, we'll come out of this. And now we have to insert those elements which are the part of adjacency list. Right? This is what I have created or initialized the adjacency list. Now let us actually insert. So for that we need a method. So void, let it be edge. So I'm going to add those. Why I'm giving edge here? Because between two vertex, there is an edge, right? So that edge defines that there is a relation between these two vertices. That's why the function name I've given edge. You can give anything else as well over here. It will have two vertices, int x and int y. I'm taking integer vertices, not ABCD. It will be 0, 1, 2, 3, 4 as a numbering. It is easy to work with. That's the reason. You can have character numberings as well. And then this will be adj of x dot add y. So add is a function, inbuilt function, which I'm using here, that is defined inside this ArrayList class, and which will help to add the elements, add those vertices which are related to the vertex x. Okay, so this is your function for adding edges, or you can say creating adjacency list. Now let's have a function for breadth first search. Breadth first search. Okay. This will take input as the source vertex. The first vertex you have to give as a input to this function. So let it be source vertex. So in this, now the logic will be that we have to take that vertex, insert it into a queue or any list data structure. Okay, you can use queue, array list, arrays, anything. And there should be one visited array also, which will keep mark that which all nodes are already visited, so that we should not revisit them. Right? So let's have that written over here. So first I will create that visited vertex. It should be of Boolean type because true and false is the value we have to store here. The size will be again equal to number of vertex. Right? Or okay, we can give here as v. Both should work fine. Okay, yeah, I have missed the square brackets. Fine. Now, once this is created, we'll have another list. So I'm not using queue here. I'm using list itself. You can use queue data structure as well, which will be of type integer itself. Let it be named as A1. Short names I'm going to use now. So array list again. And in this, we'll have of type integer. So these two requirements are over. Now, what we have to do is, first you have to mark the visited for the source vertex as true. Because initially, by default, it is false. So first thing I'll do is visited for source vertex to be marked as true. Okay. Now next will be, we have to add the source vertex to this list A1. Add source vertex. This is what we have done, right? Even in the logic, this was there. Now, until the complete queue became empty. So here I'm using list. So until the complete list becomes empty, you have to keep doing this task, deleting the topmost one and inserting the values which are, the vertices which are related to it. We'll keep on doing this until and unless the complete list is empty, the complete queue is empty. So here it is list. So while, we'll be using while loop for putting that condition. While let's have not even dot till when there is an element. So is empty is an inbuilt function which I'm going to use here to say that we have to perform this operation till there is some elements in the list. So is empty will tell you true or false. Is it empty or not? So until unless it's not empty, you have to keep doing this. When it's empty, it will come out of the loop. So what we have to do is source vertex will be removed. So I mean, not source vertex will be removed. We'll remove the topmost element, that is the 0th index every time, and that will be stored. That becomes our new source vertex. And so again, the whole process will be repeated. That is first thing. And then we have to also print this. So we'll be printing source vertex. Let's have little formatting here. I'll do here print itself. After printing it, now we have to iterate over it to check that is there some more elements or not, right? Or we have to iterate over even the adjacency list to find out which are the other vertices related to this. So we need a iterator for that. And so I'm going to use the concept of iterator over here. Iterator I maybe is equal to adj source vertex every time will be made iterable dot iterator method will be called. So it is made iterable. Then we have to import this. That's the reason it's showing error here. So yeah. Now we'll have again to iterate over what we need is while loop, right? And has next method. So while I dot has next, yeah, till when there is more elements into it, what we should do, int n is equal to I dot next. Okay, we have to convert it to this integer here. Now we have to also check that if the particular vertex is already visited, that is, we have to check that visited array. If it is already marked as true, then we should not revisit that. That condition I'm going to write now. If not equal to visited for that particular n, then we should, if it is not visited, then in the visited of n, we should mark it as true, else it will remain false. Okay, and then add that to the list. That is a1 dot add that particular node to the a1 list. That is the array list, right? So this is what the logic was earlier as well. We have seen. So this is the complete program for breadth first search. Okay. Now let us come to the main method and just write up for calling this. So in the main method, we are going to just create an object for the class. Now what is that class? Graph search itself. So yeah, graph search. Maybe G1 is equal to new graph search. And there was a constructor right over here. If you could see, where is it here? Where you have to pass number of vertices. So let's have some graph which is having 6 vertices. And then we'll be calling all the method. We'll have first adjacency list, guys, right? So edge will call and we'll define the edges now. Okay. So let us take one example of the same graph we'll take which was there in our slide. So let's go to the slide. So yeah, this was the slide, right? This was the graph in the example here. So in this, the adjacency list will be, if I mark this as integers, because integer is what we are taking. So 0, 1, 2, 3, 4, and 5. Okay. So adjacency list will be 0 and 1. We have to insert this edge. 0 is connected to 1, 0 is connected to 2, and 0 is connected to 5. So let's insert this 0, 2, 0, 1, 0, 2, 0, 5. 0, 1, 0, 2, 0, 5. Okay. So similarly, I'll first write this Then we'll insert the values. G1 dot again edge, then again edge, G1 dot edge, then again G1 dot edge, and again G1 dot edge. Okay, now let's see. We'll go back to the graph again. Next is your from one vertex, which all are connected, 0 is connected, and then from 1, 2 is connected. Right? So 1, 0 and 1, 2. Then similarly from 2, which all are connected, all of these except 5. Right? So 2, 1, 2, 0, 2, 4, 2, 3, and that's it. 5 is not directly connected. Then from 3, only 2 is connected. From 4, 5 and 2 is connected. So similarly, we'll insert all the pairs. Let's see. So we'll go back here. So 0, 1, 0, 2 is done. Then there was 1. 1 was connected to only 2 of them, that is 0 and 2. Right? Now next, 2 was connected to all the others except 5. So we'll insert that. 2, 0, 2, 1, 2, 3, 2, 4. It's not connected to 5. Now 3 was connected to 2 and that's it, I guess. 3 was connected to only 1. Then we'll have again some few more edges. Okay, and one more, I guess. Okay, so let's have 4 now. So 4 was connected to 2 of them, 4, 2 and 4, 5. Lastly, 5. So 5 was connected to 0 and 5 was also connected to edge. 5 was connected also to 4. So this was the graph. So this is how you will insert all the edges. Okay, so this will prepare the adjacency list. Now after once this is done, we have to call the breadth first search algorithm. So breadth first search, you have to pass the source. So let the source vertex be 0 itself. So it'll start from 0. Okay, and we'll now execute this and see what's the output. So the output is 0, 1, 2, 3, 4, 5. Yeah, so let's see what should be the exact output. 0, 1, 2, 3, 4, 5. So the output is 4, 5. Okay, so the output here is first 0, then 1, 2, 3, and then 4 and 5. So the output is wrong actually. The output should be somewhat similar to this, right? Level by level it should traverse. Okay, so let's check what went wrong that we are not getting the correct output. So if we traverse over the function, it was right. Let's just check once the calling part. So have we entered all the edges or not? So 0, 1, 0, 2. Let's go to the our graph. So 0, 1, 0, 2. Okay, 0, 5 is also there. Have we entered that? No, right? So let's see that thing that was the issue. So 0 and 5 will be entered. Let's execute this and check if there is something else. So now we got a different output, that is 0, 1, 2, 5, 3, 4. Okay, 0, 1, 2, 5, 3, 4. Let's see if this is a correct output. 0, 1, 2, 5, 3, 4. So yes, you can see here that 0 was visited first. This was the first level. Second level was this. Now in the second level, the order can be anything. This level, either there can be 1, 2, 5 you can visit, or 5, 2, 1, or 2, 5, 1, 2, 1, 5. All is correct answer because it just has to traverse level by level. So this is first level. So next was this the output. Then 4 and 3 was the output. So our output is correct now, right? So 0, 1, 2, 5, 3, 4. So this is the implementation of your breadth first search. So let's revisit the code once. So what we did was had a class named as graph search, where the constructor of it was used to initialize the number of vertices and also the adjacency list. And we are using the concept of array list here, which is a dynamic array, which is the concept of a dynamic array actually. And using the for loop here, we have initialized it to so the number of vertices becomes the size of the array list. Then the adjacency list is created, and that is done using this function edge. That is, you have to insert the edges which are directly connected between two vertices, which will be added to this adjacency list. Then the breadth first search algorithm itself, this function method itself, which will take input as a source vertex, and from this source vertex, it will traverse down alongside the breadth of the graph. Okay, so for that we need a visited uh, Boolean array, which will keep track of which node is visited, which is not, and one array list, which will keep track of which all vertices are being visited one by one, or which will help us in implementing the whole concept of breadth first search. And there is only one condition check, that till we are completely emptying it out the elements of the list or a queue, till then we should keep repeating the process of deleting the topmost one and then inserting all those nodes which are related to or directly connected to that particular vertex or node. And that's what is done. Then lastly, we need one more condition check with the help of while loop. That is, until unless there is the node is visited, we should not, if the node is visited, then we should not enter it into the list again to revisit it. So no revisiting should be there. That's the reason this while loop is needed. And that's it. In the main method, we'll just create an object of the particular class, and then call the edge function, edge method, to create the adjacency list. And then lastly, call the breadth first search method. So that's all about the implementation of breadth first search algorithm. Now let's see the implementation of another application of a graph, that is depth first search algorithm. So what is depth first search algorithm? First, let's try to understand that. Okay, what is the data structures that are used here to implement? Although graph itself is a data structure, but implementation of these concepts of the graph will take some other data structures that are there in the collection framework of Java while implementing it. So let's see how it is, it works and how is it implemented. So let's see the concept first. So what is depth first search algorithm? So depth first search is a searching methodology that scans through a graph depth-wise. Like vertically, first it scans all the nodes in a single depth, and then it backtraces to the previous one, the first vertex, and then it again traverses through the depth of the second line, and then again it backtracks itself, then again the next depth is traversed. So depth by depth, or in a vertical line, you can say the searching methodology continues. That is, the nodes are traversed in a depth first order. Now, what is the exactly meaning of this depth first order? Let's try to see with the help of this example here and understand. So A, B, C, D, E, and F, this is the graph. Okay. When I say depth first, so suppose this starts from here. Okay. This is your source vertex. I'll tell you the data structure which is used to implement this, and that is your stack. Okay. So we need a stack here to implement this. And then there will be again a Boolean, you can say array, which will store true or false. Initially, all the values will be false, starting from A, B, C, D, E, and F. So all the values will be false. Once we visit that particular vertex, we'll make it as true. Now, this is your how the depth first search algorithm works. That will be explained with the help of these two data structures. But first, logically, what it is like. Okay. So depth first meaning, suppose I start from the source vertex. Okay. And I go to, so three vertices are connected to it. I can go to any depth first. I can go to F, I can go to C or B, any one. Suppose I go to F first. So I'll visit this first. Then F to F, what is connected? E is connected, A is connected. A already visited, so we'll not go back. We'll go to E now. So E is connected to C and A, B and D. So we'll go to C. Now C is connected to B and D both. So suppose I go to D now. So that's it. It ends here. Now D is no more connected further anywhere. Now it will backtrack itself till A, and then it will go to the next depth. That is, it will go to, so C it is already traversed, so it won't go to C. So it will go to B. That is your next depth. So this is one depth. One line vertically down till the end of the graph, and then backtracking it to the first vertex, and then again going to the next depth. So this is what depth first search is about. If suppose I would have gone to B first, then it would have gone to this depth first till wherever it goes till the end. And then it will backtrack itself to the source vertex until then it will go to the next one. Got it? Now it's easy to understand like this when a graph is in front of you, but we have to write a program for it, right? So to write a code for it, you need to understand it in a different way. And that is, we'll be using stack over here. So what we do is that we pick up the source vertex first and insert the first vertex, that is source vertex, into it. Okay. This also what we'll do is we'll remove the topmost element in the stack. Okay. And then insert all those which are connected to that particular topmost vertex. Fine. As we know that stack, we can insert also from here and we have to delete also from the top itself. So this is what will be following the pattern. So first A is there. Now first we'll delete the topmost element. Right now only one is there, that is A. We'll delete this. Okay. And we'll mark this A to be visited, that is true. And A will be our first element to be traversed or searched. Now connected to A are which all? F, C and B. So you can insert this in any order. That is not important. So B, C and F, suppose I inserted. Now next element to be deleted will be F, because we delete from the topmost. So okay, F will be deleted. F will be marked as true over here and F will be placed over here as well. Okay. Now which are connected to F? E and A. A is already visited, so we'll not insert A again. Next is E. So we'll insert E into the stack. So our stack is going to look like something like this. B, C and E. E will be inserted. Right. Now we'll delete again the topmost element. Topmost element is E. So E will be deleted and E will be marked here as true. It will be deleted from here. Now which all are connected to E? Which all vertices are connected to E? C is connected. F already is visited, so no need to go there. C is connected. C is already there in the stack. So this also one condition check is that you have to check the stack also. If it is already there, then no need to insert it again. So C is already there, so we will not insert it again. Let it be like this. Now again we'll delete the first topmost element in the stack, that is C. So C will be deleted. C will be marked as true and it will be the next element to be searched. Now which are connected to C? D is connected to C. B is also connected to C. B is already inserted there. So D we will insert it again in the stack. So we'll insert D. Okay. Now we'll delete again the first topmost element, that is D. So D will be deleted and D will be marked here also as a true, that is it is visited now. Which all are connected to D? Nothing is left to be connected to to be inserted to stack because D is connected to C and C is already visited, so no need to insert it again. So will not perform any insertion here. Now next element to be deleted from stack is B. So B will be deleted. B will be marked true here, that it is visited, and B will be the next element to be searched. So this is the sequence we got. And as you can see, now the stack is empty. So until unless the stack is empty, you have to perform this operation. Once it is empty, no need to perform this operation again. We can stop there. So that will be our stopping criteria of the algorithm. Now this is what we got. So you can see here, A is traversed first, then F, then E, then C, then D, and then lastly B. So this is one depth traversed first or searched first, then the next depth. So this is your depth first search algorithm, and this is how it works. So we are going to now write the code for it, and we'll be using these three concepts itself, guys: stack and a Boolean array which will store true and false, and maybe a list which will store the adjacency list that is called as, that is which vertex is connected to which all other vertices. To maintain that, we need one array list, and then we need one stack and one Boolean array. So using these three data structures, we are going to implement the concept of depth first search. So let's go to that. So we have come to the Eclipse IDE here, and I'm using Eclipse IDE to write out the code. You can use any other. Where the already I've created a class graph search where there is the main method of the class. So we'll be writing down the code in this itself for depth first search. So let the main method go down. Okay. So as I've told you that we need three different things here. One is here the concept of stack. Then one we need a Boolean array to keep track of which all nodes are visited, which are not. And then one more list that is your adjacency list. So let's create all these. So first will be the number of vertices, which will be denoted with the help of variable v. Then we'll have a array list, which is of type integer. This is will be maintaining the adjacency list. Okay, you can give any name to this, which is an array. So if we can give maybe adj. Okay, I think we have to import the class. So yeah, let's import it. And this should be the wrapper class. We cannot use primitive data type over here because all these classes which are defined in the collection framework takes wrapper class to be the data type for it, not the primitive data types. Now we have to create the constructor for the class graph search so that we can initialize how many vertices are there. Also, we can initialize the adjacency list. So let's have the constructor here for the class graph search, which will take input as number of vertex, which will take as a parameter. So it is a parameterized constructor, which is taking one parameter, that is number of vertices. So we'll initialize v with this number of vertex. Then we are also going to add, initialize the adjacency list, new array list, number of vertex will be its size. Okay, this will be a square bracket here. So yeah, this is done. Now let's create the structure for the adjacency list. Like we created an array list where all the vertices are there, but each vertex should be connected to a list that is called an adjacency list, to which that will represent that that particular vertex is connected to which all other vertices. So that's what I'm going to do here. That is int I is equal to 0, and then I should be less than here a number of vertices, and it will go till I plus plus. And then here I am going to initialize this. This is equal to new array list. Okay, so this is done. The constructor for the graph search class is created. Closing, this is also closing. Now we have to create the elements inside this adjacency list, that is the edges which are there that should be inserted. So for that I'm going to create a method void edge, which will take two parameters, int x and int y, and which will be inserted into this adjacency list. So adjacency of x will be having, you have to add y here. So add is an inbuilt function which is being used. It is inside the collection framework, or you can say it is inside array list class. So that's it for adding the values or edges to the adjacency list. Now we'll write down our main function of depth first search. Okay, it will take input the first source vertex. Okay, let it be source vertex as a name. Now in this the logic is we have to use stack, we have to use boolean array. So let's define first all those whichever is needed. So boolean array, maybe the name will be suppose visited. Okay, the size will be equal to your number of vertices. We need a stack now. So how to create a stack? We have to use inbuilt stack class and create an object for this. Okay, let it be s1, which is equal to new stack. Then we have to import this, I guess. So let's import it. In the java.util package, it is there. So we have to import that. So now stack and this visited array is created. Now we have to come to the logic. So every time we should peek into the stack and see which is the topmost element, then pop it out, delete it out, and then go to the adjacency list, and whichever is connected to that, we should insert into the stack again, and then perform the whole operation. So let's write the logic for that part. So s1 dot, first we have to push the source vertex, Okay. And also change its value in the visited to true, because initially it will be false. Okay, let this be represented also as a node. Now the condition check will be there. So while there is some element in the stack, we have to keep doing this. Okay, it should be s1 dot empty. Yeah, so empty is a function which we are going to use. So till the stack is not empty, we should keep continuing and doing the process of deleting. So that will be s1 dot pop. Okay. But before this, what we should pop? So for that, you have to peek into the stack, right? So your source vertex will become now whatever you peek into the stack, right? And then you should pop out the topmost element. Okay. So while loop is completed here, now we have to do what? Check the adjacency list, whichever are there that has to be inserted, and also we have to keep a check that the visited vertex, visited node should be marked as true, or it should be false first, then only we can insert it. So let's write the code for that. So for int I is equal to 0, adj of source vertex should be its size. So yeah, size is the function there. We can have that till the size of it, like complete list you should scan. Okay, should be I less than. Now here your node will become adj of source vertex, adj of source vertex dot get function is will be used, get of I. Okay, so get of I will tell you that particular at that particular index, whatever is the value it gets you, like it fetches that value, because that's what we'll be comparing, right? Is it inserted first or not? Now here we have to also keep a check that in the visited uh, array, it should not be true. It should be false. If it is true, it means it is already visited. So that check should also be done. So s1 dot push. If it is not, then only we should perform push. And what we should push? Node, whichever node we are referring that time with. Okay. Now, okay, this is closing here for loop. Okay. Now we will do the changing of true to false. So if visited source vertex is equal to false, then we should change it to true, right? Visited source vertex should be changed to true, and also it should print. Nowhere we are printing, so let's print it here. So we should print what here? Source vertex, because that is the vertex being visited that time. Okay, and we'll change it to true. So that's it, I guess. This is the ending part of it. This is end of the function. So yeah, this is our depth first search algorithm. Let's call this in the main function now. So to call it, we have to make an object of class graph search. So let's make it quickly. Graph search g1 equals to new graph search. So to pass the source vertex should be passed over here, right? Okay, no, the size of it. So size, let's take the same example which we have to taken for the explanation. So in the explanation, if we go, you can see this is the graph. So it is connected to A to B, A to C, A to F. So we'll insert all these values here. So let's call G1 dot edge, G1 dot edge. Okay, I'll copy paste it. Let's save some time. So how many edges are there? 1, 2, 3, 4, 5, 6, 7. 7 edges are there, right? Okay, let's go back. We have inserted so many. Okay, let's insert the values of it and see. So 0 is connected to 1, 0 was connected to 2. Then 1 was connected to all except 5, you remember, right? So 1 is connected to 0, 1 is connected to 2, 1 is connected to 3, 1 is connected to 4. So yeah, let's see. I think 2 was connected here. So yeah, if I represent this with numbers like 0, 1, 2, 3, so it will be something like this. This will be 0, 1, 2, 3, 4, 5. So 2 is connected to all except 5. 1 is connected only to 0 and 2. 1 is connected only to 0 and 2. Okay, let's, my mistake. 2, 2, then 3, and then 4, uh, again 4, then 5, and again 5. So yeah, these are the number of, so 1 is connected to 1, 0 and 2. 2 is connected to 1, 0, 3, 4. 3 is connected to, I think, only 1, which was 2. 4 is connected to, let's check, guys. 4 is connected to 5 and 2, and 5 is connected to 0 and 4. Okay. So 4 is connected to 2 and 5. 5 is connected to 0 and 4. I hope this is right. Okay. Let's call the function g1 dot depth first search and pass 0th index there. Let's have one print statement as well here, stating that result of depth first search. Okay. Okay, so it is not printing correct. Again, there is something which we have missed, so let's check it out. Okay, so as we are checking what went wrong, so we'll see here depth first search, it's correct, source vertex stack, then we have to push it to it, then this node will refer the current vertex being visited, s1 dot empty source vertex, then we'll pop it out. Size, okay, till the size of the edges list we have to traverse it all and then push it into it. It's false. Okay, it's looking correct. Let's figure it out. So I think, okay, we will, okay, this while loop should not end here. It should end over here. Let's see if it works. Okay, yeah, so that was the problem. We have closed the while loop over here itself. So it should be closed at the end. So this is the output of the depth first search, 0, 5, 4, 2, 3, and 1. So you can see this is also the output. We can match it with what output we got. So it is 0, 5, 4, 2, 3, 1. 0, 5, 4, 2, 3, and then 1. So it's correct, right? This was one depth, and then this was the next depth. So 0, 5, 4, 2, 3, and 1. So yeah, our output is correct for this program. So you can see, just I'll go through the code once again. So what we did was we created a depth first search function here. Before that, adjacency list was created, and the edges which were connected were added to that adjacency list. And then while performing depth first search, we have to keep no we have to use these two data structures, the stack and one boolean array, which will keep track of whether the node is visited or not. And that's what is done. We have to peek into the stack, whichever is the first element, we have to delete that, and whichever is connected to that particular deleted vertex, insert all that to the stack, that is push all that to the stack, and then also check if it is the visited vertex value is false or not. If it is false in the visited array, then should make it true, and that will be printed also as an output. And then in the main function, we have created the edges, that is the adjacency list is created, and then the depth first search method is called, and that will give us the desired result. So this was all about the implementation of your depth first search algorithm.
So let's start with the heap concept. So as I told you that heap is a complete binary tree, right? So what happens in heap here? Here a root node key is compared with its child node and arranged accordingly to that. Let's take an example. Here, if I am having this, so the first condition for the heap that it must be a complete binary tree. So is it a complete binary tree? Yeah, this is a complete binary tree. So this is my heap. Now what will happen here? I will compare the root node key with its child node and I will arrange accordingly. Now how to arrange? So the heap can of two types. It can be a minimum heap and maximum heap. So what happens in minimum heap? The parent node value must be less than or equal to its child node. Similarly, for maximum heap, the parent node value must be greater than or equal to its child node. Now let's take an example of maximum heap. So this is an example of maximum heap. So you can see that here this is my root node, right? So here this will be a parent node for this node and this node, right? And the values of this node, that is root node, must be greater than or equal to its child node. So here you can see the value is 70 and the child node value is 60 and 50. 60, 50 are smaller than 70, right? So the condition was the parent node value must be greater than or equal to its child node. Similarly, here 60 will be a parent node for this 40 and 30, right? 40 and 30 are the child node and the value of this parent node is greater than its child node. So this is a maximum heap. Now here if you see, this node will be a parent for these two, right? So the value of this node must be greater than or equal to its child node. So here the value is 50 and its child node value is 20 and 10, which is less than the value of its parent node. So this is the concept of maximum heap. Now if you want to represent it into array, then we have to insert level by level, right? So if I'm writing here 70, 60, 50, 40, 30, 20 and 10. So this is the array representation of maximum heap. So always remember the root node value must be the greatest in the maximum heap. So here you can see that the root node value is the maximum here. Now as I told you that parent node value must be greater than or equal to its child node. So here you can see that this node is a parent for these two and the value is greater, right? 70 is greater than 60 and 50. Similarly, this is a parent node and the value is greater here. So 60 is greater than 40 and 30. Similarly, this is a parent node and the value is 50 here, which is greater than 20 and 10. So now coming to the time complexity. So what is time complexity for the maximum heap? So the time complexity for removing as well as inserting an element is big O of log of n. So now how to create a maximum heap? So here you can see that we are having the input values. So let me create maximum heap. So first I will write here 33. This is my first node, right? So this is only one node. Let me create its child node. So I will write here 31. Now I have to create maximum heap. So what's the concept of maximum heap? You have to do only one thing. The main key point is that if you see that parent node value is less than its child node, then just swap it. And if it's greater than, then do not swap it. So here if you see that 33 is greater than 31, right? So we don't have to swap it. Now if I'm writing here 39. Now here you can see that the child node value is greater than its parent node, right? So what I have to do? I have to replace, I have to swap it. So I will swap it and now 39 will go here and my 31 will come here and 33 will be here. Now, after that, what will happen here? I'm having the element as 8. So 8 is less than 31, right? So I don't have to swap it. Then coming then 12. 12 is also less than 31, so I don't have to swap it. And here you can see that this is a parent node, right? So the concept is same, that parent node value must be greater than or equal to its child node. So 31 is greater than 8 and 12. Now, coming further, here, I will insert 17. So 33 is greater than 17, so I don't have to swap it. Now after that, once again, let me write here 25. So once again, 25 is less than 33, so I don't have to swap it. Now if I'm writing here 42, so 8 is the parent node and this is the child node. So the child node value can't be greater than its parent node in maximum heap, right? So I have to replace it. So when I'm replacing here, so what will happen here? So 42 will come here and then 8 will come here. Now, after that, if you see, then 31 is the parent node for this 42. So can the child node value can be greater than its parent node? No. So once again, I have to swap it. So 42 will come here and 31 will go here. Now, if you see, then 39 is the parent node for this 42. So again, it's not possible. I have to swap it because my parent node should always be greater than or equal to its child node. So I will replace 39 with 42. I will write here 42 and it will be my 39. Now if you see, then 42 is the parent node for this two, right? And the value is also greater. Now, moving next, let me insert some more elements. So I'll write here 24. So if you see here, 24 is less than 31. So it's good to go. Next, I'm having 29. So if I'm inserting here 29, let me write here. The figure looks good. So now if I want to insert 29, so on inserting 29, you can see that 29 value is greater than its parent's node. So I have to once again swap it. So on swapping, 29 will go here and then 12 will come here. Now, you can see that this is the maximum heap that I have created as of now, right? 42 is the parent node, so its value must be greater than its child node. Again, this is a parent node, its value must be greater than child node. This is a parent node, its value must be greater than child node. Same here. Now, once again, I have to insert 60 here. So if I'm inserting here 60, then you will see that 60 is greater than 29. So I have to once again replace it, right? So what will happen here? 60 will go here and 29. If you see here, 39 is the parent node and its child node is having value 60. So once again, I have to do the swapping. So 60 will go up here. 60 will go here and then 39 will come here. So if you see here, 60 is once again having the higher value than 42. So once again, I have to replace it. So 60 will come here and then 42 will be here. So you can see that this is the creation of maximum heap where each parent node is having the higher value than its child node. And even parent node value can be equal to its child node also in maximum heap as well as minimum heap also. So we have seen how to create a heap. Now let's see that if we are having the maximum heap, then how to delete the element from max heap. So let's suppose this is a heap I'm having here and let me insert the value here. Let's suppose here I'm having as 38 and here let me insert 28. I will insert here as 13 and then I will go here as 8 and 18. So here you can see that this is my max heap, right? Because the parent node will be having the higher value as compared to the child node. So this is my max heap. And now if I want to delete the element in max heap, then how shall I delete? So always remember, if you want to delete the element, then the root element will be deleted. So which one is the root element? So root element is 38. So 38 will be deleted. Now you might have a question that after deleting 38, then which element should come at the root value? So if you are thinking that 28 will come, then it's wrong. Let me explain you. Here, first I will create an array representation. So as we know that if you want to insert the elements of heap in an array, then it will go level by level. So here it will be having 38, then 28, 13, 8 and 18. This is the array representation. Now, as I told you that removal will be done only on the root value, right? So this is the root node 38. So I will delete here 38. So 38 will be deleted. Then which element should come? So always remember the last element will be coming as the new root values. So in this heap, which is the last element? 18. And here also in array also you can see that 18 is the last element. So 18 will come here, and then my 38 has been removed. So here if you now see the array representation, so let me write here 18, 28, 13 and then 8 I'm having, and 38 has been removed from heap. So let me write 38 like in this way. So in this heap, I am having only 4 elements, right? Now, as I told you that in maximum heap, the parent node value must be greater than its child nodes. So here you see that 28 is greater than 18, right? So what will happen here? Let me replace 18 with 28. So 28 will come here and then 18 will come here, right? Let me replace here also. So in an array also, this will be 28 and here it will be 18. Now, if you see here, so once again if I want to remove the element, then I have to remove this root value. So 28 will be removed, right? And which is the last element? 8. So what will happen here? Let me remove 8 here. I will insert here 8. So 8 will be coming here and then 28 will be removed. So let me write here the array representation. So I will be having here 8, 18, 13 and then this will be 28. So I have removed 2 elements, right? 28 and 38. So now I'm having only 3 elements left in my heap. So if you see here 18 and 13 both are greater than 8, right? So what will happen here? First I will compare with 18 and 13. Which one is greater? 18, right? So 18 will replace with 8. So I will write here 18 and then 8 will come here and 13 will come here. So if you see the array representation, then it will be 18, 8, 13 and then 28 and 38. These are the 2 elements which have been removed from the heap. Now if you see, then if I want to remove the element from max heap, then 18 will be removed and then 13 will come here. So what will happen here? Let me remove 18 and 13 will come here. So 13 will come here and 18 has been removed. So if you see my new representation of array, then it will be like this. My 13 will be here, right? My 18 will be here. So 3 elements has been deleted from this heap. So right now I'm having only 2 elements, and as we know that parent node must be always greater than its child node. So it's correct, right? It's my maximum heap. So what I will do now here, once again I will remove 13 here, right? So what will happen here? I'm having only 1 element left, that is 8. So if you see the array now, I'm having only 1 element left, 8, right? And 13 has been also removed. So you can see that here the sorting of this array has been done. So here you can see that this is the array that I'm getting. So let me write here once again 8, 13, 18, 28, 38. So here you can see that sorting has been done. So this is nothing but a heap sort. So if you want to create heap, I've showed you how you can create heap, and also you can delete the heap, and you have also seen the sorting while deleting. So this is a heap sort. So this was the idea about the max heap. So now let's see what is minimum heap. So in minimum heap, the parent node value must be smaller or less than to its child node. So let's take an example. So here you can see that this is the parent node for this 20 and 30. So here the value is less than its child node. Similarly, this is the parent node for these 2 nodes, right? So here you can see the value of this parent node is less than its child node. Similarly here you can see that 30 is less than 60 and 70. So this is the parent node for 60 and 70, right? And also remember, the time complexity of removing and inserting an element will be same as maximum heap, that is big O of log of n. Now if you want to see the array representation, so we know that the elements of a heap will be inserted level by level in an array. So it will be like 10, then 20 and 30, 40, 50, 60, 70. So one key point that you have to remember, that parent node value should be smaller or equal to its child node value. Now let's see the minimum heap construction. So here input is 33. So let me write 33. So this is my root node, right? So let me write its child node. So here you can see that I'm having the value 31. So we know the concept of minimum heap, that the parent node value must be smaller than its child node. So here what will happen here? 31 will come here and then 33. After that I'm having 39. So here you can see that 31 is having the smaller value as compared to its child node. Now here you can see that I'm having 8 here. So 8 has to be go here, right? So 8 will go here and then 33. If you see here, the concept was that the parent node value must be equal to or less than its child node. So here once again you can see that the child node is having the smaller value, right? So I have to once again replace it. So 8 will go here and 31 will come here. Now if you see, 8 is my parent node for this one. It is having the smaller value. Similarly, 31 is having the smaller value as compared to its child node. Now after this, I will insert the value as 12. So once again 12 is there. So once again I have to replace it with 31 and 31 will come here. Now if you see that 8 is the parent node for this one, it is having a smaller value. 12 is the parent node for this one and is having a smaller value. After 12 I'm having a 17. So 17 will go here. So once again 17 is having a smaller value, so it will go here. 17 will go here and then 39 will go here. Now after this I'm having 25. So 25 will be like this. And here you can see that 17 is my parent node and it's having a smaller value as compared to its child node, right? So let me write here once again so that you can understand easily. So up to here if you see, so this is my parent node for these two and it is having lower value. Similarly, this is my parent node which is having lower value than its child node. This is my parent nodes which is again having the lower value than its child node. Now after inserting this, once again I will insert here 42. So yeah, it's good to go because the child node is having greater value than its parent node. Then again I am writing here 24. So the parent node should have the lower value as compared to its child node. So I will replace 33 with 24. So 24 will be here, 33 will be here. So after this I am having here 29. So 29 will be my left node of 31. So 29 is having the smaller value. So once again it will go up. So 29 will go here and 31 will come here, right? After inserting 29 I am having the last element, that is 60. So 60 will be the right node child of this 29, right? So 60 is greater than 29. Yeah, it's good to go because we know that the minimum heap parent node must be smaller or equal to its child node. So now if you see this node, so this node value is less than its child node. Similarly for 12 is having less value as compared to its child node, right? Similarly here 17 is having the less value as compared to its child node. Even for 24, 42 and 33 are the child node values which are greater than 24. Now comparing to 29, 31 and 60 are having the higher value than its parent node. So this was the overall idea about minimum heap construction. So now let's understand the concept of heapify. So what is heapify? It is a process of creating a heap, right? And also it's having a time complexity of big O of n. So here you can see that I'm having a complete binary tree, but it's not a max heap. So now earlier we have seen that while creating a maximum of heap, we were going from left to right in an array, right? Because we know that the elements are inserted in an array level by level, right? So if you see here, this is my heap. So if I want to insert the element of heap in an array, then I have to go through level by level. So I'm going from left to right here, 8, 18, 13, 10, 38, 23 and 16, right? Now in heapify, I will go from right to left. So what I will do here, which one is my last element? I'm having 16 as my last element. So after 16, if I'm moving to 23, again it's a leaf node. So I don't have any child node, so I'm unable to compare. So I will go from 23 to 38 and then 38 to 10 because these are leaf nodes, so I can't compare, right? Now after 10, if I'm going there, then I'm getting 13. Now 13 is my parent node and it is having two child node. So here you can see that I'm having the value of child node as 23 and 16 and I want to create max heap. So in max heap, your parent node value must be greater than the child node, right? So what will happen here? This is 8, this is 18 and now my 13 will be replaced with 23. So first we'll compare the child node elements, which one is greater, 23, right? So 23 will go here. So I'll getting here 23 then I will be getting here 10 and then 38, and here I will be getting as 13, and here I will be getting as 16. Now after 13, since I am going from right to left, right, I will be coming to 18. So if I am coming on 18, again it's a parent node. So here you can see that this child node value is greater than parent node, right? So I have to replace it because the parent node value must be greater than its child node. So let me replace it. So this is 38 and this is my 18. Now coming further, since I am going from right to left, I will come to at 8. So again, on coming to the 8, you can see that its child node is having the higher value. So I have to replace, right? 38 and 23. Which one is greater? 38, right? So 38 will go here and then 8 will come here. Now here you can see that my 8 is a parent node, right? But its value is less than its child node. So once again, I have to replace it. So this will be my 18 and this will be 8. Now if you see it, this is a maximum heap, right? Because in maximum heap, parent node's value is greater than its child node. So here this is 38, its value is greater than its child node. Similarly, and here also this parent node is having the value greater than its child node. So this is the basic idea of Heapify, in which I am doing the arrangement while comparing. So this was all about Heapify. So now let's see the coding for heap sort. So I will be using Python for heap sort algorithm. So I'm using Jupyter Notebook here. So I will go and click on new. Then I will click on Python 3 file. And let me give here the name as heap sort. So the best thing about the Python is that in Python we are having the modules. So I'm having a heap queue module from where I can take two functions, that is heap push and heap pop. So heap push will convert the list into heap, whereas heap pop is used to remove the element, or you can say that popping out the element from the heap. So let me write here the modules. I will write here first from heap queue import heap push, and then I will once again write same thing from heap queue import heap pop. Now after importing the heap push and heap pop function, what I will do, first I will create a list. So let me write here the list name as L1, and inside this list, and let's suppose I am giving here the values 2, 3, 5, 7, 35, 46, 79. Okay, so these are the values that I am giving. Let me write down some more values, 55, 45. So this is my list. So now what I will do here, I will create a function here. So I will write here def, and the function name, let's suppose that I am having heap. Let me write here heap. Now what I will do here, inside this function I will create a for loop. So I will write here for I in, and let's suppose that I am giving here the parameter L. So this is my L1 list, right? So I want to call this function. So how can I call this function? So I will simply write here heap, and inside that I will pass the parameter L1. So I will call this function. Now what I will do here, as you can see that I am creating a for loop. So I will write here for I in L. So you can see that this is my list that I have created, right? And I am passing this list value inside this function. Why I am doing this? Because I will be using now heap push function. So I will create here heap push. So inside my heap push function, what I will do, I will create a variable heap1. So let me create the heap1 variable here, which will contain the empty list, right? So I will pass here heap1, right? This is my empty list, and then I will write here I. So what will happen here, if you see here, so basically I am using heap push function. Let me write heap push. So here it will be p, right? So what I am doing here, heap push function will change the list into heap. So here you can see that this was my list, right? L1 is the list, and I am passing into this, right? And this is my empty list. So now what I am doing, I am doing iteration. I am using for loop. So this is my L1, right? This is a list. So I will take the value one by one, right? And heap push function will convert the list into a heap. So that's why I'm doing iteration here, right? So after this, what I will do, I will create one more variable. Let's suppose I'm giving the name of the variable as sorted, and this is again my empty list. Now, so after this, what I will do, I will create a while loop. So I will write here while, and I will give the condition while heap. So this means while my heap is not empty, then I'll give here sorted, and then I will be using the append function. And inside this append, I was telling about the heap pop function. So heap pop function will pop out the element from the heap. So I will write here heap pop. So inside this heap pop function, what should be the parameter? So if I want to remove the element from the heap, so what was my heap? My heap name was heap1, right? So I'll write here heap1. So it will remove the element one by one. Now after this, what I will do, I want it to be print out. So what I will do, I will just write here return, and then I will write here sorted. So if I'm executing it, so on executing, you can see that it's showing index out of range. So what's the error here? Here you can see that heap is the name of the function. Heap1 is my variable name, right? So I will write here heap1. So now if I'm executing it, now let's take a quick recap for this course. We have started this course by understanding what is data structure. We have seen different types of data structure. Moving ahead, we got to know that why it is required to understand first what is binary tree, then we will jump to the heap concept. Now, in binary tree, we have seen different types of binary tree, mainly focusing on complete binary tree. Then we have seen the concept of heap, in which we have discussed about minimum heap and maximum heap. And after that, we have also seen heapify. And at last, we have seen heap sort logic with coding example.
Now let's talk about the concept of hash tables. So what is hash table? How is this hash table implemented in Java? Now before understanding all that concept, we have to understand what is hashing. So because hashing is a concept which is being utilized when we talk about implementation or no, coding of hash tables or hash map and so on. So what is hashing? So hashing is a black box technique in which if you pass a key, the key can be anything, a number or a string. If you pass a key to that black box function, the output will be a code that is called as your hash code. Okay, now why this input and why this output? What is the whole concept? Why is it required first of all? Okay, so let me explain you. So suppose I'm talking about a function. Okay, let this be represented as h of x. Fine. Now this will pass a key. Okay, this key can be a string, it can be an integer, it can be anything, any number or a sequence of characters, anything. Okay, output will be a code, also called as your hash code. Okay, now what does this hash code is used for? So hash code tells the position where that particular key is going to be stored at the backend in the computer system. Okay, for example, suppose there are these many, this is your array you can assume, or this is a space which is there where your data will be stored. Fine. Suppose the data example I'll take is of a student. Okay, so a student will have its name, will have its roll number. Okay, now this data has to be stored somewhere. When we talk about the storage in RAM, that is a temporary storage, right? So when we talk about storage in RAM, this is how the storage is structured. So suppose this data about a student who has a name and a roll number has to be stored somewhere. Okay. Now that data or that name of a student, suppose, is a key. Okay. That key will be passed to this hashing function or hash function. And the output will be a code. That code will be nothing but that position in the storage area where that particular data of a student will be stored. That name or roll number of a student will be stored. Okay, suppose the key or the name of a student is something called as maybe ABC. Let the student name be ABC. So ABC will be the key which will be given to this hash function, and output will be a code. This code is, suppose, for ABC key is your 4. Okay, so starting from 0, 1, 2, 3, 4, and suppose there are more numbers, more storage space here, 4, 5, 6 and so on. So at fourth location we'll store the data of the student ABC. Getting it? Next, suppose there is some other another student or whose name is maybe Priya. Okay, so Priya name will be this key. It is a key here. It will be passed to this hash function, and the code or the output which we get out of this hash function is supposed 2. Now at second location, the information or the data related to Priya student will be stored. So this is how hashing works. Okay, this whole concept of finding a code out of a given key. That key can be anything, either a string or either an integer value. Like in this example, it was a name. So for the Priya name, the code was, or the output of this hash function was 2, and we stored there. So this is the complete concept of hashing. Okay, so you can say it is a one-way function, meaning if you provide a key, it produces a code or a hash value. Okay, but if you provide a hash value, it won't produce a key. Right, now what is this function? So this function is designed in various ways. This function can be like as simple as picking the last character of a string and converting it to its ASCII value, and that ASCII value becomes the index or the hash code. Okay, or it can be as complex as some mathematical calculation over the ASCII values of a given string. So we are not bothered about what this hash function is going to be, although the complete hashing concept depends on this hash function itself. The more better and well structured your hash function is, that good the complete hashing technique will be. Why I'm saying that? Because a good hashing technique is only that where there is minimal collision. Now what is this collision? So we'll take this example again and see. So the same hashing function, I'm going to take another example. Okay. Now, let's see here. Suppose there is a student called by the name of Priya. Okay. Then another student is there by the name of maybe Pooja. Then there is another student maybe by the name of, you can say, what, Rohit. Fine. Now, we have to store these three data or three names of a given student into the storage space. Now, Priya will be passed to this hash function as a key. Okay, it will produce a hash code. Suppose it produces the hash code as 2. So this Priya will be stored at location 2. Then there is another student named as Pooja. It will be passed as a in the hash function, and it will produce the hash code to be suppose 4. Okay, at the fourth location we'll store this Pooja. Now next is your Rohit again. So Rohit is passed in this hash function, and the hash code which it produced was again 2. But at the second location already there is another information about a student named Priya is stored. So where will this Rohit be stored? Now this complete situation is called as your collision. And a good hashing function should avoid this collision situation. Okay, so when we talk about its implementation in Java and where it uses hash map and hash table kind of a concept, there this collision is resolved. Now how is this resolved there? It is resolved by using the concept of linked list. It means what? Like suppose the second student here, Rohit, also had a hash code of 2, but 2 was already occupied by another student information, that is Priya. So what will happen? There will be a pointer to from this place, that is second index, to another node. Okay, and this node will be having the information. This is a node of a linked list. Okay, and this node will be having the information of a student Rohit. This will also be like one node of a linked list. Okay, which will have the value, that is Priya, the name of the student, and the address to the location where this node is. Like how in linked list it is. Every node of a linked list stores a data and a pointer to the next node, right? Similarly here, the data will be the student name Priya, and then address to the next node, that is this node where the Rohit information is stored. Getting it? So this is how collision is resolved. So there are multiple techniques to design this hashing function. Then there are multiple techniques also to resolve the collision whenever it happens. So one of the way I told you is by using the concept of linked list. So all those keys which are mapped to the same location are linked with the concept of linked list or linked as a nodes. Okay, but we always try to have a hashing function which has minimalistic collision, and that's a good hashing concept or a good hashing technique. Now we'll talk about what are those ways in using which we can implement these concepts of hashing and how it works when it comes to Java programming language. Now let's talk about the implementation of the concept of hashing in Java programming. So for this, what will be the problem statement is that we are going to write a program using which I'm going to tell you how this hashing concept works, or what is hash code, and then what are different hashing functions which we can use in Java programming. So guys, there are so many hashing functions which already exist, like MD5, SHA. All these hashing functions produces 16-bit hash codes. So you can do the direct implementation of these hashing functions also. But even if you don't do, like, how in a most simplest way you can use the concept of, or is Java using the concept of hashing? So for that, we will talk about two of the concepts of collection framework in Java. One is your hash map, and the next one is your hash table. Okay. So hash table is an interface which is defined in the collection framework of Java, which we'll be making use of directly here to write down the code and understand the whole concept of hashing. So what happens basically is, so let's try to understand that first, and then I'll come to the coding part. Suppose I'm using the concept of hash map. Okay. Now hash map is kind of a associative array where there are two fields. Okay. One is your key, and other is your its value. Okay, so this pair is always stored in hash map as well as in hash table. Both is same, just with a few minor differences, which I'll tell you what is the difference between them. So key and value pair will be there in both hash map and hash table. Taking example of a student data. Okay, so every student will have a name, and suppose that student name will have a roll number as well. Okay, so every name of a student is associated with roll number. Let's take few examples. For example, Priya is a name, and the roll number of student Priya is 3. Pooja is another name of a student. Roll number of the student Pooja is 2. Then Rohit is another student whose roll number is suppose 6. Okay. Now, how hashing works here? So what happens is, when we create a hash map and store these values there, backend what happens is that this particular key, that is Priya is a key here, Pooja is a key here, Rohit is a key here, and these are the associated values with that. Okay, so for the key Priya, this Priya will be passed to the hashing function, which is an inbuilt hashing function when we use the concept of hash map and hash table. In fact, for every other objects which we create of the wrapper class in Java, there is a hash code. I'll show you the implementation or whatever I said right now in the IDE also. But try to understand first here the concept, the logic. That is, the student Priya is passed in the hashing function, and it generates a hash code. Okay, and suppose this hash code is generally a very lengthier one, like it will have 10 digits or 11 digits or something like that. So which is you can do modulus operator on this and reduce it to a smaller number also, like suppose mod 10 I do, then I'll get one single value, right, of as a hash code. So you can do that, but normally, like by default, a longer 10 digit or 9 digits or 11 digits, some this kind of a hash value is generated. Okay, and depending on that hash value, suppose the hash value, and after doing mod operator or reducing it to a smaller size, I get a value of maybe 20. Excuse me. Okay, maybe 20. So in that case, this what will happen, that at the backend, at location starting from 0, somewhere at location 20, this information Priya and its roll number, the other value also, that is 3, both of these will be stored, Priya and 3. Getting it? Similarly, for the key Pooja, only as key will be Pooja here, the name of the student, which will be passed to the hashing function, and hash code, one hash code will be generated. And that hash code, suppose generated is maybe 25. So at 25th location, okay, the information about the key Pooja and its associated value, that is your roll number, both will be stored there. So Pooja and associated roll number, that is 2, will be stored there. Getting it? So this is how the hashing concept or hash code concept is being used by these two collection frameworks, or the concepts of collections of Java. Now let's see the implementation or coding part of it, and let's go to the IDE now. Okay, so here you can see I have already created a class named as hash, and there is a main method, public static void main here. So now let's go to directly seeing how the concept of hash code actually works in a real scenario. So for that, I'm going to create a hash map. Okay. So hash map, as I said, it takes two value, the key and the value of the other element. That is the example we saw, name and the roll number, right? So two values will be there. So similarly, you have to provide the data type also for those two values. So if I take name and roll number, the same example, continuing further as implementation, then name will be a string value and the roll number will be an integer. So let's take a string and then integer. Okay. After that, we should give a name to this hash map. Let that name be student. Okay. Then new keyword, which is equal to new keyword, which is used for allocation or creation of an object or allocation of space basically for the student hash map. So okay, new keyword and then again hash map, and then again you have to provide the data types which we have already provided, that is string and integer, and then round brackets and colon. That's it. Okay, it's showing some error. Let's see. I think you have to import it. So yeah, let's import this hash map. Okay, so hash map is declared here now or created here basically. Now let's add the student information, that is its name and roll number. So to do that, we use a concept of, or we use a method that is called as put method. And how it is called? So let's see, student dot put, and in the bracket you have to provide two values. First will be your name, that is maybe your, let's take Priya as a name, and let its roll number be, this will be an integer value, so 3. Okay, so I'll just copy paste this again and again just to save time, guys. So if you put here 3 students, suppose I'm going to put, so Priya, Pooja, okay, Rohit, okay, these are not my friends, just simply I have taken the names, and suppose 7. Okay, now to get the information, like okay, I have stored it, now let's check has it been stored correctly. So if you'll give a key here, it will give you the value, that is the roll number of that person, the student, as an output. To do that, how can you use, just see here, student dot uh, get. Okay, okay, we'll do one thing, let's put it under the for loop so that we can use it for all. Now, again, for before putting it in the for loop, there are two ways by which you can iterate over a given hash map. Let me tell you both of that. So two ways are there by which you can iterate over a hash map. Okay, one is by simply using the concept of set, and other is by using the concept of entry concept. And that, what is that, I'll tell you. So first, let's see the concept of set. Okay, so what you will do is we'll create a set here which is of type string. So all these data of the hash set will be converted as a type of set. So let's create a set first here. Okay, and to do that, we use set class and then string, the data type for that, and then any name you can give. I've given data as a name of the variable of that set variable. So data on, and then we can call student dot key set. Okay, so I'm going to make the student hash map as a set of data or a set of keys. Okay, think we have to import this also. Okay, let's import that. Now we can use for loop on this. Okay, so I'm using for each loop concept where string I for data. What I'm going to do is I'm going to print. Now here I'll use the get method. So get method, put method was used for storing the data. Similarly, get method is used for fetching the data. So get of I. So we can see here. Now let's run this code. So you can see that with respect to all these names, all these keys, we got 3, 2, and 7 as here values for them. They're all numbers. Now suppose you want both to be printed, the key as well as its value, that is the name as well as their all numbers. So for that, you can use another concept is there, which is your entry set concept. Let's see what happens there. Okay. Okay, so after this. So in this, what we'll do is we are going to create an entry set. Okay. And this takes map dot entry, and the data type will be a string and integer, because this time we are creating in pairs, this entry set. Okay, so it will be in pairs, a string and then integer, the name and the roll number. Okay, and then let it be data1. I just change the name of student dot entry set will be called as a function, then semicolon. Okay, this is how we create a entry set. Okay, now using this again for each loop on this entry set, we are going to iterate over the given hash map. So for again, but here there you see that data type was string, right? But here the data type will remain same, that is map dot entry. This will be the data type, and here you should write string, and then you should write integer I colon over data 1. Okay, so in this we are going to iterate, and then I'm going to write the same thing, that is I dot. Okay, the here function is get key. So this will tell you the complete key, that I mean that is your name of the student as well as its roll number together, because you've created the entry set. Okay, so get key will give you the key, and then you can have again I dot get. So you can see here the get key, get value, get class, three methods are there. Get key we used, which will tell you the string part of it. When get value you do, it will tell you that integer part of it. So we'll use get value. So both we can get the key and the value, that is the name and the roll number of the given student. Okay, so that's it. We'll save the file and then just let's run and check. So you can see here, this is the output of the earlier for loop, and then this is the output of the second one, that is entry set we used. So this is how we iterate over it. Now, let me here tell you where is the concept of hashing here used. Okay, although I have told you that when this particular no, set, that is the hash map, that is the name of the student and roll number is stored somewhere, first the hash code is generated for it, and then it decides the position of that particular data to be stored at the backend. Let's print here I dot hash code. So you can see here the hash code is an inbuilt function already in Java, which helps you to get to know what is the hash code generated for each of this data. So I here is nothing but the key, that is the string part here, that is the name of the student in this example, that is Priya, Pooja and Rohit. Okay, so let's see what is the hash code generated. So guys, you can see here, okay, I will just comment out some of the lines, okay, so that it's easy to understand the output. So you can see the output here. So it has generated the hash code. First one is for Priya, the second one is for Pooja, and the third one is for Rohit. Right? So this is the hash code generated. Okay, one more thing. Okay, it's not necessary always that this is how the order will be. So let's print this for that matter and check what is exact hash code. So 3 is the roll number. So 3 is Priya itself. So its hash code is this one. Then 2, its hash code is this, and then 7, its hash code is this. So you can see how longer hash codes are generated by default. So most of the time what we do is we get mod of n, and this mod of n we do. N is nothing but the total space that is there. Suppose initially we use a number of, suppose we are using arrays to decide the position. So suppose the array size is 10. So we'll do mod of 10. What is the total complete size where these data are going to be stored? That becomes your n, that is used as a mod here to bring the complete hash code to that range. So if you do mod of 10, it will come to the range of 10 storage space. Okay, 10 indexes. If you do 12, it will come to 12 indexes. Okay, so in that range it will come. So let's see what's the output after that. So you can see here for 3, the 3 roll number, that is Priya, the hash code is 9. For 2, the hash code is 2. For 7, hash code is 0. So you can see it is stored at that particular location ranging from 0 to 9. When you do mod of 10, it is 0 to 9. Okay. So these at the backend, what would have happened is that these particular data would have been stored at this particular indexes. So that's how the concept of hashing works inbuilt or by default in Java programming. If you can see this by the whole help of the concept of hash map, or even if you don't create hash map, like suppose directly I create a string here, a is equal to and hello suppose. And if I try to print, okay, this will be capital S. And if I try to print a dot hash code, then also you can print the hash code value. So it's always that there is a hash code generated. So this is the hash code for string A. Okay. So that's all about the concept and implementation of hash map and hash table. So hash table, guys, it's similar in implementation, just that here you have to use hash table in class. And then you have to import this as well. And that's it. It will work in the same way without any error. Okay. But there is a difference between hash map and hash table. Okay. One is your hash table is your synchronized and hash map is not synchronized. I mean, hash tables are thread safe, so and hash maps are not. So that's a different concept here altogether, but that's how hashing is implemented using Java programming.
If you haven't subscribed to our channel yet, I want to request you to hit the subscribe button and turn on the notification bell so that you don't miss out on any new update or video releases from Great Learning. If you enjoyed this video, show us some love and like this video. Knowledge increases by sharing, so make sure you share this video with your friends and colleagues. Make sure to comment on the video for any query or suggestions, and I will respond to your comments.